Test, test. Oh. All right, are we ready? Are we ready? Should we do this? Yeah, good? All right. Hello, everyone. Welcome to VeloxCon 2025. This is our third VeloxCon, and it is amazing how much this has grown. The few people I've talked to so far this morning, I'm just hearing words like, this is so exciting. I can tell it's grown so much. The momentum is there. And I think this conference is going to be a testament to that. So I'm very excited. By way of introduction, my name is Ali Leclerc. I head up open source strategy at IBM, and I work with many different projects, Velox being one of them, to do community events like these. And I'm joined by Sridhar from Meta, engineering manager. And today we're going to be kind of welcoming you and doing a quick opening for VeloxCon. So I need my clicker here. So thanks for being here. I know it's early. I know there's traffic and all these great things that happen in the Bay Area on Tuesday mornings, but really appreciate you being here on time. And we're just going to take a few minutes to talk about what's been going on in the community for the last year. What's really exciting is this momentum, like I've been mentioning. So since the project started, we have today 334 total contributors. Since we met last year at VeloxCon 2024, we've added 64 new contributors. That's really awesome. Oh yeah, all right, woo! We have over 3,500 GitHub stars, 500 added in the last year, over 1,000 forks, so active development going on, which is really incredible. And then we have contributions from over 25 different companies. And look at that logo wall, that's awesome. A lot of those, it is. A lot of those companies are going to be here today talking about what they're doing, the work that's been going on, and we're really excited. You probably saw the agenda. This is like a jam-packed 2 days. So I hope everybody is ready to learn a ton. We are not leaving a ton of time for questions at the end of sessions. So I've told all of our speakers, after your session, go out and make yourselves available so that you can talk to people who might have questions and just kind of meet and network with the community. So really, really great to see. And then one other thing, social growth, I have to share. We just launched our Velox LinkedIn page. If you are not following, please do that. We just launched it 2 months ago. We already have over 50,000 impressions with like all of this content and all the work we're putting out, which is fantastic, over 1,000 reactions and 600 followers. This is really cool growth for just 2 months. So I think it's a testament to the project. It's a testament to the community around the project. And let's use these 2 days to celebrate. We're going to learn a lot about what's going on in the project, but let's celebrate with each other. This is a really cool community, and it's growing so much. And I appreciate it, and I think I speak for Sridhar here. We really appreciate all of you coming and being a part of it over the next 2 days. So with that, I'm going to pass things over to Sridhar to talk a little bit more about what's going on from the innovation perspective.
Cool. Thank you, Ali. Again, I'm Sridhar Anmandla. I'm the engineering manager on Velox, and I support Velox and the ecosystem around that. So first of all, super excited to have you guys here. And I need to keep up with Ali's energy, which is very hard, but I'll try my best. So with that, I want to give a quick overview of what has been happening around Velox and the community around it, and how the ecosystem has been evolving. So three themes come to my mind. One is about the hardware acceleration. I remember a couple of years ago when we were hosting our first VeloxCon, so we were talking about, hey, hardware acceleration. How do we need it? Do we not need it? In what shape and form can we accelerate analytics? So that was where we were. And 2 years down the lane, it's just amazing to see the kind of strides we have made in this space. So there are very exciting talks happening tomorrow from NVIDIA, Data Pelago, and there's a panel as well. So stay tuned for that. And the second theme I say is there's quite a bit of engagement happening from the big tech and hyperscalers as well. So a lot of announcements happened from like, for instance, IBM is hosting Prestissimo on their cloud. And then Google and Microsoft had made announcements about providing Spark native execution on their cloud as a cloud offering. So this is big deal. And this is just because of all the people over here. And the third theme is the core innovation that is happening within the engines itself. So Presto Spark being the like large-scale engines, it's becoming even more popular as well. There are other things that are happening around flings and things like that. So I just want to throw some light here in terms of Presto. So we have taken up a major challenge within the Meta ecosystem where we migrated more than 50% of the Presto warehouse workloads over to the Prestissimo, and we are seeing substantial performance and efficiency wins. And you're going to hear more about that like later today. And there's on the PySpark stuff. So we are unlocking a lot of potential for our AI ML customers as well through this innovation that is happening through PySpark Velox. And if you talk about Gluten, Gluten is just like widely known now. Like last year, there's so much of adoption that happened. There's so much of activity in terms of development that is going on within the ecosystem. And it's just the center of like everything that's going to happen for the next generation of data management. So with that, I want to jump a little bit into deeper about like what are the key highlights. There are way more highlights than what I can list here. I just wanted to highlight a few of them. So our friends, NVIDIA, they're going to give a talk tomorrow. Basically, they brought like GPU acceleration to Velox. So they've been working with Meta, IBM teams as well, just to integrate Velox with GPUs, and they'll be providing more details around that. So which is super cool. And Aeroflight connector, like our folks at IBM, like they have been working on native support for Aeroflight to stream data between external systems and Velox, and this is super cool. So we have envisioned these fundamental components, Velox being one such thing, and it's also great to see Aero, how we are evolving our ecosystem through these common foundations. And PyVelox, this is something super dear to me. Now we can run Velox without having any engine locally on your dev machine. You can iterate, prototype, run benchmarks. This is just amazing. So we started this like a couple of years ago. We paused on it, and now it is back to life. So there's a talk later today. Please stay tuned. It's going to be super exciting. Please give it a try. And the final one I want to call out is we made improvements to our join performance. We implemented this index lookup join operator. And the need for that is, we have these evolving AI needs, and like we are hitting the performance ceilings. So this is something which is very cool that happened. There's a lot of traction happening internally just with such an improvement, and there are more such going on. All right, let's talk about culture and collaboration and the philosophies how Velox operates. So Velox started as an open source project. I mean, we did a open source GA in 2022. And as the saying goes, right, if you want to go fast, go alone. If you want to go far, go together. Community matters. You all matter. Thank you so much for being here. And on that front, like we want to talk about like, we built it in the open, and all the design discussions and in the RFCs, everything happened in the open source. There are a bunch of companies and contributors who have been working closely hand in hand with us in order to kind of shape up the ecosystem of Velox. And high trust collaboration, as I was already mentioning about this one, right? So we have like really strong engineers from like several companies like Meta, IBM, NVIDIA. They have been working hand in hand, doing respectful code reviews, thoughtful design discussions, and constantly brainstorming on how can we evolve the next-gen data management. And finally, welcoming new contributors. So last year, we did a technical governance discussion, and we actually have a philosophy around that. And since then, right, we have a bunch of maintainers already supporting, several components within Velox. And we have been growing the community as well, grooming the next set of maintainers. But if you want to if you want to know more, like join our Slack channels, follow the GitHub discussions, and stay tuned. So finally, not so finally, but if you're excited to give it a try, please try out any of these things. You can run Velox locally using PyVelox. You can try Velox, Spark, or Presto as well, and get excited. If you want to contribute more, we are looking for help. There's a ton of help we need on documentation. We want to kind of upscale the reliability of the overall stack as well. And there are several open issues that you could help contribute as well, including function coverages and features and sub-connectors. So finally, join us on Slack and GitHub if you have not already done. Follow us on LinkedIn, and continue to attend these public forums. With that, thank you so much. Super excited to see you all here. And the next couple of days is going to be the time where we have to celebrate, have fun, and also realize how much we have accomplished together as a community. So with that, we are planning to host our next VeloxCon in China. Stay tuned on more details around that. We have a big community over there as well. With that, thank you so much. I'll hand it off to Ali.
Thank you. All right. So I forgot to mention, we are live streaming this right now. So for our community, maybe in China, it might be the wrong time zone, but India, maybe East Coast, maybe you just couldn't make it. Hello, first of all, thanks for joining on live stream. But we are going global with this thing for the first time ever, so that's super exciting. And I also forgot to mention, this morning when I checked registration numbers, we've doubled from last year. That's like really incredible. So kudos to the community, and again, exciting 2 days. Okay, so I have to do a few housekeeping items that Meta wants me to share. First is, if you are a non-Meta employee and you leave this area, please make sure you are with a Meta employee. They want you to stay with Meta employees if you're gonna wander around. We have lunch. You saw breakfast out there. We'll have lunch out there. Please stay for the happy hour tonight. We have a really cool area outside where we're going to be hosting it. It's going to be really fun. Great weather today. Again, chance to celebrate and connect with the community. So that's tonight. We hope you can stay. Tomorrow, same thing. We'll be kicking off at 9 o'clock. We'll have breakfast and lunch tomorrow as well, and we end a little bit earlier tomorrow. Okay, so I think with that, we're not that far off time. I'm going to introduce Pedro to come up next. All right, I'll do an official introduction. Pedro's talk will be Velox in the Age of Machine Learning. Pedro is the Velox lead. Yeah, you can take that out at Meta. So, Pedro, here you go.
All right, let me just see if the clicker is working. It is not. That's okay. All right, so good morning, everyone. Thanks for coming. I'm Pedro. I'm a software engineer here at Meta. I've been working in Velox for the last, I guess, almost 5 years. So yeah, super excited to see so many familiar faces here. Even more exciting to see new faces. Thank you guys for coming and taking the time. I'm going to be talking a little bit more about the investments we've been doing in kind of accelerating AI and machine learning workloads. Before that, I think just echoing Ali's and Sridhar's words, just thanks everyone for coming. We really appreciate you guys taking a couple of days out of your busy schedules. That was just amazing to see how fast the community has grown. So yeah, I really appreciate you guys taking the time. So getting back to business, I'm going to be focusing on just describing some of the work we've been doing at Meta and the community and kind of accelerating all types of AI and machine learning workloads from a Velox perspective, but also more broadly as a kind of research community and query processing in general. So Velox has been around for almost 5 years, so we can already talk about Velox in terms of Velox history, which is pretty cool. If I look back and look at kind of the different points in time and different things we did as a community, we can sort of group the things we've been working on in 3 different moments or 3 different phases. First one was just the early days when we were bootstrapping things. There was a lot of work on just getting the right memory layout, working on type systems. There was a lot of work on just expression evaluation, UDF execution. And we started using Velox. And the first system we integrated inside Meta was a stream processing system called Xstream. And that was a lot more about, like I mentioned, expression evaluation, UDFs, and things like that, right? So we had to build the foundations to kind of build more complicated types of processing, right? So the first couple of years from 2020 to 2022 was a lot of work on just that, getting the kind of the foundations, the data representation part really consistent and really strong. There was a lot of work on just aligning Velox's memory layout with Arrow's layout, making sure that they're compatible and things like that. Moving on a couple of years, what we've been working on is just supporting large-scale SQL workloads. There's a lot of work on just supporting relational operators, things like joins, hash joins, merge joins, very efficient table scans, merge sorts, and all sorts of things you need to implement large-scale relational engines. So from 2022 to 2024, there was a lot of work on integrating Velox inside Presto, which is a Prestissimo project we've been talking about. On the Prestissimo side, inside Meta, we got to a point where today we're already running about 70% of all Presto batch workloads already running Prestissimo, right? So it's not a prototype anymore. It's not a test system. It's actually a pretty battle-tested system already. We're planning to migrate all the workload to Prestissimo by the end of the year. Later on today, we have a talk by Amit, who might be here or maybe not yet, but he's going to tell you all about the Prestissimo journey, how we've been going about replacing all the Java engine by Velox. We've been working pretty closely with the IBM team. Prestissimo is also available on IBM at the Watson X data cloud, so we made a lot of good progress there. Outside of Prestissimo, we've also been working with the Gluten community. I guess last year, Microsoft also announced that Velox running through Gluten is also available on Microsoft's Azure cloud. Google later on announced that Velox can also be used on the Google cloud. So on both Presto side and Spark side, we've been making a lot of progress on not just running benchmarks, running TPCH, TPCDS, and things like that, but actually having something that can be used by production, by real customers, and by real workloads. So we made really good progress. Sort of fast forwarding to today, we're now living in a world where AI and machine learning became the largest customers. So we always say that data's largest customer today is AI and machine learning application. And that means that if you look at most of the large-scale lake houses, most data and most tables nowadays are training tables. Also, most compute or just most of the computation goes into cooking training tables and feeding training tables to training frameworks like PyTorch. So the lake house has become an AI and machine learning lake house. Not just those are the main or the biggest workloads today, but they're also growing the fastest, right? So if we need to optimize for something, if we need to focus on one customer, one type of workload, that's where we need to focus on. So that's why we're making this entire conference. The idea was making VeloxCon about how do we accelerate AI and machine learning, just because this is data's main customer nowadays. So then we got to sort of a third moment in Velox history, and in a world where we need to accelerate AI and machine learning, the questions are, of course, how can we get Velox and how can we use Velox to better accelerate or to better support this type of workloads? But not just that, but also how can we extend Velox and what are the new tricks we need to add to query processing to be able to process those things more efficiently, right? So this is a lot of the work we've been doing in the last, I guess, a year. And that's what I want to focus and summarize on this talk. So basically just leaving this message of if we need to optimize for something, if we need to accelerate something, accelerating AI and machine learning are probably the most impactful thing we can do as a data community, just because of where the industry is today. So before I describe some of the work we've been doing, just as a quick background on how sort of the machine learning data workflow works. This is a little more centric in machine learning applications for recommendations and ranking systems. But those things are also, there's also a good degree of similarity with other applications of machine learning like Gen AI and content understanding. But the workflow is a little more about supervised learning for recommendation systems, right? But essentially, when you have those, this type of machine learning applications, you have those programs called models. And models make predictions, and we serve those predictions to users. Whenever you make a prediction, you need to specify parameters, which people call features, right? So you pass the user features, we make predictions, we serve those predictions to users. Whenever we make a prediction, we log the fact that we made a prediction along with all the features used in this process. We ingest all this data in the lakehouse. We do some data preparation. We generate new training data, and we feed this training data to train new models, right? And then whenever you train a new model, you validate this model, you make sure that it behaves the way it's supposed to behave. You go ahead, deploy to production, start serving traffic, and then you start capturing more training data, right? So you have the cycle where you have models, you keep capturing this data, training new models, and the more data you have, the more data you can feed to trainers, usually the better the recommendations you can serve to customers. In this process, there are two main workloads that you use in this entire workflow. The first one is whenever this data lands on the warehouse, there's this process of kind of cooking, preparing those training data sets. There's usually a degree of taking experimental features, adding to the training data set, running many iterations, trying different models, throwing them away, trying them again. So there's this part of once the data land in the warehouse, curating and creating the actual training data set. So this is what we usually call training data preparation. Another big workload is what we call training data loading, which is essentially this idea of once you have the training tables on the warehouse, you need to read this data and you need to feed them very efficiently to trainers. So those are kind of sort of the two main workloads in this data workflow. And those two are highlighted here. Just this part of how do we efficiently transform and prepare training tables, and how do we efficiently feed those training tables into PyTorch or other training frameworks. So the first one is training data loading. Like I mentioned, the idea is just getting the data out of the warehouse and feeding them to GPUs. Because GPUs nowadays are the most precious resource you have, you want to make sure that you're not starving GPUs, right? So the system you have to feed this data needs to be very optimized for latency, right? You don't want to keep the CPUs waiting while you're joining, while you're doing pipeline breaks and things like that. If you look at the type of transformations we do in those systems, they're actually very close to other traditional SQL engines, except that, like I just mentioned, we try to not cause pipeline barriers as much as you can, so you don't keep GPUs waiting. Right? So those are mostly streaming operations. But outside of that, the transformations are very similar. It's all very latency sensitive. It's all order sensitive because depending on the order you feed those things to models, the model you train might end up being different. There's a lot of very interesting challenges here. Masha, who's patiently waiting for the next presentation, is going to talk to you all about training data loading. We're going to focus a little bit more on the second workload, which is training data preparation, which is exactly as it sounds. Right? When you land this data in the warehouse, what are the kind of preparation, the curation you need to apply to this data before the final training data is ready? In this type of workloads, there's actually nothing new. Whatever you do is just traditional relational transformations. You do joins, you do merge joins, you do expression evaluation, you transform this data. But there's nothing really anything very different from that. Most of this workload already runs in large-scale SQL processing engines. Inside Meta, we run a lot of that in Spark. Some of them we run in Presto, but just kind of traditional large-scale systems that can process relational operations. However, one of the things we identified throughout the years is that although those things are very well understood by the query processing community, we see that in a lot of cases, machine learning users, they just cannot use or they don't use the engines we provide for a lot of reasons. So what people end up doing is sort of extending, or we even say abusing the engine in all sorts of ways through UDFs, through transforms, or through all sorts of custom code execution to sort of bypass inefficiencies on those engines. And then we got to a point where a lot of the workload we run inside those engines is not the engine itself processing thing, it's running custom code. And you can imagine that this may cause all sorts of problems, like it's hard to know what's happening. Sometimes it's even hard to understand where data is coming from. Its reliability is harder. It's hard to even figure out who maintains those things. So this is not a good place to be, right? So this is, in a way, it just means that the engine we develop is not, it's not very optimized or is not very useful for our biggest customers. So a lot of the things we've been doing throughout the last year is essentially trying to understand why do people have to compile their own binaries and run inside the engine to do things that the engine should do in the first place, like filtering joins and all sorts of things. So there was a lot of work on just kind of trying to identify exactly what they do and how we can provide a better engine for people so that they can use the engine in the way it was intended to be used. So I have a couple of slides here. Okay, we've spent some time identifying what are some of the things we found and what are some of the things we are extending in the engine. A lot of this work is already done. A lot of this work is things we're planning to do in the future, but I'll make it clear where we are in each one of them. First thing we found on those tables is that they have a tendency of being very wide, meaning that you have a lot more columns and column streams than traditional or kind of typical analytic tables you have on Warehouse. One of the reasons for that is that whenever you want to train based on those tables, if all the features, if all the columns you need, they're all denormalized, you can just read that table, you can just scan that table, and you can very efficiently fit this table to the two GPUs. Right? While if data is normalized, you might need to join things, and the training data loading process might become a little more expensive and more complicated. Although normalization is, of course, a discussion for some of the workloads, by and large, most of the data sets are heavily denormalized. So not just denormalized, but they usually have a whole lot of columns. So you can imagine that all the features you need to use in the training process, they need to be part of the table. And the more features, the more kind of different characteristics, the more data and more context you can feed your trainers, the best. And in a lot of cases, people don't know what are the features that are most impactful. So it's very common that people just keep adding more and more features to those tables to a point where it's very common to find tables with tens of thousands to hundreds of thousands of different features on those tables. Right? So it's a lot wider than they used to be. If you look at traditional analytic tables, you might have dozens of columns, maybe hundreds of columns in the worst case, but you never had hundreds of thousands of columns. Right? So this kind of breaks the engines that process the data in all sorts of ways. The other part is that the features we use on those training data sets, they're usually very dynamic. So it's very common that people add new features, they remove. So adding columns, removing columns, executing DDL statements in all sorts of, and a bunch of tables that might make part of the entire training pipeline, it's not practical. So what people end up doing is that they model those features as maps. Right? So I have an example here, but it's very common that you have your table, you have some attributes, and the features themselves, they're modeled as a map, and the map is essentially maps some sort of feature ID to the value of your features. Even worse, in many cases, the feature values, they're not just primitive values like integers or floats. In many cases, they are lists or they're maps or they're sequences of other values. It's very common that features might be things that a user has done in the past, like what are the list of the last hundreds of or thousands of things the user clicked on the past. So the values of those features can be sequences, and we have found that the longer those sequences, actually the more context you feed to the trainer, the better the model quality, right? So those things are already large and they have a tendency of getting even larger. And this got to a point where in a lot of training tables, some of the rows, they might be larger than a megabyte. So you can see that the shape of training tables is very different than what they used to be, right? So that's one of the things that kind of breaks all the engine in all sorts of ways. What I mean breaks is not that it doesn't work, it just works in a very, very inefficient way. Now the question is, what can we do about it? What are the things we can do or extend to the data stack to better support this workload? So when you're processing data, you can imagine that this is sort of what happens, right? Usually, when you have data pipelines, you have an input table, you read this input table, you map this to some in-memory representation, you apply some processing to this data, you write it back to the other side to an output table. Of course, in some cases, you might have multiple stages, but this is a simple case where you have sort of a map-only query, right? So you have a table, an input table on the left side, you write that back to a table on the right side. So the first thing we did was to evolve the storage layout. One of the things we did was adding this new encoding called flat maps, where the idea is that usually when you store maps in columnar files, you take all the keys and all the values for one particular row and you store them contiguously on disk. And the idea there is if you want to materialize the entire map from one row, you can do that very efficiently. The problem there is that in many cases, for those tables, you store thousands to tens of thousands of features. And when you're training, you usually don't want to read the entire map. You usually train based on a subset of those features. Right? So if you need to read a few features from this map, there's no efficient way to do that with a regular map. So we created this new abstraction, this new encoding type for maps called flat maps a few years ago. This, in a way, it's a way to store those maps in a more sort of vertical manner, such that here there's an example. If you just need to read the feature 1, you can just go ahead and just read the sort of the pink region of your file, right? So if you want to, we call the thing feature projections. If you want to project a few specific features, which means you just want to read some keys from your map, you can do those things a lot more efficient, right? So this thing is something we created a few years ago. This is something we use very broadly. The trade-off there is that you're usually trading some storage efficiency for reader efficiency, right? So on the read path, you can be a lot more efficient, but on the other hand, the streams you store, they're a little smaller, so they might not compress as well. Second thing we did is we added support for what we call cascading encodings. So the idea here is that you can have, whenever you have a stream of data on disk, the streams are able to describe themselves. So you can have one stream inside another stream inside another stream, and you can sort of recursively or hierarchically apply different encodings to the data. And this is important for those tables because in many cases, because this data is denormalized, you have repetitions between the features across different rows. So if you have support cascading encodings, you can have streams that represent maps or represent arrays, and you can actually deduplicate them by putting them inside an RLE or a dictionary stream, right? So cascading encodings make storage efficiency for those tables a lot better. So we wrapped all those things. We ended up creating this new file format that we initially called Alpha and that we recently open sourced as Nimble. See a few people here from the DI storage team who actually support us. If you have questions, I'm happy to make the introductions. We also open sourced Nimble, I think about a year ago. So it's an open source project. It's sort of a replacement for Parquet and ORC. And it's a lot more efficient, especially for training tables that have those characteristics. We use this very broadly already inside Meta for training tables. So this is how we evolved, how we store data, the sort of the storage layout of the data. We also did a lot of things to evolve how we process this data. And this is a lot of more kind of strictly speaking the work in Velox. First thing is, of course, vectorization. Velox from scratch, we implemented all the relational operators using vectorization, which is this idea of as you take larger relational operators, like how much you can break this into very concise and very small loops, and very little loops, so that you can execute those things more efficiently. And then CPUs can execute loops that are very tight a lot more efficiently because you have less pipeline bubbles and things like that. So every single operator in Velox is implemented in a very particular way to make sure that CPUs can efficiently process those things. This is sort of a given nowadays. But the second main thing was implementing what we call compressed execution, which is this idea that often when you're processing data, you can leverage columnar encodings of the data to process data even more efficiently. And you can also generate data that's encoded. So some examples here is if you're filtering a data set, you might not need to copy the data to the output. You can just wrap the data using a dictionary or something that just tells you the records that pass the filter. You can do similar things even with joins. If you need to increase or decrease the cardinality, you can do that by just wrapping the data using dictionaries. And of course, the point here is that the fewer times you need to copy this data, because this data is so wide, the more efficient those things become. Right, so we do that very often for expression evaluation, executing expression over dictionary alphabet. So there's all sorts of different places in Velox where we use this trick of, instead of just kind of copying data sets back and forth, to just play with dictionary encodings. And again, this is a lot more efficient for ML workloads because copying each one of those records in some cases means that you're copying an array with 10,000 elements, right? So those things can really add up. So we implemented all those things. Things became a lot more efficient. Like I mentioned, we've been pushing this to Prestissimo. Although this is sort of what we saw if you profile Prestissimo today. And this is not even just machine learning workloads. This is profiling things across the board on every single workload we have on Presto. Right? And this is a breakdown of where CPU goes, broken down by operator. So the interesting thing here is that if you look at where most of the CPU is going, is actually just going into table scan and table write. So if you just copy, or if you just look at how much time we spend into table scans and table writes, this is more than 50% of the CPU time, which is sort of surprising, right? You're just, in a way, reading data, mapping this to some in-memory layout. You would expect that the time actually goes in processing those things. Right? But we spend a lot of time in just reading and writing these tables back. If you look only at the machine learning workloads that process training tables, this number goes up to 90, even maybe even 95%. Right? So kind of virtually all the time, or at least the vast majority of time, goes into scanning and writing table. Part of that is because as we vectorize operators, some of the other operators became so much more efficient that they're smaller slice of this pie. But then there was a question of why are those things so expensive? So then we optimize the storage layout on the edges, we optimize how we process data, but then the way of kind of mapping the storage layout into in-memory and then doing the opposite on the writer side, it actually became the main bottleneck. So one of the things we've started observing is that this impedance mismatch between storage layout and in-memory layout has become a bigger bottleneck. It's something that's always been there, it's something that is by design. I think the point is just that as we optimize other parts of the stack and as you start kind of passing a lot more data through this pipeline, this became a more evident bottleneck. Right? So there's a lot of discussions on how can we optimize this part. So just kind of describing this problem a little more, usually the point is that when you're storing data on disk, you use a much wider set of encodings, right? Because usually optimizing for storage space. So usually you want to encode this thing using the most efficient way to encode from a storage perspective. So you can use things like bit packing dictionaries, delta, and all sorts of things. While when you map this storage layout into memory, usually the execution engine doesn't understand all those different types of encodings because the encodings you support on the execution engine are usually the ones that can make execution faster, right? So mapping from this kind of wider set of encodings into a much narrower type of encodings that the execution engine can understand, like that actually adds quite a bit of overhead. So other than evolving the execution independently, the storage layout, we also look into ways of kind of evolving the interplay between those two layouts. There's a couple of things we did here. One is what we call encoding preservation, which is this idea that if you're reading data that, for example, is dictionary encoded, you might just preserve this data as dictionary encoded and deliver this to Velox because Velox can understand those things. Also the opposite on the writer. So let's say that you executed a join. The join actually generated data that's dictionary encoded. In a lot of cases, you might just leverage this encoding as you write this data back. Right? So kind of as much as you can, try to preserve encoders, okay? Try to reuse the encodings between storage and in memory. This is something that makes this problem a little less expressive. Another thing we do very often in Velox is this idea of lazy materialization, which is whenever you read a table, you don't actually read it, you just pretend you read, and you only materialize the data once you actually need the data. And then the idea of doing that is that in many cases, if you delay, right, if you read this lazily, chances are that most of this data will be filtered out, or maybe even all this data will be filtered out, and you don't need to materialize things, right? So of course, if you delay this materialization, you need to decode fewer data. You don't need to decode as much data, and those things become more efficient. Another very interesting thing we observed recently is that, especially when you're processing those machine learning workloads, a lot of data is what we call pass-through. And pass-through is this idea that this is data that doesn't actually participate in query execution. It's just data that we read from one side, we kind of carry through the operator chain, and we write on the other side. So of course, if you're doing things like joins, you need the values of the join keys, but all the other columns you're projecting, you don't necessarily need their values, right? You just need to know what's the cardinality change to those values. So there's a lot of data we saw, and actually most of the data we saw in those pipelines, they're just pass-through data, which is data that you just read, you decode that, you kind of copy that multiple times through the operator chain just to re-encode this later. So of course the question is, this is of course sort of a work that we don't necessarily need. Can we create a different execution model that prevents some of that? So the idea here is that if we had a model that instead of having to carry all this pass-through data through the execution, we could just move them from storage, from one storage layout directly to the output storage layout, things could be a whole lot more efficient. And turns out that you can. This is still a prototype we've been investigating. We call this the wormhole execution model, but the idea is essentially that, right? If you're executing a query, you actually only need the control columns so that you know what is the cardinality changes you need to apply to the pass-through data. But then potentially you can have a process that reads data from one storage layout and maps this straight to an output layout. And then all this, or a lot of this overhead we've been discussing about mapping things from a storage layout to an in-memory layout, you can bypass. So we ended up writing this paper. We submitted to one of the database conferences. Hopefully, I'll be able to share this soon if this goes through. In this paper, we have a lot more details of what this process looks like, how we do this mapping, how generalizable is this framework, what type of relation operators you can apply, and what types of operations you can't. putting it all together, we build most of those techniques. We build them as part of this PySpark Velox project that Konstantinos is going to tell you all about a little later today. We saw that specifically for machine learning workloads running in the system, we saw something like a 75 speed up over vanilla Spark, which is just a crazy number. It's almost 2 orders of magnitude. On top of that, for some machine learning workloads, we don't need to necessarily rewrite the entire table. We're only adding features, or we're only adding columns. So we also had some work on integrating those things with table layouts so that you don't need to move as much data. Inside Meta, we don't use Iceberg, Delta, Hudi, or any of the open source table formats, but we have our own file table format called Metalake, and Darren's going to give a talk about a little later today about this, focusing on how a table format can allow you to be more efficient while processing machine learning workloads, specifically on when you're injecting features, which is something that people do very often. On top of that, the prototype we put together gives you another 2 to 3x speed up. Like even after you accelerate all those things, then the encoding and decoding CPU overhead becomes even more prominent. So the idea here is that if you put all those things together, you get more than 3 orders of magnitude over vanilla Spark, which is sort of something that is used very widely in the industry, right? So there's a lot of opportunities here if you really look at what the machine learning pipelines are doing and dissect and try to come up with something more efficient. There is a lot of opportunity there. So just wrapping up, we're seeing that with all those query processing techniques, Velox is disrupting how we can, or how efficiently we can prepare those large-scale training data sets. We're seeing like literally orders of magnitude speed up over sort of off-the-shelf engines that are available today in the industry. One thing we learned is that only optimizing the storage layout or only optimizing execution individually just takes you so far, right? So you really need to look at this thing end to end and look at the interplay between storage and in-memory layout, which is something that hasn't got as much attention as it should have got. And lastly, like I mentioned before, I think as a data management community, as AI and machine learning become the largest customer, this is where we need to focus our attention. We're doing a lot of work internally based on the use case we have internally, but we want to collaborate. So, if anyone is interested, if people want to discuss how we're processing any of that, I think this is a challenge we need to tackle as a community. There's a lot of work to be done. Of course, we make some progress, but there's a lot of new things that are coming down through the pipe. As we like to say at Meta, this journey is just 1% done, so there's still a lot of work in front of us, and that's everything I had. Thank you.
Yep. Thank you, Pedro.
Do you want to use my laptop?
Do you have slides? Oh, you have her slides? Okay. You can turn it off, yeah. All right, thank you, Pedro. So I'm really pleased to introduce Masha. Masha is a co-creator of Velox, and we're so happy that she's here in person today to talk more about data loading for AI training. So please welcome Masha.
Thank you so much, and thank you everybody for coming. It's so exciting to see you all here. I know it's busy for everybody, and so coming out for like a whole day of talks and maybe even 2 days or a day and a half is a big time commitment. Just want to say thank you. Thank you for coming. I'm going to learn how to use this clicker. Okay. So in the past 9 months or so, I sort of took a little bit of a detour from the work I've been doing with Presto and Gluten projects to help accelerate analytics engine, and went to learn about how AI data loading works. As Pedro was explaining, AI training became the biggest consumer of the data in the warehouses, and so understanding how that data is being read, transformed, and feed into training became interesting and important. And one of the questions I was looking to answer is, what's so different about preparing data for training? How is it different from the work we're doing in Presto, in Spark, to prepare dashboards, to prepare reports, to answer questions about the data, finding insights and about the data. Is it the same? And if so, why we need separate systems to do this data loading for AI? And so hopefully today I'll share some of the learnings, some of the findings. In summary, it turns out that data loading for AI is very similar to what we do in Spark, what we do in Presto, but it has its unique differences. You need the nuances which matter and that require new capabilities, new features, new optimizations. In Meta, we use primarily two systems for analytics, which is Presto, today it's largely Prestissima, and Spark. And today it's moving into Gluten, into PySpark, into more optimized versions. And for AI, we're using a third system, and we call it DPP. If you look at it, it looks very similar to both Presto and Spark. It essentially runs a two-stage query. First stage, essentially table scan, kind of reading from storage, doing basic transformations, think about filter, project operators. It runs on a tier of CPU machines. And then those machines prepare data and put them into output buffers, from which it's being fed into another tier, the second tier, which runs on GPU machines, which reads data from CPU tier and feeds into training processes. One way to think about it could be like we're running an aggregation, where aggregation operator is essentially an AI training. It keeps consuming data, you feed data into, it accumulates the data, and at the end gives you a model. In a way similar how in aggregation in a traditional engine works. It keeps accumulating data, keeps summarizing, it keeps accumulating, and at the end gives you, say, a number of distinct values in your input. The shuffle, the data exchange between those two tiers is a bit different. In Presto or Spark, usually we do like a hash-based shuffle, where we move the records that hash the same way to the same machines. But here, there is no affinity between the data coming out of CPU machines and going into the GPU, so we call it like arbitrary exchange. Essentially, any trainer can pull data from any CPU node, and it's first come, first serve. So you prepare the data, it can go into any training machine, and as long as the training machine is ready to get more data, it will pull that data. The nuances about that, like for example, this arbitrary exchange, it actually exists in Presto, and it's used when we are implementing table writer. In certain cases, it doesn't matter which nodes would write the files. And so there is an arbitrary exchange in Presto. So we can say that this is kind of similar. But the differences come when we realize that trainer processes specifically care about the size of the batches. They really like homogeneous batches, say batches of 1,024 rows or batches of 512 rows. There is a certain batch size that they advertise, and they really like batches of the same size. That's essentially because they run on GPUs, and if you give the same size batches which are processed the same way, that processing happens faster. And therefore, the data produced by CPU machines needs to come in batches of specific size. And that's a functionality that doesn't exist either in Presto or in Spark. It's called a rebatcher process, where we take batches which are coming out of table scan or filter operation or project operation, and we stitch them together into batches of a fixed number of rows. Another important property that AI requires is that the order of the data produced by the CPU tier matters. In Presto or Spark, it only matters the total set of rows that's being produced, and very rarely we have like an order by operator at the end, usually for very small data sets. Definitely not when we're processing billions of rows. We would not put an order by on that. But in training, different models have different requirements, and often they want data either random, which is also like a property of the data. You can't just read it anyway and pretend it's random. You actually need to shuffle the data. Or sometimes they want data in actually chronological order, like older data comes before newer data. And if you think about the amount of data being fed into training, sorting it, just how we do it with a traditional order by operator, is not practical, simply cannot possibly work. And so the sorting implementation in AI training is implemented by sorting splits. Essentially, you think about your data is usually organized into partitions. Those partitions could be daily partitions, hourly partitions. They could have a few more partition keys, but they have this temporal component to it. And so you can sort the splits. You can sort the splits by day partition and hourly partition, and then sort the files or chunks of data within those partitions randomly, and that gives you the ordered or like nearly ordered data, which is essentially good enough for training. One other aspect with data reading for AI is that imperfect data or not 100% correct or not 100% exactly ordered is usually okay. And that's not the case with any sort of analytic engine where correctness of the execution is the top most important feature. We never say that Presto query can return almost correct results or return almost all the rows except few rows got lost, or maybe like they got a little bit corrupted. This is just never okay, never works, but for AI that works. And so we'll see further on, like here we're talking about that how sortedness can be close enough or good enough, which allows us to implement it practically and efficiently. But we'll see how also like dropping some rows to provide fault tolerance is also okay. One thing that trainers do not tolerate, and that becomes important focus for building the engine for training, is duplicate data is death. You can lose a row, you can lose maybe some small percentage of rows, not deliver them, but it's really disastrous if you start feeding the same data again and again to the trainer. Even a little bit of data duplication is a major challenge, and models simply can't tolerate that. And so one thing that we'll start seeing is that for many of the features that are required by training, there is no SQL way to describe the property. Like there is no way to describe this kind of order that's not strict order by, or there is no way to efficiently describe that I want it kind of sorted chronologically and then within big chunks, say hours or days, I want data shuffled. And so one of the things we as a community need to think about is how we evolve not only the engine and the implementation, but how we evolve the language which we can use to specify the data reading. One other requirement that training has to do about union. In training, like Pedro was mentioning, we cannot starve GPUs. And therefore, most operations, if essentially all operations, have to be somewhat streaming, We cannot, like, for example, use a hash join because it takes some time to build the hash table. And while you're building it, you cannot produce results, which means GPUs are sitting, waiting, idling. And so the algorithms are usually streaming aggregation, merge join, and like for union, it means there is no union, there is only union all. Because if you need to dedupe something, that becomes a bottleneck. It becomes too slow, too hard to implement with so much data. So, but union all is a common construct in training for AI, where you have training data from multiple places and you want to combine them. And now, union all semantics in SQL just says, okay, make sure that in my final data set, we have rows from all the branches of the union. But that's not good enough for training. Usually training wants each batch coming out of the data processing pipeline to have a mix of data from all the union branches. So it's almost, you can think of like if you're, there is like online training and offline training. If you're doing online training and the data is coming from 3 different places, you naturally get like a mix of data and you train on that mix of data. So when you're training offline on like data stored in Hive, you want to emulate that kind of data shape. You don't want having one batch of data coming from one source and having one characteristic to it and having your model learn the pattern in that data and then abruptly switch to another source of data from another union branch, which has different characteristics, different patterns, and now your model keeps going back and forth, and that creates not very good results. So what you want just this kind of nice mix of data from all sources with all patterns present pretty much in every batch, or at least nearly every batch. And not only you want a mix, but you want the ratio of data from different sources to roughly match relative sizes of those sources. So if you're like combining data from 3 sources which are of substantially different sizes, you want the mix in each batch to reflect the size ratio of those sources. And just like the previous examples, here we don't even have a language to express that using SQL or any known SQL extension. And that's like a challenge for us as a community to figure out how to start evolving SQL to be able to express those kind of data properties in a convenient way. So here I just kind of have an example of that kind of union. And in addition to the mix of data coming from those branches, the order in which the data comes from is also a little bit interesting. It could be that you have multiple data sources and then you say, I want a mix of data in every branch, and then I want my data coming roughly ordered, older first, newer next, and kind of like at the granularity of, say, like daily partitions or hourly partitions. And so I want like Monday, then followed by Tuesday data, followed by Wednesday data. And that's all fine. We can do all that. But then sometimes what you have is you have 2 sources or you have multiple sources. And logically, Monday's data for one source corresponds to Wednesday data from another source. So you can have like some data that like logs activity that happened on Monday, and then you wait for some events to happen a few days later, and then you want to combine an action that happened on Monday with an event that happened on Wednesday and train your model on that kind of data. And so in this case, you have like a somewhat like a logical partitions, which say that Monday's data in source 1 corresponds to Wednesday data in source 2. And the way you can express it is by having a transformation on top of partition key, like a DS partition key. In one source, we use a UDF called DS shift. Essentially, DS shift means add so many days to the date. So DS shift, DS6 means if DS is Monday, then DS should add 6 days to it and arrive on Sunday, I think. Sometimes it's hard to get those off by one things right. And so that presents like a new challenges to split generation and kind of figuring out what are the actual partitions, logical partitions for that query, and how they map to actual physical partitions. And again, that's an example of what's important for AI training and what simply doesn't exist in traditional analytics world. Here I'm just giving more examples about like how this DS shift operation allows us to implement the logical partitions. The key is that being able to solve the equation DS shift DS6 equals some constant value, because you need to be able to go from a logical partition to an underlying physical partition, and that means solving those kind of equations. And you can do that as long as you're using invertible UDFs, functions that for a given function, you have another function that if applied twice, you get an identity. And DS shift is, of course, that, like DS plus 6, you can take a result and minus 6 to get the original value. Which essentially means that the optimizer, like the language, needs to evolve to allow us express those properties, and then the optimizer needs to become more powerful as all of a sudden now it needs to be able to solve those equations that involve invertible functions, specifically for being able to push down filters all the way to table scan and translate them to metadata queries rather than filter operations during runtime. And so we're seeing how the language needs to evolve, how the optimizer needs to support the new language, and of course execution needs to support both the optimizer new plans and new language. Just to summarize, the GPU starvation is the most important concern in AI training. When we talk about efficiency, primarily we're talking about how many CPU machines we need to keep one GPU not starved. Like the fewer CPU machines we need, the more efficient we are, which effectively means that we're not looking for, say, CPU savings. We're not looking at like CPU utilization and trying to squeeze a 5% here, 5% there. We're not looking at like memory usage. We are looking holistically at literally like number of machines you need to support one GPU. And the fewer machines, the better. At the same time, if the optimization doesn't allow to reduce the number of machines, maybe you optimize and now all the machines use less CPU, but the throughput, the number of batches they produce per minute hasn't changed much, then it's as if that optimization didn't happen. And streaming algorithms are essentially the only ones that are practical. And that's why we'll be seeing more focus on those like streaming aggregation. And recently, Jamie from Velox team has been improving the efficiency of that particular operation. And that was really helpful, like 3x improvement in batches, in total throughput, not just CPU time. Merge join, just by nature, is a streaming algorithm, so that's used quite widely. And the newly added index lookup join becomes relevant and important for AI training. Another kind of aspect with training jobs is that they take a long time. Like a long time meaning sometimes they take days, some of them take weeks. which means fault tolerance and being able to fail and not forget all the work that's been done, but rather pick up from where you left, or maybe a little bit behind, redo a little bit of work, but not all the work, is becoming critical. And so tolerating failures of individual CPU nodes without failing the whole job, and also tolerating just like fatal crashes or fatal conditions and still be able to resume from some reasonable state where most of the work is preserved becomes critical. And fault tolerance is just plain hard, especially in distributed systems. You need to apply some sort of trade-offs. For AI, what helps is that losing some data is okay. Duplicating data is not. And therefore, the system that's feeding trainers is being designed to deliver at most once semantics. It essentially guarantees that a row will never be duplicated, will never appear twice, but it also says there can be some data loss, especially in the face of failures. And so it's important to have that semantic, and in addition to have some sort of control on, like some sort of tracking of how much data is being lost or potentially being lost, so that at some point you do need to fail the job. Like if you're losing more than certain amount of tolerable percentage of rows, it's actually better to fail and say something is catastrophically wrong rather than spending more time, more days training and then just getting a wrong model that succeeds in training but then fails, then is deployed in production. And so the system we use, the DPP system, has some logic where it allows for checkpointing progress. And it allows to pause a job and then resume it from that checkpoint. And that not only kind of supports fault tolerance, but it also supports this use case where scarce GPU resources, if they are used, for example, right now to train a medium importance job, and a higher importance job is waiting access to those GPUs, we can pause the job that's running now, let the high priority job go, and then it finishes and GPU resources become available again. The job that was paused can resume, it will continue running without losing the work that it's done. And so that's currently being implemented as with certain assumptions in mind that allow for somewhat clever and relatively simple technique that doesn't require a lot of development, doesn't require a lot of kind of complication that's traditionally involved in implementing checkpointing to be viable. One assumption is that the query plan or the data frame that's being used in real life is deterministic. And like many things AI, it doesn't need to be 100% deterministic. It needs to be deterministic enough. And here, what it means is that individual values in individual rows can be slightly different when ran again, but the set of rows needs to be the same. Like the number of rows produced needs to be the same. The order in which they are coming out of like individual threads of execution need to be the same. And so here I have like an example where we have a table scan followed by filter and followed by project. And the project uses rand, which of course makes it non-deterministic. But that's okay, because project doesn't change the cardinality, doesn't change the order of the rows. And for the purposes of checkpointing, that's fine. However, if the rand is used in a filter, that presents a problem. If filter is non-deterministic and then you rerun again, you ran a risk of having duplicate data because the rows are just not comparable to each other. And so the way checkpointing works in AI is that we are processing the query one split at a time. And for every split, each split is running single-threaded. And single-threaded and somewhat deterministic, so it produces a stream of output rows. And we can number those rows. As they're coming out, they are saying, okay, row 0, 1, 2, 3, 4. We create batches from those rows, and for each batch, we annotate it with metadata. We know that this batch was produced by a certain split, and we know that this batch contains a range of output rows from the output split, from the output stream corresponding to that split. Which means if we need to produce it again, all we need to do is take the same split, run it through the same query, and wait for the row number at the start of the range to get the batch. This very simple technique that essentially allows us to annotate output batches and track which batches were fed to trainers, to GPU processes, and on restart, rerun the splits which didn't have all their batches processed by trainers, and then splits which were not processed at all, works remarkably well. It does have those assumptions. It takes a little bit of time to understand how this tracking of output rows works, because it's not tracking the input rows, which is something that's pretty straightforward to think about. Like you would think about, okay, I need to track which rows I've read from storage. And that doesn't work because all the filters, the joins, and other conditions. But tracking output rows surprisingly works. And again, that kind of checkpointing logic today exists only in DPP, only in the AI training data loading system. It doesn't exist in Presto, it doesn't exist in Spark. We do not have native support for that in Velox. But that's something we need to look into and figure out how to add. So similar mechanism that's used for checkpointing is used for also fault tolerance. Then a machine, one of the CPU machine goes down, the coordinator or the master node remembers which splits were assigned to that machine. It also knows which batches from those splits were delivered to trainers. And so it can make the splits which were not fully processed, not fully delivered to the trainers, available to other CPU nodes for pickup and reprocessing. So fault tolerance, so we talked about data ordering, we talked about mixing data in batches, and we talked about the fault tolerance. Another big aspect of reading data for AI is handling enormous sizes of the maps that are storing features. As Pedro was explaining, there are like thousands, sometimes dozens of thousands of features stored in a single column, in a single map column. And many of those are experimental. Some of them are used for one model training, some are used for another, some are not used at all because the experiment didn't pan out, and cleaning that up was not a priority. And so in general, what we are seeing that in individual data reading for a specific model training job reads about 10% of keys from any given map. And when we're talking about those huge maps, reading only a tenth of it versus reading the whole map is a big difference. And it's a big difference not only because it takes CPU time, it takes network bandwidth to transfer that data, to kind of copy, to decode it, but one also important aspect is it takes a lot of memory to simply store it on the CPU machine. So if you're storing 10x more data than needed for processing, essentially it means 10x memory is being not used. And interestingly enough, while Presto and Spark tend to be CPU bound, and that's why we mostly primarily talk about CPU usage. We saw a slide that Pedro had about the distribution of CPU time across different operators. It's very relevant in the world of analytics. What's relevant in the world of AI is how much memory we need to run a single thread processing for a query. It turns out that data reading for AI is memory bound, and CPU is plentiful. There is usually about 30-ish% CPU utilization on the CPU machines, but they are booked in terms of their memory usage. There is CPU to create more threads and go faster, but there is no memory to do that. And so figuring out why there is no more memory, why we're so CPU memory bound, becomes critical to understanding how to make AI training go faster or use machines more effectively. The figuring out how to not store large maps in memory when only 10% of them is needed makes a big difference for memory usage. And so if we solve that problem, if we don't read the whole map, but only read the keys that we need and do that in memory efficient way, for example, without having to decompress and decode the map, which still takes memory, allows us to not change anything about the CPU efficiency of the process. It simply allows us to add more threads and go faster. And that's why like the feature projection or like which refers to reading only certain keys of a map is very important. I have this kind of snippet from just one kind of node from a query plan from one of the queries that's used in AI training. And the reason I have it here is simply to kind of illustrate the sheer scale and the difference between query plans in analytics and query plans in AI. Like we all probably know in production, queries are huge. Query plans are huge, sometimes hard to read, a lot of things in them. But we still have all the systems provide explain command, which gives you a whole plan, full plan, no abbreviations. This doesn't work for AI training jobs. When I started working in that space, I was kind of looking, okay, so what are we doing? What are we reading? Where's the plan? And I printed the plan, and it kept printing and printing and printing in my screen, and I was seeing kind of numbers and letters and more numbers and letters, and I'm like, what is this? It's so big, you can't, like a human cannot even tell how many plan nodes there are, or what are they. And so the first thing we did is created a summary of a query plan. Essentially how, like in big data, when we have large data sets, data scientists came up with ways to summarize those. Like they came up with things like average, percentiles, min, max, which gives you a few numbers, which give a sense of what kind of data you have, but it's not the data. There are not enough details there, but you can work with that. So we did something similar for query plans for AI. We created a summary. And essentially here, we don't give you the full plan, but we do tell you, okay, there is a project operator. And we tell you how many output columns it projects. So here we say 14 fields, meaning 14 columns being projected out of this operator. And then we give some names, but not all, because 14 is small. Sometimes it's hundreds and thousands. And we give a name and a type. But if you look at that type row 13469 looks like some sort of ID maybe, some sort of lookup thing. What this is the number of fields in that struct. And it's not a typo. I didn't type it by hand. It's like a screenshot. And I didn't look for the most biggest plan I could find. It was just the first one that was lying around on my machine. 13,000 fields in that struct. And then if you look at how they're computed, we're not going to produce expressions which are many pages long. So what we do, we have a summary of what kind of expressions are used in that project. So we're saying there is a 34,000 function calls, UDF calls. There is 42,000 constant values being used in those function calls. So you can think of something like a plus 1 plus is a function call and 1 is a constant. And there's it accesses 17,000 columns, or it accesses them that many times as a field expression. And then we provide a list of functions with the count of each function, how many each function is being used. And so we can see bucketize is being used almost 4,000 times. And some others are used not so many, or I think that just got cut off. So I'm just providing this to show that the scale in AI applies not only to data, but to metadata, and to simply the query plan that's impossible to even just print out as is. And so later, I think it will be probably next, tomorrow, I think Ori will be talking more about how we can efficiently process plans like this. Because one intuition we get from it is, okay, if there are so many subcolumns we are processing, we probably are not doing data-dependent operations across all of them. So there might be an opportunity for us to break it down into data-independent subsets and run those in parallel, as opposed to traditional project operator, which runs serially. And so we'll learn more about it, hopefully tomorrow. And that's essentially where we are thinking we can solve the memory problem. If we can parallelize the single-threaded today query execution by breaking down expressions into groups of data-independent operations, we can run more CPU, use more CPU to do more processing within the same memory envelope. And so we keep the memory usage. I'm being told I'm going over time, so I will wrap up. I think what I'll say is just thank you for being here. Thank you for being part of Velox community. Thank you for helping us build Prestissima and Gluten. I think we'll hear today from Amit and others on how successful those systems became. That's something that when we started, and we were telling people that Presto can run 3 times faster. And it was like, what? Do you know what you're talking about? This is a reality. And this is a reality, and I can't be more excited about this. As Ali and Sridhar were saying, today and tomorrow is celebration time. I'm celebrating with you. Thank you for you all coming to celebrate with us. Thank you for coming as a community. And let's chat more during happy hour.
Thank you, Masha. Okay, we are at break, so breaks out there. Feel free to go grab. We're going to try to stay on time, so maybe a little bit of a shorter break, but we we have a lot to cover today. So, and folks, there is a ton of seating in the front too. So for people that didn't have seats, there's a bunch of space up here. And last, we are recording all of these sessions, so they'll be available after the show. Hello, hello, hello. All right. I think I'll just hand you this one. Okay, we're gonna get started. So I am happy to introduce Konstantinos, who's a software engineer at Meta, and he is going to be talking about PySpark today. Let's take it away.
Thank you. All right. Let's start. All right. Hello, everyone. My name is Konstantinos Karanassos. I'm a software engineer at Meta's data infra, working on batch compute engines. Today, we're going to be talking about PySpark meets Velox, or like our take on how we're redefining efficiency for our ML workloads. This figure up there, I was playing last night with Meta AI. Its take on what it means PySpark meets Velox. I don't know which one is PySpark, which one is Velox. Yeah. Let's start by looking, you saw at Pedro's presentation, the slides as well. This is the general figure of how the AI lifecycle looks at Meta. You see at the bottom right there the lakehouse. So this is where all our data lands from logs, from various different types of data. We have the lakehouse. We do a lot of data preparation to prepare data so that then we can use them for training machine learning models. You see at the bottom this training line there. We have DPP that Masa talked about that loads the training data, and its purpose is to keep the GPUs busy. So then we use the GPUs to train the models. We get the models, we deploy them in production. Then they are used to do predictions by users. And then there is this whole loop there that as predictions happen, we log data, and then we keep on doing this process. What is very interesting is that we see an important shift in our workload. So the majority of our workload at Meta now is fueling machine learning and AI use cases. This means that we no longer have only the traditional analytics we are used to all these years. There are different query engines that are used in the lakehouse for data processing. Spark, Presto, and DPP are the most widely used ones. Presto is used more for like the interactive type of scenarios, like lower latency, dashboards, etc. DPP, Masa talked about. Spark is what we're going to be focusing in this talk. And let's look a bit at, in general, batch compute for AI. Spark is the main engine used today for all the data preparation of our various AI, ML, Gen AI use cases. Meta maintains one of the largest Spark deployments worldwide, if not the largest. Following the shift I talked before about going from traditional analytics to more fueling AI and ML use cases, we see that SQL used to be for many years the only language that our users could use in the warehouse. Right now, we started offering PySpark relatively recently, a little bit more than a year ago. We see massive adoption, and the reason is AI. People are much more eager to use Python for all their use cases, for all their third-party libraries, and so on. Let's look a bit at how our use cases look like. So we have two main categories of users. The one is our recommendation systems. Basically, the idea there is batch compute engines want to enable efficient data preparation for our recommendation systems, and that's across our products, from ads, Instagram, all the feeds, everything your billions of users worldwide are interacting with. And the second big pillar is Gen AI. You are all familiar with the Llama models. They use massive data to be trained. All those have to be somehow pre-processed. So one of the main focuses is how do we provide all the data to build state-of-the-art Llama models. Let's focus a bit. Let's double-click on the recommendation systems, and let's look at what we're calling feature injection. So the idea here is that we want to add some new features to our training tables, and we want to do that within hours so that we can enable fast experimentation. Until now, that could have taken even up to days, and we want to bring it way lower so that our ML engineers can fast iterate to produce the best models. On the left, you see we have this training table. It's a toy example. We have the user ID on the first column, user 1, 2, 3. And then we have a feature map. So this is the way we typically store our features. We have multiple such maps. But the idea is that we're using maps instead of columns because we have deeply nested structures, and we also want to keep the flexibility for schema evolution, adding new features, etc. So you see there are some F1, F2, some features. What the ML engineer wants to do is wants to play with some new data. So in order to do that, they want to inject some new features in this map. So they use this other table. Again, we have the user 1 and user 3. The target map is this feature map 1, and then we have these F5 features and their values that we want to add. And the result, of course, this looks like, as you all know, it's clearly a join. We want to join the left and the right tables, and the result will be this new map that has been updated with the new features. Now, where this gets complicated is that first, users are in the order of billions. The second complication is that features can be tens of thousands, right? So we have, or even more features. This is not your traditional data analytics. And then we have several questions that are coming up. First of all, how can we perform this massive join fast without taking several hours or days to complete? The second one is, let's say we use Velox. How can we control what exactly happens in the engine? How can we really have tight control of the execution of the plan that gets executed so that we can squeeze the best performance out of this massive join? Another question is, how do we control storage optimizations when we have these maps? Pedro mentioned we have this optimization of the flat maps, but how exactly do we allow the writers to optimize this further is an open question that cannot be easily done. And then a last question is, how can we avoid rematerializing this whole table with all the users and all the tens of thousands of features just to add one new feature? Right? And through this example, this brings us to our main challenges here. First one is data scalability. So all the AI and Gen AI workloads are increasing our demand for data scalability by orders of magnitude. The second big challenge is wide tables. Unlike traditional analytics, tables for ML can be really wide. And by wide, this means both number of features, like we see, for example, in all these recommender systems, but it can also mean much bigger, like each row can be much bigger, each column, basically. So think of it like in Gen AI, you can have multimodality, you can have whole documents and websites being stored, so we also have much bigger tuples. Another observation is that we have custom user logic much more than we used to. So in AI and ML, people use third-party libraries. They include their logic that cannot be expressed as traditional relational operators. And all this brings pressure to our engines for how can we do that more efficiently. Another challenge is data mutability. So applications often need to just update a very small fraction of the data, and we need to do that efficiently. And then we also have what I consider as dev productivity and fast experimentation. We want to allow our ML engineers to very quickly go through this new data to be able to experiment and build new models. What you see as a non-challenge here is that we don't have also the typical analytics here that require heavy query optimization in the sense of 5 and 10 way joins like we used to have. So we see similar computation in that sense, but very different challenges. What are the existing solutions we have in hand so far and that people are using in our lakehouse? The first one is Spark, so what I call vanilla Spark. So it has proven its scalability and it has been battle tested throughout the years, but the very execution of the engine doesn't include vectorization, doesn't have native execution, so this leads to scalability limitations. And of course, what this means is that our users become very crafty about what they can do to circumvent all these problems. Most of it happens through UDFs or Spark C++ transforms. If you're not familiar with transforms, basically it's a C++ process that is running next to the main Spark executor, and then Spark reads the data, pushes them to transforms, and then gets them back. The problem with that is that there is no reusability of components. Like the moment the customer creates this solution, no one else can use it. The second one is, as I described, by Spark reading the data, we have heavy serialization costs. Now, people have tried to bypass that by reading data directly from transforms. But then, if you want to do vectorization, if you want to do all this more low-level operations, you have to rely on the application user to do it, which leads to a lot of reliability issues. Whenever something changes up the stack, we have SEVs, etc. And also, there is no out-of-the-box support for Metalake. Metalake is our version of, let's say, all these mutations, Iceberg, kind of thing that Darren is going to talk to you about later today. Also, no support for different file formats. And then the other thing that we're observing is that we have use case specific services that are created by our customers, are tackling a very, very niche problem, and they cannot be reused. So these are bespoke solutions that often eventually become unreliable and cause problems. So our solution to all this is what we call PySpark Velox, which brings abstractions for native execution on top of Spark. Our goal is to combine Spark scalability with Velox's efficiency and performance and Python's ease of use. This is the high-level architecture. You see the user on the left. What they do is they're specifying their pipeline with a Velox execution spec, so it's the specification of what they want to execute. Then you will see that we have, this is basically a PySpark framework, a framework built on PySpark. We have the PySpark Velox runner. So the first step there is to create the committer so that we can, whatever results we get, we can commit them to the Metastore and write the data, and we generate Velox tasks. The way we do that is we take this specification from the client, we build the Velox plan in C++, we generate ourselves the split, so we look at the Metastore, we look at all the input tables, we generate the splits, then we generate and serialize the Velox tasks from these splits, and then comes the time to run these Velox tasks. In order to do that, we have, at this moment, we initialize the Spark driver. The Spark driver takes these tasks. It starts the cluster with thousands of executors. And then through a Python UDF, we use PyBind, we then initialize Velox. We get the serialized Velox tasks. We execute them. And then as a last step, we commit the result to Metastore. So this is the high-level architecture. Let's get into some details of that. So first of all, Velox plan definition. Users specify their execution plan in Python using this Velox plan builder. You see on the right here the type of, no surprise here, we have scans, writes, projects, limit, filter, various types of joins, aggregation. So under the hood, this builds a Velox plan with metadata in C++ through PyBind 11. And we will soon integrate with PyVelox so that we use the more standard way of doing things. You will hear from Krishna about this at 3 p.m. today. We currently support a meaningful subset of the Velox operators, and the way we are doing things is very easy to extend to new operators. We have already support for different types of file formats. We have ORC, which is the default, but now Nimble is the new open source file format that is much better for AI. So we have support for it. And then the big advantage is that we can specify low-level Velox parameters, which has been key for performance. Just a sample of them is, for example, we can have better control of how we use memory. We have various plan optimizations, for example, how we read flat maps to struct columns internally. We have various configurations for different types of encodings. We do split preloading to mask various I/O costs, and so on. So all these have to be, highly specified so that we can squeeze performance. The pipeline execution looks as follows. We have the pipeline class. Basically, this is specified by the customers. They create the execution plan, they create the committer, and then they commit. It's a very simple API. Note here that Velox has a very low-level API of specifying the execution, and so we have to adorn that with some metadata so that we can commit the results, etc. Then you have your PySpark Velox session. We have modeled this after the Spark session. You do get or create. Then you have the creation of the execution plan. You generate the Velox tasks that we talked about before. Then you create a data frame with the serialized tasks, and then you use a Python UDF in order to drive the execution in Spark. Let's talk a bit more about how the execution happens. One concern is how do we distribute the execution? We create one Spark task for every Velox task, and then within every Spark executor, we can run one or more tasks. By default, we run 4, but we heavily customize that based on the use case. It's an open problem how we can do that automatically so that we don't have to, for every use case to fine-tune that. The good news is that we are inheriting reliability and failure recovery from Spark, so we don't have to worry about all the task retries, stage retries, and so on. We have implemented our own commit protocol. We support single partition queries at the moment, and we support different types of commits. So a user can add a new partition in a table. They can override a partition, or they can do some Metalake commits for mutations. And we have various tools for monitoring debugging. We have a local Velox run so that you can debug just on a single task. What happens, you can run that locally. And we have several internal tools for observing execution. But one caveat here is that it is still challenging given the different systems involved. Some of the benefits we're seeing already. First of all, reliability and developer productivity is much better because we have this shared abstraction. So instead of having users specify, create their own custom-built solutions, now we provide these abstractions within PySpark. Cost and performance benefits for high production use cases is the main reason we did all this. It allows us to iterate fast through this, being able to specify lower-level plans. We have clear semantics because we don't have to go through the business of, okay, is this SQL, is this ANSI SQL, what exactly you're doing. It's Velox semantics, so it's very clear to know what happens. We have compatibility with different versions of Spark. So we have an older version of Spark running. We are currently upgrading to the latest version. PySpark Velox will work out of the box in both. And another important part is that we are learning at a smaller footprint. By smaller footprint, I mean for some specified use cases, and then we can learn and bring the benefits back to the main engine. Let's talk a bit about now the level of abstraction, because that is important. For our AI ML use cases, what we are observing is that SQL or PySpark, the data frame APIs, is too high level for us to be able to squeeze the performance out of our plans, but it is at the same time too low level for end users, right? At least at this stage of maturity of our system. As an example, a high-level operation someone wants to do is what we called before about feature injection. We want to inject a new feature in a hash map field of a table and store it as a Metalake commit, right? How are we bridging this gap between this high-level API that our users want and the lower-level API that we are doing? We let customers specify higher-level specialized operators. So we have introduced a feature injection operator. We have introduced a data merging, clustering operator. And then we allow only power users to build actually Velox plans from scratch. Some features that are currently under development. What we have so far in production is single-stage queries. So these are like map-only queries, which means that your tables have to be bucketed and so on if you want to do joins. We are currently integrating with our internal shuffle service. This is going like later in the month. This will be ready. We are doing the data plane through PySpark Velox, and then we have the control plane still being done by PySpark for reusability. Our current focus is on simple DAGs, like simple two-stage jobs with a single reduce, but we are investigating whether we should open this up further. And another big feature we are adding is Velox UDFs. These are already supported internally for some users, but we want to make this more officially supported by PySpark Velox. Adoption so far. We have a bunch of high caliber use cases across all our AI ML initiatives that are using it. Feature injection across different products are using it. Metalake compaction, so how do you compact commits so that you're not slowed down by, sorry, by merging the commits on the fly. This has been already done in PySpark Velox. We have data clustering so that then you can apply better compression so that you save disk space and also read time. Deleting features from tables. This is also something that we are implementing on PySpark Velox and using in production. And then we have some custom file creation for some internal services, which is also done through some file write operations. And we have several more use cases lined up. And now you might be wondering all this time, okay, there is also the open source project Gluten, which is adding support for Velox in Spark. So where are we starting with respect to that? The reality is that we started prototyping Gluten at Meta. For the last few months. We see some very key advantages here. The first one is that we have better integration with Spark's ecosystem for like specifying the plans, using Spark's API, SQL, PySpark, all this work out of the box. We also saw, based on our investigations, we also saw a bunch of challenges that came up and that we have to overcome. The first is ANSI SQL compliance. We're trying to move to ANSI SQL for our internal offering of Spark. Gluten is still using the Spark SQL semantics. A second one is that we have to rely on Spark 3.4 for Gluten while we're using an older version of Spark still. We're upgrading it now. Integrating with our ecosystem, we have all these custom file formats, custom shuffle support, custom Metalake, and a bunch of different services. This requires work, which is non-trivial. And also there is the part of the SQL part of our workload, which is also still a big part of our workload. It is unknown how much gain we will get once we integrate with a shuffle service. A lot of our customers are using Java UDFs. These have to be rewritten to C++. Otherwise, probably the gains are not going to be as pronounced. But bottom line, realistically, it will take more than a year to move significant part of our workload to Gluten. Where we are right now is our current focus is on the efficient end-to-end execution. We are, like trying to push the envelope on that front. And the longer-term goal is indeed to bring this learning back to the main engine, possibly through Gluten. But this will take longer, and a lot of our use cases are much more urgent. So we're focusing on this end-to-end execution for now. Some performance numbers. So we took this feature injection operation that I mentioned before. We ran it in Spark. We couldn't finish, so what we did is we took 1% sample of our data. That took a little less than 10 hours, or a little more than, I think it was 11.9 hours, actually. So you can see that that is clearly for like our whole data that's impossible to ever finish. Then we took PySpark Velox, what we have today. That took about 11 hours, and that was a 75x performance improvement. And then we applied Metalake on top of that, and that was another 20x improvement. So the end-to-end system that we have today that can do feature injection actually takes about 35 minutes to complete, up from probably more than 100 hours if Spark finished. And to wrap up, this is the second image of PySpark meets Velox that Meta AI generated. So the success of Meta in the AI ML space relies a lot on the success of our batch compute engines. Rexys and GenAI are pushing the limits of our engines in terms of what is possible. With PySpark Velox that I introduced today, we're combining Velox's efficiency with Python's ease of use and Spark's scalability. We introduced a Python API to specify highly customizable execution plans that get distributed by Spark. We have a lower level API through Velox for efficiency and higher level operators for ease of use. We've seen orders of magnitude of performance improvements over production use cases. And all this happened Like we started this, I forgot to mention, at the end of 2024. So we managed to do all this in a matter of a few months. And we have a bunch of exciting future extensions that we're planning to do. We want to bring better multimodal support, vector search, offline inference, and so on. Thank you.
So while Darren sets up, are there any questions that we can take? Or if not, I think you'll be around, right? People can come find you? All right. Come on up, Darren. Thank you. All right. So next up, I'm happy to introduce Darren, who's software engineer at Meta, and he's going to be talking about Metalake.
Thank you, Ellie. Hi, everyone. My name is Darren. I work at a DI, Data Infra Storage Engine team at Meta. So today, welcome to our talk on Metalake, a mutable data warehouse solution at Meta at scale. So this empowers our AI and machine learning workload. Specifically, I will talk about feature injection and the optimizations we applied in feature injection pipelines. Thank you, Konstantinos, to setting up all the context that makes my talk way easier. OK, we will spend a few minutes talk about what is Metalake, why we built Metalake, and the key features in Metalake, and how this Metalake works internally at a high level. And then we will dive into the use cases for feature injection and how Metalake plus Velox accelerate machine learning engineers to adding their features to the flat map and modify the existing flat map on the fly and make it more efficient for the pipelines within 1 hour. And we will also talk about all these optimizations, maybe pick 2 of them to dive into it to explain how these optimizations work at Meta, how we optimize it. OK. Let's start with the motivation. Why we need to build Metalake? Meta actually open sourced Hive back in 2009. This is the immutable solution in the warehouse. Hive Metastore is the backbone of our warehouse. And it supports, the IT idea is to organize the data in a directory tree. So this works well and it's reliable for a decade, over a decade, but it's designed to be immutable. So in the past few years, with the surging needs of training data growth and a lot of use cases coming to us, we need to mutate the data in a more efficient way. So that's why we need to build something on top of Hive Metastore to make the data immutable. All right. So prior to Meta, the traditional way of doing this is to do insert override, like reading the entire training table and modify a small fraction of data and re-insert override back to the directory. That's how typically it works with the immutable architecture. As the business grows, we have a lot of use cases coming to us, trying to solve 2 categories of problems, privacy and training. We are required to remove rows from the table to nullify the entire column, or we need to do training experimentations in a different data set, a playground. And today we will dive into feature injection, specifically how it helps the machine learning engineer to evolve their training lifecycle to be way faster and with a high velocity. OK, so what is Metalake? Metalake is an in-house solution for mutability warehouse. This supports super efficient column updates and the row deletion. This is transactional, and we support data mutations. OK, let's walk through one quick example how column update works. So think about you have a table with 3 rows. You want to update the entire column, city, to a constant value, Metalake. So in a traditional warehouse, traditional MySQL database, what would you do? You just run an update query, very simple. But in the immutable warehouse, what would be the what would be the common way of doing that? There are usually two ways. One is to copy on write. You selectively pick some files you want to mutate and replace the file in place. And the second way is what we're trying to do is merge on read. Since our data is immutable, sealed in a directory, we need to create some extra data files to merge on the fly. Okay, this is the Delta files we create, trying to implement this update feature. So we will have some synthetic data, synthetic columns stored in the Delta file, and the data columns stored as CD, as Metalake. Now, when merge happens, we overlay this Delta file on top of the base file and associate the row numbers sequentially with the base file. That achieves the merge on read with the correct merge result. This is a high-level architecture, how we evolve from the immutable architecture with Metastore to the current Metalake solution. So in Metastore, all the partition, under the partition object, when you insert override a bunch of files, it's written to a directory. And this directory will be hooked to the partition object. That's a very traditional way of doing insert override. But how can we associate the base files with our actual Delta files? We introduce another layer under the partition we call commit chain model. So when you issue an update query or delete query, we create a bunch of Delta files stored in a Delta directory. And this directory will be under this new commit, which is update commit. So we remodel the insert override directory and wrapped into a commit, into the insert commit. Now with the mutation, more mutation queries coming, we will drop more and more commits in this commit chain. So at some point, we need to do compaction and to make the merge on read more efficient. Okay, let's dive into the feature injection use case. Feature injection, the goal is to efficiently enrich our training data set with additional features or modify existing features. This feature can be a single column, can be a map key entries. So in the traditional workflow, this is how insert override works. We extract some features from another feature table F, and we trying to inject them into the training table. What we do is do a left outer join from training table T and the feature table F. We select the additional injected features and all the existing columns from the training table. We create a new table. That's how it works with the insert override solution. But as a comparison, for Metalake-based feature injection, we run an update using PySpark plus Velox data frame. So we only need to selectively choose which column we update. We drop the Delta files. More advancedly, we also invent this map concat solution. Basically, we only need to drop the single features we want to modify. So when we read, we do a merge on read and stitch the map entries on the fly. Okay, this is a high-level workflows we do the merge. So when the training data lands, the training table will join with a feature table, and we create a wide partition. As a comparison, in the Metalake-based feature injection, we only drop one skinny Delta files with limited columns or map keys, which was way more efficient. But the cost is we need to do the merge on read on the fly. So as Constantinos already mentioned, the workflow actually achieved two orders of magnitude improvement. We are using the petabyte level data join. So you can tell like the numbers has been significantly reduced by 75x, And then using Spark plus Velox plus Metalake solution, we reduce within 1 hour. This is, again, it's like petabyte level data join. Okay, let's dive into some Velox optimizations. Since Pedro and Constantinos already mentioned a lot of optimizations we did in the right time, so I will focus on the read time optimization, how we merge the data in DPP. So this achieves reduce the latency regression from 200% to down to 130%, and then we are continuously improving it. All right, so the first optimizations we did is on the update merger. So when we trying to merge the base commit or the insert files with the delta files in DPP, we actually need to consider how we stitch the file in a more efficient way. Here I want to just quickly introduce the concept of batch. Batch is, in Velox, we call it row vector. So usually in DPP, we maintain a fixed size of batch, which is a row batch, and we process it in a batch fashion. Okay, how we position the base file and the delta files. Here we use one-to-one file mapping to stitch the base file to the delta file, and they are row by row aligned, file by file aligned. That way we can sequentially load the data into different batches, and the batch sizes are fixed. Ideally, we can stitch two batches in a more efficient way in Velox. This is a naive implementation. Without Velox, we can do row by row scan and copy the cell value from delta file to base file. But this row by row copy definitely is very expensive. If we use Velox, we can do vectorized copy, which basically within a batch, we copy the entire column to the left-hand side, a little bit faster. The more efficient way of doing that is if the entire column we need is already in the delta file, why should we read the base file column? Especially when the base file column is huge. Data loading into memory costs a lot of effort. So the innovation we have is we directly point, just like pointer, we directly point to the delta column score and append this column to the left-hand side, create a new row vector. That way we minimize the data copy. So this is about aligned batch merger. Okay, but there's always a gotcha. The batch sizes are not always aligned. The reason is we have file stripes. Between every file stripe, there's a boundary. Every time we hit a boundary, you will have a remainder of rows falling into a small batch. People may already familiar with file stripe. Basically, it's the row groups, row chunks within a file, ORC file. And what you can specify is the physical bytes in a stripe. And you divide it by average row size in byte, you get the row count per stripe. So every row count per stripe is different. Okay, so here we also need to do the rebatch. The way we do rebatch, naive way of doing that is, in this example, on the left-hand side, we have base files, which has a larger stripe size. And on the left-hand side, the delta file, which has a smaller delta stripe size. Now we sequentially scan the two files, load them into batch. When we hit the first stripe boundary on the left-hand side, we have a problem. We need to forward-looking to fetch the second batch, which is batch 2 dash. Now what we got to do is copy these two batch and align with the left-hand side batch. If this batch is encoded, the first thing we need to do is flatten the two delta vectors and do two range copy to the large vector. This is quite expensive, right? It costs decoding costs, lose lose the encoding, and you did early materialization, basically lose the, you don't even preserve the encoding during the batch. And this happens over time. We will hit every single delta boundary. All right, the question is, how can we further optimize to preserve the encoding? Let's take an example using dictionary encoding. The goal is to merge two delta vectors. And this is how dictionary vector look like. You maintain two vectors. One is index vector to record every single element. And you have a value vector to record where you can look up. Here we can look up 3 city values. The best case scenario is these two delta vector, they share the same superset of values. Now what we're trying to merge is we can reuse the values vector because they are shared. And then we just merge the two indexes, which is quite cheap comparing to merge, deflatten the dictionary vector and merge all the real repeated values. Especially in the flat map, you have like thousands of floats and store in the features. This cost will be amplified. But in most cases, the dictionary values are not reusable. In this example, on the second delta vector, we have a unique value, San Diego. Now, how can we merge these two value vectors? So the innovation is, why not just merge the values which are not referenced by the first vector? Since the San Diego is not used in the first delta vectors, we can simply merge these unique values into a new value vector. That minimizes the data copy, only copy the not referenced values from the second vector. And similarly, we need to merge the index value vectors. But there's a gotcha here. Since the value has been shifted, we need to do the index remapping, which from 1 to 2. So with this optimization, we bring down the read regression from 200% to 170%. There are other optimizations we are still continuously working on, trying to bring down this number even closer to minimize the regression. All right, to recap, Metalake introduced a partition local commit chain model and associate with delta files, create this base file to delta file association policies, and achieved mutability at scale. And feature injection is becoming way lightweighted. We can only need to drop a very small portion of the file of the columns to disk, and we merge on the fly. This helps the machine engineers to achieve the feature preparation pipeline, and they can parallel their ideas and try on different experimentations. And Velox here plays a key role to accelerate both write pass and read pass with vectorized join and efficient rebatching techniques. Okay, thanks for listening.
Thank you, Darren. We have a few minutes. Any questions before? Oh, yes, Deepak, here.
One quick question. So for the Metalake metadata part, was the reason not to choose an open format like Iceberg or Delta?
Hello. Yeah. So the reason we didn't choose Iceberg and Delta is we have this high meta store. The entire data warehouse is built on top of high meta store. So we're trying to keep the change minimal out of the existing immutable data structure. But we definitely evaluate it.
We already have Hive meta store, but we are also using Iceberg. So was the reason like you are using HDFS a decision maker in using this? I mean, deploying this?
One of the reasons we are using our own file system called warm storage file system, and it's more like a HDFS, and it doesn't maintain the replications. So we don't have a strong replication policy to maintain those metadata files. And also we have some bottleneck if you want to store this metadata file on the warm storage file, and there's a rate limit for those small files. So we need to solve these problems before we move to Iceberg.
Hey, a quick question. Is Metalake open sourced or is planned to be open sourced soon?
We haven't discussed this yet, but definitely there's some innovations like the update merger part, which make the merge on read way faster, could be open sourced, but it's still on the fly for discussion.
Okay.
All right.
Thank you, Darren. All right, next up, I'm going to introduce Binwei Yang, who is an IBMer and is going to be a creator of Gluten and is going to be kind of giving a state of the union on where we are with Apache Gluten. Thanks, Binwei. So plug in here. And then I think this is the clicker, so you just press that to advance. Allow. I think, yeah. Quit, yeah.
Hello, everyone. So today I will give an update of the Apache Gluten project. So I like the name, Stable Union Apache Gluten. So the Gluten is used to combine the Spark and the Velox. So it offloads the Spark SQL engine to Velox SQL engine to get the performance. Today, I will cover several topics. Firstly, it's a simple introduction. I already introduced many times in different forum, but there are some new people today. I'd like to introduce a little more. And then it's the current status of the functionality, community, and the customer adoptions of Apache Gluten, and then some performance data and the roadmap of 2025 this year. This is a Gluten overview. Gluten itself, it's a Spark plugin. So it's a Spark plugin. It's reuse Spark. It's a Spark user transparent. So the reuse Spark control flow and added several components into the Spark. So one is the plan conversion, convert the Spark plan to the substrate plan, and the second one is the memory management. It's you reuse Spark memory manager, but it controls the memory location over the Velox. So, and the columnar shuffle is a big part of the Spark, and then it's similar, and similar is used to support different Spark versions. And the fallback, because Gluten is designed not to replace all the Spark SQL engine. We cannot actually, because of the UDF and the operators we haven't implemented. So for those unsupported features or operators or functions, we have to fall back to vanilla Spark. And then it's the metric. Metric is very useful. Metric is here. The metric is taken from the native SQL engine and show in Spark UI to quickly identify what's the bottleneck of the Spark SQL operators. And under Apache Gluten, we have support different plugins. Firstly, it's the Velox, of course. We already support now. We worked with Meta very closely on the Velox. And then it's a ClearHouse. Actually, Gluten have the ClearHouse backend as well. It's used by Collegians. And we all use the substrate plan and pass the substrate plan to the different native SQL engine. That's the common part we use. And also, we support the Apache General Computer. It's currently we only use the CSV scan in Apache Angular, and then it's FPGA accelerators. We are working. So this is how the Apache Gluten works. Firstly, we use the Spark has the driver node and the work node. In its work node, it has the executors and different task threads. We all know that. And also, they have a Spark block manager to handle the shuffle things. What Gluten does is inside of each task, we check this operator is supported by native SQL engine or not, native library or not. If it's already supported by native library, we send this operator to the native library and execute it and return the data. If it's not supported, then we fall back to vanilla Spark, the GVM SQL engine. And we reuse the Spark control flow. We didn't do anything about the Spark control. We reuse the Spark shuffle. We use the catalyst optimizer, everything. We just offload the Spark circle, the data processing to the native circle engine, because the data processing is a bottleneck. Here is a simple journal of the Gluten. We actually started Apache. We started a Glue project back to 2019. It's 5-6 years ago. And in 2021, end of 2021, we noted that the Glue project cannot go on because our team developed the Apache Arrow-based circle engine. It's very hard. Its performance is not good. Lots of issues. So we moved to Velox in 2021. End of 2021, we started the Gluten repo, and in December of 2021. And you may note that Photon is released in 2020. It's in October 2021. So we actually started Glue before the Photon project released. And then we spent half a year to pass the TPC-8, 6 months past the TPC-DS. Then we focused on the performance improvement of the TPC-8 TPC-DS from 2.3 to and 1.3 to until 3 times and more than 2 times of TPC-DS. Meanwhile, we added some more urgent features like data like support, basic data like support, the CPU support, UDFs frameworks support. And in 2024, last year, since last March, we have several big features implemented here. So in March, we have in August, before August, we implemented a salt-based shuffle. So previously, we used a hash-based shuffle always. The hash-based shuffle have a big issue is that we have to allocate the memory before when we split the branch. And if the shuffle partition size is very large, then we will have a lot of small split, small branches, and the memory is not enough. And the shuffle data size, because each branch, its shuffle data is the partition is too small, and it leads to even larger larger shuffle data size. So in August, in last year, we implemented the salt-based shuffle. And we also implemented fire test over vanilla Spark versus Velox to verify if the Velox functions can work correctly. And later, we implemented SMG support. So before that, we only supported hash-based sign. For the salt merge join, we offloaded to vanilla Spark, but later we implemented that. We also uploaded the perf script. And the partial project is used to solve the UDF issues. So when you have a project, and the project only have one UDF, all the other operators, all the other functions is already implemented in Velox. In this case, without this feature, we have to fall back our project to vanilla Spark. And before the fallback, we have to do a column to row. And after the fallback, we have to do a row to column, vice versa. So before the fallback, we have to do a column to row. Yeah, and after the fallback, we have to do a row to column because they use different data format. And the column to row to column it's expensive actually. It's not only the copy mem copy, it's expensive, and sometimes it's even have its penalty is even bigger than the project itself. So with the partial project, what we do is that only fallback this operator or is this function. So for other of the functions or for the project operators, we still use Velox. And when Velox calculates the project and calculate the function, UDF functions, we convert the necessary columns over this function. So for example, if we have one column, we don't convert that, just send it to Velox, send it back to GVM. And if we have 2 columns, we do a simple column to row, and then send back to Spark. send back to the JVM, and the JVM call the UDF functions, and return the data in raw format, and then we convert it to Velox format, and then continue the next operators. So it's a partial project. It's used to solve the UDF issues. And the other one is that the other way to solve the UDF is, of course, to offload or to implement the UDF in C++, but sometimes it's very, very hard. And the Rust control cost model, so it's used to, we want to offload when we should fall back, when we should offload. And it's not always that Velox can have better performance. For example, Q72 of TPCDS, Vanilla Spark actually has better performance. So we need a way to detect how under which condition we should fall back to Vanilla Spark, and under which condition we should use Velox. So it's what Rust is about. And in this year, there are many new features implemented again. And the first one is the state-level resource adjustment. So one big issue of Gluten is that when we allocate the memory, Vanilla Spark uses on-heap memory more, but Gluten uses all off-heap memory. It's allocated by all the memory allocation is happening in Velox. It's off-heap memory. And when we implement the Gluten, when we use the Gluten to run the query, sometimes for some states it has to fall back to Vanilla Spark. Then we have to configure a large on-heap memory. But for some other states, we already offload all the states to Velox. In this way, we have to configure a large off-heap memory. So the Velox memory, consumed memory is much less than Vanilla Spark, but it does solve some. To finish the query, we have to configure a large on-heap memory and a large off-heap memory. And eventually, the memory consumption is even bigger than Vanilla Spark to run these queries. The state-level resource adjustment is used to solve this issue. So we detect that these states have fallback. Then we fallback these states to have fallback operators. We fallback the whole state to Vanilla Spark. And then we restart the executor using more on-heap memory. And after these states, then we start the executor use off-heap memory. So we change the executor profile. It's already supported since Spark 3. We change the executor profile and use the Spark's dynamic resource allocation feature to allocate a new operator or new executor to fulfill the on-heap or off-heap requirement. So this is how the state-level resource adjustment works. And then it's the query trace. Query trace is used to. So in Gluten, we need a way to easily debug or optimize the Velox operators. So, but if you run a query using Gluten, it's very hard. It's on top of Java. It's lots of. We need a way to offload or to reproduce the logic, the whole logic in C++, and we can use the C++ benchmark to run in native. And previously, we already implemented the state-level benchmark. So we can dump the data before, after the reducer read the data, so we dump it. And then we dump the query plan over the whole state. And then we use the input data and the query plan to reproduce the whole state in Velox. We can do that in single thread or multiple thread. And that's one feature we use to do the optimization or to debug the Velox. And the other one is that Velox recently added a new feature. It's the query trace. So it can be used to trace the single operator, not only the whole state. You can select the hash join or select the project to trace it and implement that. It's the query trace we added to Gluten support. And the Java 17 support, it's a new feature, and also there are several guys in community to start to add the ARM support. So currently the ARM support, the Gluten can run on ARM machines without any issues. And also one big feature, we created a POC over the GPU, and we just upstreamed I think last week. It's through the UDF, thanks to Greg and the NVIDIA team. And also the other big feature, we started the Flink support. It's talked many times with the Gluten customers. So they wanted to use the same way, use the use Velox to offload the Flink operators, the SQL operators. And, but we don't have any resource on that. And recently, one company in China, they started a project and they created a POC, and the POC is under review, active review. And one thing I wanted to highlight is that 2025 is a new start. It's a new journey start to the Gluten project, to me and to the Gluten team, to the whole community. Okay, this is the current status of the community. So there are more than 163 contributors from more than 25 companies, and there are 1.3 stars and keep growing. And we have the Apache Slack, the ASF Slack channel created, and we also have the WeChat group. So currently, most of the Gluten users are still in China. And we also created our linked page in, and we have the Slack, Velox Slack channel. So the Gluten adoption, Gluten is already used. We know the Gluten, Velox itself is used in Meta. It's very mature. So it's much more mature than 1 year ago. And the Gluten Velox is known to be adopted by more than 10 companies. So, but in the WeChat group, we have more than 400 people, I think. Almost every Chinese companies who has a Spark cluster, they already tried or already adopted Gluten. But most of them didn't ping us, or they ping me, but I don't have time to cover. So it's already used there. And because the Gluten is designed to not fully replace the Spark SQL engine. So in their adoption, they offload the parts of the queries and with the performance gain and fallback the rest with some other queries. Currently, most of the companies, they still use a manually set. So they set a couple, they manually detect this query and should fallback that query should offload. So they manually set it up. And the Gluten and the Spark can run on the same cluster, definitely. So it doesn't need any extra requirement over the hardware. It runs the same hardware they can use. So the query, they can switch the Gluten and the Spark SQL engine seamlessly on the same cluster. And here is some cloud providers used. AliCloud, they joined the Gluten community very early. I think it's when we started Gluten, 2 months later, they ping me and they start to contribute. Microsoft Fabric, you know, and Google Data Proc, there will new session later. And we are working IBM, Watson X data integration now, and there are more to come. And the Gluten ClearHouse is used mainly by Clearance and Big O, the two Chinese company. So what I wanted to highlight is that Gluten currently is already running on several nodes in those big clusters. So some of our customers told us it's really amazing. The performance is very good. Like Meituan, they claimed 40% of the resource saving. It's amazing. And there are some common issues, obviously. We cannot solve everything. So first one is the functionality. So exceptions occur when the operator should fall back, but it's not. So sometimes we solve this issue still. And the result mismatch issue is another big issue. So the vanilla Spark is not a standard, a SQL standard, but sometimes it also has a bug, but we need to make sure that the Gluten result, the Velox result match the vanilla Spark result, even it's not correct. So we have to make that in this way, the Spark team can tell their customer, their business customer, that you can use Gluten transparently. It's transparent to you. You don't need to worry about the results. And but until now, we still see many cases the result is different actually between vanilla Spark, and we are trying to solve that. Another one is still the memory issues. We tried our best to under CPU support, under off-heap support, under on-heap support, but currently sometimes we still see the Gluten task or Gluten executor is queued by Yarn or OS or global OEM. The main issue is that the Velox should, or vanilla Spark should track every big block of memory allocation. So all the bigger block of memory allocation should be tracked by Spark. And in the framework, when the Velox use the Velox memory pool API to allocate memory, then we can make sure that it's tracked by vanilla Spark. But actually, it's many memory allocation is not using the Velox memory pool, and it's not tracked by vanilla Spark. In that way, it's counted into overhead memory, and eventually caused OOM or killed by yarn. And also, we noticed some performance issues, and the first one is the spill performance issue. The spill, once the query has spill, the performance is not good. And the sort, we noted that the sort operator in Velox is not faster, or n times faster than vanilla Spark. It's almost the same as vanilla Spark. And then it's a column to root column with a complexity type. And the complexity type is used more and more, but unfortunately, we noted that with the complexity type, the performance is still not as good as we expected. And this is the Gluten benefit, the performance boost benefit. So this is, the test is on AWS for R60 ID to X large instance SF500 on TPC and TPCDS. And we will upstream this script to Gluten and upstream so everyone can reproduce the performance number by yourself. And one thing to highlight is that in vanilla Spark and Gluten, we use different partition numbers. And we use 2 times over or 4 times the bigger partition number in vanilla Spark than Gluten to keep no spill triggered on both. So both vanilla Spark and Gluten, there is no spill here in this test. And the Gluten is 3 times better on TPC8, and the TPCDS is 2.53. And this is tested on Spark 3.5. And the Gluten benefit is not only the performance. Actually, the more important benefit comes from memory utilization. From this chart, you can clearly see that when we run vanilla Spark and the Gluten, and you can see that the used memory in vanilla Spark is almost 80%. Actually, it's already triggered a spill in this test. But in Gluten, it's under 20%. It's under 20%. Only Q21, the performance is the memory is close to 80%, but no spill triggered. There in vanilla Spark, it's also 80%, but it's already triggered the spill with a spill. So here we use the same partition size over Gluten and the vanilla Spark, which means that the customer can configure their executor with half or 1/4 of the memory vanilla Spark used. And if they configure the same memory, then less spill will happen in Gluten, and the performance is boosted again. If they configure less memory for each executor, then they can start more executors on the same cluster. It's because that the common case over Spark runtime is that the memory size is the limitation. The CPU number is not. The memory size is. So once they decrease the memory size, more CPU will be used on the cluster, and then they can get better performance. So they impacted each other. And also we noted that especially on the cloud, because on the cloud, the memories, the S3, like the S3 throughput and the network throughput, it's already there. We cannot change. And to Spark, we may say that, okay, CPU utilization is very high, and it's good. The memory throughput, the network throughput is not a big issue, or the disk is not a big issue. But when we run Gluten, because the Gluten is 3 times faster, in theory, it also needs 3 times more throughput over S3 and the network. But on the cloud, it's not possible. It's limited. And when we run the Spark, when we run the Gluten, we can see that the I/O will become a bottleneck commonly, and the CPU utilization can decrease. In this way, we can still save the power cost. Okay, this is the roadmap, the same roadmap over this year. In this Q1, we focused on the performance track on AWS. Previously, we don't have this environment, we don't have this budget. Now in IBM, we can do these things. We keep track of performance on AWS. And then we ported the Iceberg UT. We under Iceberg, Hudi, and Data Lake support last year, but actually we didn't port the UT. We didn't pass the UT. It just support the basic reading, memory, the file reading, the partition reading, but it's the UT is not passed. This year, this quarter, we take some time to port the UT and pass the UTs. And there are many UTs still failed. We still fallback. There are many UTs fallbacks onto VeloxSpark actually. And the Velox upstream, we're still working on this and the state level resource adjustment. And we started the first GPU POC here. That's the implement. Under Q2, we focus on documentation, dictionary shuffle. Dictionary shuffle is used to decrease the shuffle data size. In this way, we can get better performance because the shuffle data size decreased. If your bottleneck network is a bottleneck, you still can get the performance. And storage memory. Storage memory is something we didn't support until now. And in VeloxSpark, it uses execution memory and storage memory. It can adjust it between each other. But actually, we already use execution memory. And the Spark 3.4 support once it's become released. Currently, it's still not released yet, officially released yet. Under PHG, and then in Q3, we will under PySpark because PySpark, especially Spark 3.4, there are more features coming in the PySpark. And Iceberg, we will under Iceberg write support. Currently, Iceberg write actually for back to VeloxSpark, and we will under that to Gluten under Hudi Data Lake UT, and then Q4 we will under Hudi our more PHG optimizations. And one big thing to happen in Q4 is that we plan to graduate from Apache in Q4. And this is currently. I want to highlight the accelerator support. So in accelerator support, we have two ways actually. One way is that we send the substrate plan to the accelerator, and then the Velox convert the data to ANRO and input the accelerator, get the ANRO data output, and then send to the Velox. It's one way to support. Currently, we supported from UDF is in this way. The Velox will offload the operator to UDF. We can control that. When we convert the substrate plan to Velox plan, we select the UDF operators or the Velox operators. We select that, and then Velox itself will handle the data conversion, will handle the GPU calls, everything, and then get the data back to VeloxSpark, to Velox. We created the POC is already upstreamed, so the performance is still not good. Definitely, we just passed the POC, created the Docker. It's a start. I think it's a start. And the Flink support is just presented. The POC are already created in community, and we started working on that. The community actually working on that. Okay, I think that's all the things I want to talk today. And if any questions, I don't. Yeah. Sorry. Wait. Yes. Yeah. The binary release doesn't have. The binary release is all x86, but we can understand. Yeah.
When you showed the timing differences, what percentage of that work is like bioscans, where that might be harder to achieve, and what percentage of that work is like doing other things where you probably could expect greater performance increases? So in those workloads that you were looking at.
Yeah, so for the workload, definitely the hash join, the prefer scan, hash join, and the hash aggregate, they are the main operators, so we can get the performance. And here, if we compare to the VeloxSpark, one tricky thing we actually do is that we use more hash join. We use bigger broadcast hash join threshold. So the current plan is a bit different. And when we compare the hash join of Velox with the VeloxSpark, the short merge join, the performance definitely it's much better. Well, but we can support that because Velox itself supports spill in hash join, but Vanilla Spark doesn't support spill in hash join. It only supports sort.
All right, thank you, Binwei. So we are at lunch. Lunch is served same place where breakfast was, right outside. And feel free, we have the outdoor area. If you want to go sit outside, it's beautiful out. Obviously, all the tables here. And then we're going to get back, I think, at 1:15. So we'll try to get started on time. Thank you.
to think that the rhythm is the most important thing, really. If one thing got off rhythmically, the whole universe would collapse.
All right. I think we're going to try to stay on time here and get started. So welcome back. Hope everybody had a great lunch. I am thrilled to introduce Abhishek Modi from Google today, who's going to be talking about their work with Velox and specifically Apache Gluten and data proc.
Yeah, thank you so much, Ali. Hello, everyone, and welcome back post-lunch. I know every one of you must be feeling that post-lunch lull after having this delicious meal at Meta, but hopefully I'll keep it short and interesting. So here is something interesting for you folks to chew on. Did you folks know that it takes significantly more amount of time to copy data from memory to CPU than the actual processing time on CPU in modern data analytics? And this is a foundational bottleneck on processing. And the technologies like Velox, which is doing efficient CPU execution using vectorized engine, are not only an incremental improvement, but they are a new way of doing the processing. They are a new thought in this era, and they do a significantly improvement in the processing. So I'm Abhishek. I'm from Google, and I'll be talking about why we integrated Velox-based technology in data proc, the challenges that we faced, how we solved that in data proc, and what are the production scale challenges that we faced at Google, and some of the performance improvements that we did as part of this journey. So where is this magic happening of Velox and Gluten in Google Cloud? So it's all happening in Google Data Proc. And think of Data Proc as Google Cloud's fully managed and scalable service, which allows customers to run open source data processing frameworks like Spark, Trino, Hive, Flink, etc. It takes care of cluster lifecycle, cluster creation, scaling, security, monitoring, while customers can focus on their real workloads while leveraging the open source APIs and tools which they are comfortable with. So customers don't have to worry about entire cluster management. That is all taken care by data proc. So we are seeing a sheer increase in data processing demand from our customers. It is not only growing, it is growing exponentially year over year. The amount of data processed by customers has grown by up to 5x in last couple of years. And with this introduction and adoption of AI and ML workloads, the kind of innovations that we are seeing in AI and ML space, this demand is further going to grow in the future. Now, on the one side, we have this rocket ship demand of data processing. I would like to present a counter viewpoint that the raw processor that is responsible for actually doing the data processing, which is CPU, their performance is kind of plateauing out now. The era that was defined by the Moore's law, where we were seeing exponential growth in hardware performance year over year, is kind of coming to an end. Previously, we used to see approximately 20% performance improvements year over year just by hardware improvements. So that free lunch is kind of over, and we have to do something new to kind of get the performance improvement for our customers. And what does it mean for our customers? So we have an increasing demand for our customers, and they want to keep the infrastructure cost as a fixed percentage of their revenue. They don't want their infra cost to increase exponentially with their data processing demands. So cost is a constraint within which customers operate. And since previously they were able to increase the data they used to process exponentially just because of the hardware innovation, and that no longer holds true, so we have to now think about newer levers of innovation. And for that, we have two paths. So one thing that we have realized is this is an era of building efficient hardwares and building hardware that is more focused for data processing world. And there are like lots of companies working in this space. So one path for us is to leverage accelerators for meeting the customer requirements. And then there's another second viable path is to build efficient software. And intelligent and efficient software is the need of this hour. And Velox-like libraries are built to squeeze out maximum performance from each cycle of the CPUs. So we decided to integrate Velox and both GPUs in our DataProc offering. And last year, we launched DataProc Premium, which supports integrated GPUs, as well as Velox and Gluten-based execution in Spark. As of today, there are 10,000s of jobs from the customers running every day on DataProc Premium, which is backed by Velox and Gluten. So we are able to run Velox and Gluten at scale in real production environments for our customers. And what does our customers see with this integration? So our customers are seeing approximately 3x better performance for their Spark workloads because of three areas of improvement that we did in our DataProc Spark offering. One is like we integrated it with Velox. Second is we did lots of I/O optimizations. And third is like we have our own query optimizer, which is derived from some of the Google's other engines' query optimizations. So customers are now able to process way more data at the same cost and at a higher pace at DataProc. So doing a deep dive into what this architecture looks like, how did we productionize it into production for DataProc? So we built this architecture composed of different building blocks. And we support multiple engines, like Spark and Ray right now, but we are planning to support Reno and Flink in future. And we have this intelligence layer that decides whether we should use Velox or GPU-based execution or the normal engine for the execution of the workloads. We have our own custom optimizer that is based on the hooks connected with the Spark optimizer. So we re-optimize the plan that is generated by Spark's Catalyst optimizer. Then we have our own caching layer on top, which caches like hot data on the local SSDs within the clusters. And we are building our own layers for materialized views and indices, which can be used to reduce the amount of data scanned. Then we support multiple storage connectors. The primary ones are GCS and BigQuery connectors, because around more than 90% of our customer workloads accesses these storage connectors. But we also support like Bigtable and Spanner connectors, because some percentage of our customer workload uses that. And the architecture has been built using the building blocks so that it becomes a lot easier for us to support newer open source engines in an efficient way on DataProc in a faster way. Talking about Velox, after the integration of the Velox, when customers actually started trying it out, they faced different kinds of issues. And I'm going to categorize them into three major pillars where we worked on. The first one is the performance. So when customers started onboarding on Velox-based execution, some of the customer workloads started seeing the regressions. And when we did a deep analysis of those regressions, we found some patterns. The first pattern was workloads which have high number of broadcast hash joins started seeing regressions as compared to normal Spark performance. Then the second pattern was when there were consecutive joins. In those cases also, we saw some regressions in customer workloads. So I'll be talking in deep about some of these optimizations that we did at DataProc to solve some of these problems. Then another area where we invested a lot into is after integrating Velox-based execution, we started seeing that the bottleneck shifted from execution to scans. And lots of our customers' workloads were slowed down because of the slower scans. So we improved the I/O connector that is used for accessing the GCS. And then we also added support for new data sources, including BigQuery native tables and BigQuery Iceberg tables. BigQuery is one of the primary engines used at Google Cloud, and lots of our customers use BigQuery storage. So increasing the scope of Velox to these data sources was crucial for our customer adoption. Then the third thing that we focused on is how to increase adoption of this technology. There's always resistance for customers to adopt anything new. Specifically, Velox as an engine is evolving. They were always worried about the correctness of the results, and they didn't want to do the testing or trying out at their end. They wanted a simplified way from the data proc so that they can simply onboard on it. And we take care of choosing the correct technology for execution behind the scenes. So that's where we developed this intelligence layer that has this automated qualification. So it figures out whether this workload is suitable for pushing down to the Velox-based engines, and it automatically pushes it down to the native or Velox-based engine for subsequent runs. Then we also developed a technique for automated validations. So customers can opt into it, and what it allows is to have some percentage of your workloads, and some stages of that workload would be tried with both Velox-based execution as well as Spark-based execution, and the results would be validated at the end, so that customers can be very confident about the correctness of the results. Because in some cases, as Binwei also talked about in his talk, there were some semantic incompatibilities between how Spark behaves and Velox behaves, so customers were worried about those semantic incompatibilities. So let's double-click on what we did for broadcast joins. So when we analyzed, a majority of the data proc workloads in real-world scenarios have broadcast joins. And at data proc, we don't have a fixed threshold for broadcast joins, as there is in open source Spark. So open source Spark has a fixed threshold of 10 MB for broadcast joins. But in Dataproc, we do historical analysis of the event files. And based on the driver and executor memory, and based on the historical analysis, we adapt the broadcast hash join thresholds. So what does it mean is the actual value of broadcast hash join threshold could be way more than 10 MB. Now, for open source Spark, the way broadcast hash join works is they broadcast hash tables directly from the driver. So the hash table is built only once in the driver, and then all the tasks use the already built hash tables. But in the open source integration of Velox with Spark, this driver was just broadcasting the raw data, and hash table was built at each task again and again. So this created an overhead, specifically if the broadcast hash join threshold is high. So each task was recreating this hash tables every time, and that causes issues or delays in our customer workloads. So what we ended up doing is building a caching in executors, and we build hash table once in the executor, and then each task basically uses that hash table instead of building that hash table again and again. So we effectively reduce the number of times this hash table is being built from O of number of tasks to O of number of executors. And that way, we were able to help our customers migrate most of their workloads or unblock their workloads to migrate to Velox. Then another problem that we saw is with the significant improvements in the execution, the task scheduling and serialization became a major overhead. The guiding principle for distributed engines is that your task scheduling and serialization should be around 5% of overall task runtime. But since with introduction of Velox, the execution improved significantly, this task scheduling and serialization overhead became more than 30 to 40% in our customer workloads. So to solve this problem, we introduced something called adaptive split computation in Dataproc's offering. And what it does is it adaptively coalesces multiple splits into bigger splits and then gives it to the execution engine. So that increases the executor efficiency at our level, because now executors are not waiting for the tasks, and they have big tasks to work on. Along with that, it also helped in reduction of scan operations, because for each split, we have to do some metadata operations, and GCS as a storage or any remote file system storage is not optimized for small size scans. So this adaptive split computation helped us in improving both scan performance as well as effective utilization of executors. Then as I talked earlier, 18% of data proc serverless workloads processes data on BigQuery storage. And we added support for BigQuery storage, BigQuery Iceberg tables, as well as BigQuery native tables in Velox. And how does it operate is basically driver gets the metadata of the table, and then it calls the create read session API on BigQuery storage, which gives the read streams to the driver. And you can think of read streams as Spark partitions. So we serialize the read streams and pass it on to the executors. Now we implemented an arrow-based read streams API in BigQuery storage API. So when executors uses these read stream APIs to read data from BigQuery storage, they directly get it in arrow. And now this arrow can directly be consumed by BigQuery connector. So since Velox is directly consuming the arrow file format, we avoided this whole conversion of formats, and that helped us in building a very efficient BigQuery storage connector for Velox. And similarly, we implemented the write flow for BigQuery storage connector in Velox. So here, driver basically creates a temporary table or the destination table using the BigQuery API. And then executors keep on writing data directly in arrow format to BigQuery storage. Upon the completion of the data writing, executor sends, or the task sends a commit message to the driver, which contains the commit ID. Once driver receives the commit IDs from all the tasks, driver calls a batch commit API on the storage to finalize the table creation. Now, in case of insert overwrite, driver also takes care of cleaning up the destination table if required. So with these two, with the introduction of BigQuery storage connector in Velox, we were able to open up Velox for even more customers than before. Now, talking about GCS connector, which is the primary data source for Google Cloud customers. So we found out like scan is the biggest bottleneck. In fact, from the morning we have discussed this, like with computations becoming more effective, the bottlenecks are kind of shifting towards scan, right? So we implemented a connector which is based on the gRPC to reduce the number of network hops that we have on the path of the scan. So gRPC is like a high-performance open source library that is used to interact with cloud storage. So as you can see here, by default, the traffic goes through multiple hops, that is via GFEs and different servers, and then it reaches the cloud storage backend. So that limits the throughput that we see, as well as it introduces the latencies in terms of TTFP. So we developed this direct connectivity part to cloud storage that avoids this inter-between layers. And right now it uses simple gRPC APIs, but in future we are planning to move to BiDi APIs of gRPC. And that will further avoid the network latencies and can give us a very higher throughput than we typically see. So as you can see here, if we use the typical JSON APIs, though the initial startup time is less, but the time for subsequent reads is way higher than the gRPC ones. With gRPC APIs, if you use it for long-range reads, it gives you subsequent performance improvements. On our C++-based connector, we saw 50% reduction in P50 latencies with this gRPC-based connector. And the last thing that we developed on our end is the intelligence layer. So customers can focus on their workload, while like intelligence layer takes care of finding the best way to execute their workloads. And as part of this, we store all the Spark event files, historical event files of our customers at our backend. And we have a background service that keeps on running, that keeps on analyzing those event files and generates insights from it. The insights could be of very different natures. The simpler insights could be like what should be the memory configurations that are required to run these jobs, what should be the broadcast hash join thresholds. But now we have developed analyzers that can decide what is the best execution engine for these jobs, whether this job should be pushed down to the Velox-based engine or GPU accelerators, or should run on Spark. So this insights, so I'll double-click on this analyzer, which makes this decision of whether this job can be pushed down to native or not in this talk. So we start with the raw plan on the left side, and then we have a node visitor, which marks which all operators are supported by Velox. And this could be like a very simple logic, whether this operator is supported in Velox or not. But in some cases, we have developed a complex logic, like what is the schema of it, whether we have correctness results for that schema or not. So for example, initially, we were facing some issues with timestamp data types. So those timestamp data types were excluded in terms of supported operators. And it has like more complex logic, like for broadcast hash joins, what is the size of the left side, and whether we should push it down or not. So after this visitor, it identifies the nodes which can be pushed down to the Velox. But then we found that if we break the whole stage code gen boundaries of Spark and we push down to Velox, it doesn't help with the performance. So we implemented another visitor that takes the output of the first visitor and makes sure that if a single node is not supported within the whole stage code gen boundary, we mark that entire whole stage code gen as not supported. And then later on, we implemented a cost analysis function on top of it that suggests whether this whole workload can be pushed down to Velox, or we should use normal Spark engine for this workload. Yeah, that's all I had. Thank you for your time.
Any questions while we get the next presenter set up?
Are you going to open source the gRPC client? Yes.
All right. Thank you, Abhishek. All right. So next up, we have our first lightning talk of the day from Shiyugan, who has been working on Velox for, I think, a while now, right? And you'll be talking about techniques for addressing UDF. Uh-oh, I lost my thing. Incompatibility between Spark and Gluten.
Yeah.
Cool. Start mirroring. Quit. Yeah.
Hello, everyone. My name is Shi Yu, and today I'll be giving a lightning talk on techniques for addressing UDF incompatibilities between Spark and Gluten Velox. So many companies are productionizing Gluten and Velox to speed up their Spark cluster execution time. And one of the challenges is that whilst Velox has mostly have UDF support parity with Spark, the Spark versions are written in Java, obviously, or Scala, and the Velox versions are written in C++, so there are different implementations. And sometimes, due to subtle differences in the implementation, it could lead to result mismatch. And when there's a case of result mismatch, it could lead to, due to UDFs, it could lead to further downstream result mismatches, such as joining on two columns not working correctly due to the string payload being different, or just that if the results are different, then you don't know if for a particular Spark task, whether you can proceed to replace the default Spark runtime with Gluten and Velox. So, so this is kind of a blocker for productionization. And today I'll go over some techniques for tackling this like category of issues. So just some examples of UDF incompatibility. So some of the most commonly used UDFs are get.json object, regex extract, and the date format. So I think anyone who has been around large-scale ETL jobs will have seen these UDFs in the wild. And on this slide, I just list how under the hood, the Spark and Velox version uses different, let's say, JSON or regex engines or libraries, and which could introduce complications that result in result mismatch. So so next we're just going to get JSON object, and I'll just give a quick example of how this UDF works for those who don't know. So say you have a JSON text, and you can give it like a path, and it will return basically a substring piece that's part of the original JSON. That's the UDF. And so technique number one that I'll present is to simply port the Spark UDF logic to Velox in C++. So for example, the get.json object implementation in Spark, the way it's implemented is it uses the JSON library for the parsing and scanning of the JSON input text. And then it uses, and then on top of that, it implements a JSON path query evaluation logic above the Jackson scanner. So if we were to, and the current Velox's implementation of get.json object, as far as I'm aware, do have quite some number, or at least a few edge cases where the results don't match. For example, when it comes to handling of illegal characters in the JSON, badly formed JSON, like invalid JSON, or even the escaping or not escaping of special characters. So one potential way to solve this issue would be that we would basically, we could take hypothetically an open source C++ JSON library and augment or tweak its scanner piece so that it behaves identically with Jackson or as close as possible. Specifically, when it comes to illegal character tolerance, for example, I think \n, the new line character, as a literal is not legal in JSON. That's just one example. And also and also I think we could also make the scanner. So when it comes to scanning JSON text, there's the full parse strategy, which parses the whole JSON. And then there's also the strategy of just parsing the JSON as you go on demand. And with the on-demand mode, if you have a badly formed JSON that's, let's say, prematurely truncated, if you only need to scan the first part of it, and you do that on demand, then whereas a full parsing JSON scanner will blow up and say the JSON is badly formed, if you have an on-demand scanner, then it will be able to tolerate that input. So basically, a port would involve a JSON scanner at the fundamental level that behaves closely to Jackson. And then we could also, on top of that, we would implement a one-to-one port of Spark's Scala implementation of the JSON path evaluation logic. And if we do this, we can achieve basically better UDF comparity to the point where within, let's say you're in a big company, you could almost get it to 100% fully identical to the Spark's Scala implementation. So that's one way. And then the other two UDFs I mentioned, regex extract and date format, these are also widely used. So the reason, again, these are hard to get matching with Velox 100% is because with most of these UDFs, it comes down to using some Java or C++ library to do the heavy lifting of the core part of the UDF logic. So for example, for regex extract, Spark uses Java util regex, and for formatting date, it uses the datetime formatter. And the issue is in the C++ world, there simply just isn't an equivalent datetime formatting library or regex engine that behaves identically as the jar libraries in Java. So basically, one way is, as the first technique mentioned, you could do a full part of the logic, but that probably would be which is what this slide mentioned. So is porting a solution? I think many people might agree that it's too monumental a task to port Java util regex basically to something that's entirely written in C++. So in this case, one technique we can use is basically, because if you're running Velox with Gluten on Spark, you probably are inside of a JVM environment. For example, I believe Velox is implemented through JNI. And in that case, you have a JVM runtime already available to you, or you're running inside of one. So one technique we can use is to have the Gluten layer basically pass in a JVM reference pointer. And then once you have that, you can basically call Java libraries by writing a piece of C++ code like below. That comes from just an LLM generated code. But if you call that, then that will allow you to call a Java method from inside of Velox in C++, and it will get you basically the identical regular expression engine behavior that you'd get in Java land. So that's the second technique we can use. And yeah, thank you. I think that's the end of the lightning talk. And any questions, I'll take them. Sorry.
What about performance impact of this? Any concerns around that?
So yeah, basically, I think these two techniques would be for cases where it's critical to fix, but there are no other alternatives. So I believe if you call a Java function from Velox, it would still be faster than I think what was mentioned earlier today, which is basically fallback to Spark because there's a UDF you cannot handle, because that would involve a round trip of column to row to column conversion. So I think this overall would still be better performant than the alternatives available. Unless, of course, one more alternative would be for you to for some customer to accept that result mismatch is tolerated and it's okay. You don't have to match results 100%. But I think in the context of any systematic productionization rollout, normally there's a piece of the rollout logic that basically compares the result and makes sure they're identical. And that comparison logic is usually fairly mechanical. So, which means it always comes down to probably leaning on the side of achieving result fully matching. Yeah.
Okay, thanks.
All right. Thank you.
Thank you.
Next, we have Felix from Pinterest, who's going to be sharing an update on their work on integrating Gluten with their platform.
Okay. Welcome to this lightning talk where I'll present how we are enhancing our data platform here at Pinterest. This is a follow-up talk to a talk my manager gave at VeloxCon last year, and I will share some of the improvements we've done since then. We are very committed to using Gluten and Velox on our platform because we are seeing good performance results, and some of them I will share today. So this is the agenda. I will give a small overview of our platform and what we're running, and I'll explain why we picked Gluten and Velox and what the platform integration work we've done so far. Then I'll share some performance improvements we are seeing for our ad hoc workloads, and I'll also share some of the challenges we are facing integrating Gluten and Velox into our platform. I'll wrap it up with sharing our future plans. About me, my name is Felix. I'm a software engineer on the Big Data Query Platform team at Pinterest. We own 2 major services at the company, Spark SQL and Trino, and today we'll be focusing on our Spark SQL platform. So our platform, we run more than 25,000 scheduled jobs and more than 8,000 ad hoc jobs every day. Our entire fleet consists of more than 15,000 instances, and we have more than 500 daily active ad hoc users. With our partner teams, we're currently in the process of migrating our cluster to Kubernetes away from Yarn, and we use Caliborn as our shuffle service. Most of our jobs are entirely SQL-based, and most of them are running on Spark 3.2 at the moment. So why did we pick Gluten and Velox? We're seeing increasing job requirements from all our customers. This is driven by increasing data sizes, more complex jobs, and a lot more machine learning workloads. Often, our clusters are memory bound, so we're looking for ways to alleviate that memory pressure, and native execution has shown large gains in a lot of data systems, so we want to take advantage of them by integrating Velox into our existing Spark infrastructure using Gluten. What was really important to us is that the integration should be easy and seamless, and we can start upgrading jobs one by one. That's the case with Gluten because we can just build a jar and distribute it to the jobs, and then we manage all the configurations on behalf of the user. They just have a simple configuration that they can turn on and off. We're also very excited by the fast-moving open source community that always keeps improving the project. And we're also very happy that it's supported by large companies like IBM and Meta. That gives us a lot of confidence in the future of the project. To integrate Gluten and Velox into our platform, we have done a few things. One, every compatible ad hoc query is automatically using Velox by default now. We achieve that by checking for fallbacks to JavaSpark on Livy. That's our job submission system for ad hoc workloads. This is achieved by running an explain on the query, and only if there are 0 fallbacks detected, we are enabling Velox for that query. That's something that we want to explore more if we can tolerate certain fallbacks while still seeing better performance, similar to what mentioned in earlier talks today. The configuration management for our users is integrated into our custom Spark build so that users can just set a simple config and don't have to worry about what memory config to set and enable RFeed and a variety of other things. It also works in our Airflow operator that a lot of our customers use. And we started onboarding some scheduled jobs with experienced customers that are owning very large jobs. There's currently no fallback check on scheduled jobs, as there's no Livy host that could run an explain session and check for fallbacks. Also, while we are migrating our cluster to Kubernetes, we also started migrating to Caliborn as our shuffle service. And Gluten had support for that early on. So we did a bunch of validation and performance testing work to make sure that it works nicely. We also, within the team, built a sampling and testing framework so that we could run our production jobs quickly and validate rebases and fixes more effectively. So performance benchmarking. During last year's presentation, we showed a performance benchmark where we tested the heaviest queries on a dedicated cluster. So there was no other queries running except the one query that we wanted to benchmark to reduce noise from other resource usage. So the goal of this test was to quantify the maximum possible gain that we could see in like the best case. And we saw an average improvement of around 70%. This is an evaluation we did last year. As you can see, most of the jobs improved by 25 to 50%. But it's important to note that this evaluation was done over a year ago. So a lot of fixes have been made and performance has been improved a lot. But this made us very confident to continue this path to enable Gluten and Velox for more of our jobs. So what I'm sharing now is the performance we're seeing on ad hoc workloads. It's a comparison of real ad hoc traffic that we're seeing. Just have to keep in mind that we're only enabling Gluten and Velox for queries that have 0 fallbacks to Java Spark. So around 30% of our queries are currently compatible. This number is usually higher for ad hoc queries because UDF usage is not as common there. The first metric I'm showing is like elapsed query time. This is an important metric for our analysts because it measures how long it takes for them to get the data back that they need and directly relates to analytical velocity. As you can see, the orange line shows Gluten elapsed time. The median time we're seeing for our ad hoc workload around last month for around 2 weeks was 150 seconds, where the non-Gluten workloads that used just Java Spark were closer to 250 seconds most of the time. So we're very happy with that improvement because it really helps our users get their work done faster. But as I mentioned before, one of our main concerns on our clusters is memory usage. We are often bound by memory, so we wanted to see large gains in memory used when using Gluten and Velox. And this is what we're seeing around the same time frame. This is the median memory that is used on the executors. And you can see a very large drop where the memory used in Gluten is 2x reduced compared to Java Spark. This is really important for us to alleviate memory pressure on our clusters and allows us to right-size our executors and shrink them in size. This will make queries faster and also save us cost. Obviously, when integrating a new project into a big existing platform, there are like learnings and challenges. One thing that we are still actively investigating is we're seeing heap memory usage during broadcasts, even for fully offloaded queries. Also, in the past, there was an issue doing sort-based Caliborn shuffles due to some implementation issues. We worked with the team at IBM, and we are currently testing a fix for that. And this shows like the great collaboration in the community, and we're very happy about that. We also realized that we need to have better ways to collect fallbacks to Java Spark at scale to better drive our development direction. We need to know what are the most common fallbacks we're seeing so that we can tackle these first. This leads us to our future plans. Our overall future plan is obviously improve compatibility with queries. Currently, only fully offloaded queries are automatically enabled, and therefore we want to increase compatibility so that more and more queries are enabled with Velox by default, and we're seeing the performance savings. One big thing that's been mentioned before today many times is UDFs. We're also seeing the same issue that we would need to translate UDFs to C++, which is expensive and difficult in some cases, but it's something that we want to take on for our most important workloads. And then the other approach is, can we still run Java UDFs in a more performant way, as described in the talk just before me? A company-wide effort is to migrate important data sets to columnar formats like Iceberg. This will also give us performance improvements and Velox compatibility increases to formats like Iceberg. It will also help other query engines as well, but it's very helpful for our Gluten and Velox adoption. I mentioned the fallback check we're doing to Java Spark, and we're currently doing that on Livy, on like dedicated submission system. We want to move that fallback check into the Gluten plugin itself, where it performs a fallback check, and if there's a certain number of fallbacks detected, it could release the off-heap memory that we assigned to it and just run the query as a regular Java Spark query. We are making use of stage-level resource profiles, which is exciting work that's happening in open source. And we will continue to evaluate it for different use cases to optimize our resource usage. Also, I mentioned that some select teams are onboarding scheduled queries, and we want to have an automated way to do that on behalf of our customers. And the fallback check within Gluten is very important to onboard these scheduled jobs. As part of the Gluten roadmap is improved ARM support, and that's something that we also want to focus on this year to see if there are any cost savings that we could take advantage of. Last but not least, frequent benchmarking and rebases are very important for us. The project is moving fast, and that's why we created the sampling and testing framework, so we can validate changes against sampled production jobs easily and effectively. We wanted to say thank you to Binwei for all the support he's provided us for in the last year. And I also wanted to say thank you for every team member on the Big Data Query Platform team for their work that I had the pleasure of sharing with you today. Thank you. Feel free.
There you can use.
Can you elaborate on the shuffle service OOM issues? So we are seeing a lot, I mean, as compared to Vanilla Spark, we are seeing a lot of shuffle being done here in while using with Velox and Gluten.
So it wasn't specific about like the usage of shuffle service, but some queries there was high memory usage when using Caliborn shuffle service, and it was due to the implementation being not optimal. There's some fixes that are I think already merged in open source that we are testing, and that should alleviate the issue.
Hi. You mentioned zero fallback check is very important for your queries. Can you elaborate why? Like you may get like 50% benefit even if there are some fallbacks, right? Why is that not acceptable?
So the problem is that we don't know if we have a fallback, if the performance is good. We don't have like very advanced heuristics yet that tell us if like we could still see better performance even if we had some kind of fallbacks. So currently we have zero fallbacks because we will know we'll see much better result, and we won't see a regression in performance or memory usage. But that's definitely something we want to like explore further, if we can tolerate some number of fallbacks or certain kinds of fallbacks.
Thank you.
I was just curious, like you showed the performance improvement bar chart, right? And is there any like regression? And did you try to see if there's any reason?
I think I know what you're referring to. So this is ad hoc workloads, and that was on the weekends. We're seeing a lot less traffic on ad hoc workloads, so the data is a lot smaller. So there's more variability in what single queries can skew data a lot more, some jobs, as analysts usually don't submit as many queries on weekends.
Yeah, but for general, like when you integrate all this, there's no regression? Like in performance?
There's no regressions when we don't have any fallbacks.
I see. Thanks.
Thank you. All right. Okay, there you are. Thank you. Thanks, Felix. All right. So next up, we have Xian from One House, who's going to be talking about work being done with Hudi and Gluten. You can plug in. You don't want to mirror it, so just exit out of this. want to keep this here, right? Or you want to drag it? Is there a way for him to keep presenter view here and slides up there? No.
Yeah, I can view here.
Okay.
Just need to present this.
Yeah, so
on
just, I
screen.
think you just drag it, right?
Wait. Can I maximize it? Thank you. Okay. Good afternoon, everyone. Thank you for joining me today at VeloxCon. I'm Shiyan Xu, a founding team member at One House, where I focus on open source development. I've also had the privilege of serving as a PMC member of Apache Hudi project for the past 4 years. Today, I'm excited to share with you some latest development on integrating Hudi with Gluten and Velox, and how this integration is transforming data processing capabilities. Before diving into integration details, please let me quickly introduce Apache Hudi for those who might be new to it. Hudi is a transactional data lakehouse platform. At its core, Hudi defines an open table format and provides a transactional database layer that delivers powerful indexing capabilities, handles concurrent transactions, and enable change data capture. What makes Hudi particularly valuable in today's data ecosystem is how it integrates, how it bridges the gap between traditional data lakes and data warehouses. It offers flexibility of data lakes and also the ASIC guarantee of the data warehouses. Let's start with the progress of what we've made on Hudi and sealed copy on write tables. For those unfamiliar, copy on write or COW is one of the Hudi's table types, where each update creates new file versions, making reads super efficient, but with potential high write amplifications. Gluten support for Hudi COW table was successfully added last year. When querying Hudi COW tables, Hudi identifies the relevant columnar-based files through various indexing mechanisms and creates Hadoop FS relation in Spark. This relation is then processed by Gluten using Hudi's scan transformer. By using Velox as the backend for execution instead of native Spark, we've observed an overall 33% time reduction in TPCDS benchmarking. This translates to real cost savings and enhanced user experience in production environment. Now let's move on to the more complex case of Hudi merge on read table. MOR tables have unique challenges due to their hybrid storage structure. Unlike COW tables, MOR table buffer the record updates in role-based log files while maintaining base files in columnar format, similar to COW tables. In Hudi's storage layout, a base file together with its associated log files forms what we call a file slice. When query engine integrates with Hudi, they invoke Hudi APIs to merge those log files and retrieve the latest records. This means a file slice becomes the smallest unit of file scan. For Gluten integration, this architecture requires providing a custom file format that contains both columnar-based file information and associated log file information. When it comes to Velox execution, we need a specialized Velox Hudi data source connector that can process these file slices. More specifically, a connector split reader in Velox should be able to use Hudi APIs to read file slices effectively. This highlighted broader need for a cross ecosystem. For various engines to integrate smoothly with Hudi, we need a common standard API for reading file slices. So this brings me to one of our most exciting development, the Hudi RS project. Hudi RS is a native Rust implementation of Hudi, designed to expand ecosystem integrations and standardize APIs across different frameworks. At its foundation, Hudi RS has a Hudi core component that encapsulate the core models and the logic required to interact with Hudi tables. Building on top of this Rust core, we've developed Python API bindings to tap into the vast Python ecosystem, enabling integrations with frameworks like Ray Data and Daft. For Velox integration, we've recently added C++ APIs by leveraging the Rust C++ binding framework like CXX. With this multiple language approach, we're able to seamlessly integrate Hudi with diverse data processing engines while maintaining a consistent core implementation. The cornerstone of our integration strategy is the file group reader API, which provides a standardized interface for reading file slices. In Hudi, a file group is a logical grouping built on top of file slices, capturing records, versioning, and offering numerous advantages in indexing and managing file life cycles. So in Hudi Rust core, the file group reader is responsible for merging log files with base files and returning Apache Arrow's record batch. So luckily, Arrow provides a stable C interfaces, allowing us to pass a record batch from Rust to C++ by exporting raw pointers. C++ application using Arrow can import the record batch through the same C interface. This approach is also quite efficient due to the zero-copy data sharing within the process. This is supported through the C interface. So looking at the bigger picture, Hudi project is being actively developed on multiple fronts. The main Java implementation recently reached a significant milestone with 1.0 release, introducing powerful new features that enhance Hudi's capability as a data lake house platform. Meanwhile, the Hudi RS project created just last year with the goal of expanding ecosystem integration and standardizing APIs. Hudi RS has evolved quickly with 3 releases in the past few months. We will also have C++ API in the upcoming 0.4 release. As we continue this journey, community involvement becomes increasingly important. I'd like to invite you all to engage with the Hudi community. We are available on various platforms like GitHub, Slack, LinkedIn, and YouTube. For Chinese users, feel free to follow our WeChat account to stay up to date with the latest development. Thank you.
Mic. I don't know where that went. Okay.
Yeah, the question was what's the scale of the benchmarking previously? It is 1 TB for TPA CDS, 1 TB. Yeah. Thank you.
All right. Where's Amit? There he is. So next up, I'm happy to introduce Amit from Meta, who is going to be talking about the latest on Presto C++ at Meta. I don't know if the clicker works with the ThinkPad, but you can try. Oh, thanks. Does somebody have the other mic in the audience? Oh, okay. I'll go grab it.
Okay, so today we'll talk about the Presto C++, the next decade in SQL processing. I'm Amit. I'm working as a software engineer at Meta. Okay. So the main topics we are going to cover, only few topics: the introduction, the Meta warehouse, how big and how large it is, some historical context about Presto, and mainly how we have built Presto C++ worker and enter Presto with new Velox, and how we are running it, and where we are, and what are the next items that we have in mind. So Meta Warehouse is one of the largest data warehouse in the world. We have Presto, Spark, Sapphire, which is Presto and Spark running together, different kind of storage engines, metadata storage, permission service, type resolution service, many file formats, and very large scale distributed storage systems to query. And Presto servers serves almost millions of query per day among all these systems. So some brief historical context. At Meta, then Facebook, the Presto 2015 to 2017, after its starting Presto, it was doing the Hive migration and mainly used for external analytics. Sorry. Okay, we get here. And in 2018 to 2019, we are mainly worked on interactive and batch. The project was donated to Linux Foundation. And 2020, 2021, major highlights was doing elastic compute, caching infrastructure. And beyond 2022, we started looking in efficiency, native execution, and very fast latency sensitive workload. So historically, the Presto ran as a coordinator worker model. So we have one cluster with one coordinator and many workers. We also have multi-coordinators, but the multi-coordinator is phasing out at this point. We have many clusters, and Presto is available globally for all engineers and data scientists that work in Meta. We have a layer of routing Presto gateway that allows us to intelligently send traffic to Presto clusters, do load balancing, and do many tricks that allows us to kind of efficiently navigate the traffic. And everything is in Java. From gateway to coordinator to worker, everything is written in Java. It's in open source, built with Maven and everything. And we used to have a major operational cost because of how Meta infra is laid out, because 95% of Meta infrastructure is in C++. And Presto being on Java stack does not play well with what we had to operate on. At the same time, Presto is a very mature product. It has decade worth of usage, decade worth of expectations. Even something like if you have a incorrect result, if it's consistent, it becomes the standard in the company to keep running with those kind of incorrect results, because as long as it's consistent, it's treated as correct. And we have faced over the years in last decade many problems to run JVM at scale. For a few machines, for small workload, JVM might be okay, but for running thousands of machines in parallel, doing very high performance computing, we continuously faced problems with garbage collection and JVM pause and so on. So journey to Presto C++, why? So definitely, it was time to modernize Presto. So it became dated, and we want to make it a new Presto powered by Velox. And the first feature we keep in mind among everything else, it needs to be fast, and it needs to be reliable for us to maintain at many, many machines, probably for the next few decades. And the cost of running it needs to be very low. And we should be able to service it, triage it, or fix it quickly with the new infra. And of course, whenever we do this kind of migration for a 10 years old system, it's a very complex procedure. But we need to make a migration that is really fast, that could migrate things in place, no extra capacity, and find a way to ensure that the migration does not break our existing customers, which there is a huge usage of Presto. People are using it for reporting, for all sorts of usage at Meta. And at the same time, we need to keep the architecture very simple, because at scale, only the simple things can survive. And for next decades to come, we need to open new opportunities with Presto. For that, some of these we'll touch today. And another most important thing is very tight integration with Meta infrastructure, which going to C++ give us all benefits that Meta infrastructure gives for all of its services. For example, code landing, release, verification, debugging, triaging, code dump, anything that we get from the infra, we want to use it in Presto, and we do not want to do anything custom. Okay, so we have been giving talks about Presto C++ for some time. So from last PrestoCon, this was the status. It was around last November, and we were running some of the low priority batch queries, which and some of the pre-verified high priority queries. And we did not have any general release for this product, because we had to verify the query before to run them. Verify means verify for correctness if it's matching with Java stack. And we did not have any interactive deployment. We did not have global availability. And we had a lot of routing imbalance. Like, how do we know on fly if the query can run in C++, in Velox, or in the traditional infra? This is very important for us because we are doing an in-place migration, so we need to have a very good way to control this routing. So at this point, the state of the union where we are. So we are able to make Presto C++ general available. And any query, we can say that if the query has a valid Velox plan, it can run in Presto C++ with correct result. The result might not match for between Java and C++ stack. That we'll touch a little bit, but the result will be correct. We have migrated almost 70% of our batch traffic and roughly 20% of our interactive traffic. And we have deleted the large batch mode, which was a traditional way to scale large pipelines to write in intermediate tables. We were able to delete that entire stack of queries and the code and we could run them in Presto C++ without anything additional added in the engine. We have also started taking more aggressive goals, like killing another infra, Presto on Spark. which is internally called Sapphire, which we have migrated 30% of the workload in Prestissimo. And this is due to Velox that we haven't even added any capacity to do these migrations. These give us enough bandwidth to run more queries because of the Presto C++ deployment, and all that work have been done in Velox. We have been able to migrate many company critical use cases in Presto C++ that was otherwise could not be run in Presto Java or even any other stack. And we have also been able to define what is the pricing capacity model in terms of dollar value. Kind of in general, it's 50% less expensive in terms of dollar if you want to run the query in this new platform. Okay, so generally we have 2 to 4 times performance improvement. In extreme cases, it can be 20x better CPU and memory performance. We have reached a position where the engine can return correct result or fail with unsupported error. But at the same time, since it's taking workload from different engines, we have also started seeing out-of-memory problems, but still under manageable, but something we are working very hard to keep it under control. So at this point, we have seen like 20 in every region, the out-of-memory problem that can cause the server to die. It is still very resilient. The ohm numbers are lower than Java and very high success rate. And our North Star here is to run the queries slow if in memory pressure with spilling, but be able to handle gracefully the container ohms. And we also have seen, we are seeing almost 10 sec faults, even though that is rare considering the scale that we are running, but we are aggressively tracking it down, and we have to make it almost zero. For Presto and Spark stack, we have migrated almost 40% queries by count, 20% by capacity to Presto C++. We have been doing and will continue to do the memory management hardening in Velox to make sure we really account for usable memory and use all sorts of techniques to make to not go out of memory. And Presto and Spark, a traditional Spark workload, they run like an hour or 2 hours, but in Prestissimo, they are really fast. They are almost 7 to 10 times runtime improvements because of just how Presto works and how efficient we have made Velox. So we are making a new term that we are calling in the company is fast batch, which is even in the batch world, if the queries takes few minutes to hours, we will be able to run in Presto. So for general availability, verification is a very important topic, which I think is a very big topic. So we'll try to touch quite a bit on this verification area. How we make Velox to run in such a wide scale of queries without correctness issue or with minimum correctness issue, and when do we decide what. So for general availability, we know the performance that we always talk about 2 times, 3 times, 4 times, 20 times for price, that is excellent. But for us, it's not a few queries. We need to run warehouse worth of queries. And we need to do migration. We need to make sure the new queries are not only fast, they are also correct. So we need to have a fast car, but also we need seat belts. So the strategy that we took, and the strategies are evolving day by day, month by month, due to how the workloads we are trying to release. At the very beginning, like beginning of 2024, we had some sort of pre-verified queries. So for each Prestissimo release, Presto C++ release, we used to verify the queries beforehand. And verify means we used to say that, okay, if this set of queries, maybe we have, say, 100 queries, maybe 2 of the queries can match with Java stack, so we can release them for this particular build. Definitely, this process is good to start, but this will not scale and will not have enough capacity to verify everything. It's way too many. We'll need to double the warehouse to do that. At that point, we moved into loosely pre-verified queries. So that means once we verify something, it stays verified, given that we do not introduce any regression in Velox stack. And we'll talk about how we did that. And this also somewhat scale, but still expensive to maintain, because we need to keep a kind of database for what are the verified queries. And there are many shapes, sizes, sources. It does not work for all of them. But what we wanted to go is to some kind of blocking list. So for example, can we in Velox identify these functions, these tables, these text, or this combination of items are not correct, and everything else is good. So because that way we could block some functions, and we could, not just functions, many things, but we could generally run all other queries and don't need to maintain a baggage of verified queries. But this is a very high risk job, because at that point we are practically allowing anything to run, and that needs to be correct, not just performant, it needs to be correct. So in the verification spectrum, so the main problem here is we have millions of queries, many query shapes. There is deterministic query, there is non-deterministic queries. And Presto is built, as I keep saying, decade worth of fixes. And Velox is just built from scratch. We just started working on 2-3 years. It doesn't have that industry experience. There are many differences between Java stack and C++ stack in terms of behavior. The library is different, the eval is different, floating point, regular expression, JSON, string conversion, you name it, there are differences. And Velox is, when Presto C++ stack is under very active development. There are a lot of change internal, there are a lot of change from outside to continuously add new stuff. So among all these, we need to have a fast verification procedure so that we could verify very quickly, and we also need to do every day with almost 1 day worth of changes. So we keep looking for solutions. So there are many items we did, but few of them we'll talk today. We wanted to look for cheaper verification, and we had this idea in Velox to do further. We have invested on that. We have expanded further to make custom input generators, make it compare with Presto eval. And this is our ground layer of testing, which makes sure that the components are good. They're very good to tackle overflow, underflow. If Presto Java side returns exception, in this side returns null, nan, infinity, all sorts of corner case boundaries are kind of flushed out with this layer. And the next layer, we do this classic Presto verification. But the verification requires a golden version and a new version. And then we need 2 sets of clusters. That will not work either, because we need to have capacity. So we started changing the verifier in many ways. We started reusing the production tables in the shadow runs, so that if a query that we want to verify already ran in production, we do not run it again. We just use their output and run in the new side, and we could verify 10x more queries. This made our verification very fast, and we also added a lot of change in verifier, like validating string as double so that we can do the checksums deterministically. We have made many rewrites so that the non-deterministic query becomes a deterministic query, and then we can do the checksum and verify. We also had, over the years, we have built many query banks. This is something we use to release Presto. So we also made sure that these query banks, these pre-verified query banks over synthetic data that works with Presto Java need to work in Presto C++. So this was another layer of stamp that, okay, this stack is getting ready. But even after all these, we could make 50% traffic, say, deterministic, but there is half of them are non-deterministic, and there are many ways non-determinism can come in. And we need to find a way to continue verification. So we continuously fixed Velox and Presto Java so that they keep matching together. And we also are very fast to decide what we can tolerate in terms of mismatch, because not all matches can be handled. And we have improved the triaging process so that our verifier can itself do triage, telling us, okay, this one has a mismatch, but this is due to this kind of reason. And then even after all this, we have manual triaging for a few months to kind of, as Presto and Velox team triage together to ensure that the stack is getting ready. And whenever we verify, the verification results give us a very strong insight which functions or which part of Velox we can release without risk, and which part we still don't know, which part is under development, which part needs work. So we kind of connected this result with our routing infrastructure so that we could only send the pre-verified kind of allow list functions to the Prestissimo cluster. At the same time, this cluster needs to take a significant chunk of traffic. Remember, we do not have any extra capacity to run this. So we try to make sure not to have a very wide list that include almost all the functions that Presto offer. So we connected the routing with verification result. We have integrated API v2 and Velox plan checker with some handwritten rules to dynamically find if the query on the runtime, if the query can run in Velox stack or cannot run in Velox stack. So the query that we can run in Velox stack are become native eligible that can bounce back and forth between both systems. But there, for performance reasons, there are a lot of queries that we had to pin to the C++ stack so that they get guaranteed performance. The verification and routing, so basically the native eligible, after all these things, we have three sets of functions. The eligible ones can run in both infra. The native only can run in Presto C++ side, and the Java only means some of the queries that cannot run or have correctness problem, or customer has expectation on the old result, they need time to migrate, we can park them in Java. And we also have configuration to influence this plan validation, so that on the fly we could say enable functions, enable some source, enable or disable something to help us to release the product. So for some of the major non-deterministic sources of verification, we'll highlight here, but there are many. There is this lower upper that has the Unicode difference, because the JDK we run with JDK 8 inside Meta that has Unicode 6.2, and in Velox runs, and Velox and all other Meta infrastructure runs with Unicode 11 plus. So there is a lot of character mismatches. Regular expression, which is we use RE2, which is a very fast regular expression library, but it also has quite a few differences with Ioni, which is forked in 2019 in Presto Java's repo, and there are syntaxes that are not supported in RE2, and there are many cases there are result mismatch also. And there is the JSON functions, like SIMD JSON versus Java side, we have JSONs. They have the path difference. There are supported paths where the results match, but there are many. There are not many. There are a few unsupported paths, like when we put expression in the path. This syntax we don't have in Velox, and we probably likely will not add also. And we have to ensure that our huge customer base can operate on this moving infra. So we had very intelligent retry mechanism, some of them in place without failing the job, some of them failing the job and trying in Java. to keep the existing customer expectation and service level agreement that we have set up, which is in a moving infra like this, is very, very tricky to maintain. And even outside of this, there are way too many corner cases between these two infra, but we try to make sure the results stays consistent and pin traffic here and there to kind of achieve the consistency and don't try to fix or overfit something in Velox that we feel is not a right decision. And this is a great learning experience of how the database eval works. Doing it in this granular level and getting the opportunities is something I'm really thankful of, because we often work in the higher layer of systems, but releasing Velox to so many customers, so many users is something, some experience. So this is the status of batch queries. The top line, the pink line, is the query that we are eligible to run. And the blue line is the queries we are running. So we almost crossed the 75% mark in our batch world. And in the interactive side, we just started the migration this year. Interactive is giving us way more challenges, even after all these fixes in batch, and we are almost around 20% in that journey. So the native only, so at the same time, it is visible to customers, and we know this is the new stack. There are a lot of ways customers can opt in to run only in C++, and that's what a lot of customer wants. And at the same time, we in Java stack does not have many evolving requirements. For example, we have this experimentation platform use case that we are running in completely native platform. We recently been successfully able to run ads delivery experimentation platform in our generalized Presto C++ offerings, and which would have not been possible to run with the timeline and SLO they have without Presto C++ and Velox's work. And during this in this kind of work, it's not only just running some query. We have to deep dive in Presto and Velox stack, see where some inefficiency can happen. And we fix many things, like in this case, one example of the row-wise encoding for very wide tables, which these ads platform are using. But one of the important part of making Presto C++ and Velox to run is we have so many changes and so many fixes, so many new features, connectors, and we have to ship it very quickly with the confidence. If we ship once in a month or once in even every 2 weeks, we'll fall behind. Regardless of how many systems we are releasing, we need to release quick. So we have decided to release every week, and we have made the verification faster, and we have made all the knobs to turn on and off something in the fly to influence the routing. And so far, we have only found 2 major correctness issues that we could not catch before, and these are very tricky cases. One of them was merging the HLL data structure between Velox and Java stack. These are not really correctness, but compatibility, because in Velox, we used to use XXS hash, and in Java, we have murmur hash for approximate data structure. So Presto allows you to persist the HLL in disk. So if we hash with one and read with another one, it does not. It has a wide error margin. And we also fix the row container extract values with nulls. That is an issue it found during some kind of window spilling. And there are many contributions. I keep poking around in OSS to ask help us to fix bugs that we find, like one of them, like TPC data generation, not a bug, but it didn't match with what we had in Java. UID binary casting, and there are more fixes that we got. We are thankful of that we got in Velox from outside. And we also made sure that we continue the general utilization across the clusters so that we just don't run any few queries. We run 70, 80%, which is the majority of the infra running in Presto C++, making it the new standard for the next decade. So the infra today, we have only 30% of hardware for Java and everything else in C++. We have a heavy routing logic that we have discussed a little bit. And we also see occasional slowness in runtime when the server is under heavy use. We have some sort of unsupported features in Velox that we continuously improve, like the Lambda support for variable arguments. We have the system, since it's running both of the infra, it getting a little bit complicated for our customers to add new functions because now they need to add in Java, need to add in C++. The pricing model in a heterogeneous infra is hard to define. So, and the migration completion speed is something we are actively monitoring. We're trying to complete it very quickly. So the pricing model today, I'll go quickly. Customers can buy units to run queries, and the unit is usually the maximum of the total CPU time and total cumulative memory. And we have a way to convert these to units, and these units a customer can buy, and they can run that many units of query. At the same time, to ensure that Presto C++ is efficient, we need to make sure this unit cost for customer going down, which will then influence us, the system or the capacity management, to reduce the machineries, and which will reduce the hardware footprint. So the whole cycle needs to work for us to demonstrate that it is actually 50% cheaper. So we are on track to demonstrate this. And this is where Velox's power comes from. The economy of scale, when we could run many, many things cheaper, is worth. If it's a few queries, few machines, it's probably not that worth taking all this. So what is next? So the immediate next for us is to ensure the complete deprecation is done, because it is very tricky to maintain both infra. We have to release, verify. There is a problem with running queries in one stack, not running with another stack. And then where we want to go, we want to run milliseconds to hour-long queries in the same Presto C++ deployment, making it ultra fast. We want to expose analytics for machine learning training tables, which are wide, both for interactive and batch. We want to make the machine learning pipelines faster, maybe hourly. We call it fast batch. We have different file formats that have been released through Prestissimo, Presto C++ and Velox integration, like Nimble format, Metalake. We want to support larger maps, wide tables, feature reordering, and we have a few siloed deployment for customers that we also could not merge in our general offering due to performance problems. But now, due to Presto C++ and Velox, we could do that. So that's probably will go for next year. Okay, any questions? Yeah.
So we had actually a major problem with the result mismatch, and the question was that whose fault it is. So what did you do regarding that? It is C++ versus Java. Whose fault is it?
So, for example, I gave one example at the beginning. Like this one. So,
that's all right.
Can I go back? So it's not anyone's fault. We try to find which one is correct, and then try to match both. Let me go back. Okay, this one. So basically, in this case, we found problem in Java stack where it was not tackling the some escape character in regular expression parsing.
But you don't know what the result of the query is. So you give it to this guy, that guy. We tested a lot of that, by the way, at IBM.
Yeah.
So what we did was that we brought in another database. We brought in our DB2 and loaded the exact the same. We used a lot of TPCDS. And then we started correcting the
But TPCD is few queries, right?
Huh?
That's like only few queries.
The results. And
Yeah.
we also wrote our own queries.
Yeah.
Remember, so the thing was that we voted. And most of the cases, actually, we fixed Velox, and then
Yeah.
we won with Velox, most of the cases, because we were not fixing the Java part.
Yeah.
Velox at the end was very good.
Yeah.
But at Java, it's amazing that what wrong results we're creating comparing with our DB2 product.
Yeah.
It was amazing. You know, it was no complaint and just give me bullshit results.
Yeah, that is true, like the Unicode and stuff. But the important part for us was we have a existing customer base. So if suddenly we change result for them and it bounce back and forth.
They don't know. The data changes, the queries change. They don't know.
So that we can talk about, but
these are big systems. They don't know.
Okay. Any other questions? Oh, yeah.
Yes, hi, thanks. My question is a little bit, I would say out of the box, because I listened to multiple presentations and everybody's talking about a code. So if we talk at Presto, what is the impact of poor data quality on all the query execution speed? It's like, it's an elephant in the room and it looks like we're totally ignoring that. I wondered if you can comment on that.
So, sorry, I didn't get, is the...
My question is, when you look at Presto query and how execution speed, performance is impacted by the actual data that is being queried. If the data is garbage, you can optimize till tomorrow, you're still gonna get slow execution speed or bad execution. So my question is, why data is not mentioned anywhere in this presentation or any other presentation when I'm talking about data quality?
So you are saying that, if I understand correctly, the table formats and partitions, these are not well written, or?
If something's wrong in the data, and you optimize the query.
Oh, so what we do, we have, so this is not in open source, but internally, we have a way to tell our customers that this table, this code is taking time because of this kind of reasons. So we surface some of these things about the data quality to the customers. We have something called, I don't know if Dr. Presto, this thing is not outside, but we have some insights on the tables. Even there is another data quality thing that if you look at like a ultra fast latency, say 2 seconds, 3 seconds, even millisecond, if you have some very small files, it is a problem. So we have been working on compacting it. A lot of storage related optimizations is also going on. But for Presto side, generally, all the talks are on compute. So they try to not look in data, but again, you are right. If the data is poorly formatted, doesn't matter what you optimize. Yeah.
Okay. Thanks, Amit. All right, next I'm going to introduce Krishna from Meta up here, who's going to be talking about PyVelox. Woo. You got a woo. Use this one. Yeah. It's kind of, you can do it. It's a little bit of a hacky thing, though. Oh, wait, is it there? They have it? Do they already have it?
Yeah, but I was going to share, like,
They can switch between the screens.
Oh, they can?
Yeah.
Okay, so I'll just do this at the end.
Sure. Yeah.
This goes forward.
Yeah, sure.
Hello. Yeah. So hi, everybody. My name is Krishna, and I'll be talking about PyVelox, which are our Python bindings for Velox. How many of you here have actually built Velox from scratch on your machines? All right, that's great. How many of you have ran into some build issue while doing that? Okay, that's not so great. So PyVelox is like to help you folks explore Velox and play with Velox without having to face the frustrations of building in C++ and dealing with all the pain that comes with anything C++ related. So oh, it's not. It's not working. Oh, there we go. All right. So why? So PyVelox has a simple and intuitive API. It uses Python bindings. It's really easy. Anybody who's been in the Python world knows how things work. Very straightforward. You don't have to deal with types. You don't have to think too hard. It just flows naturally. And any problems you deal with, you'll deal with at runtime, right? So the audience we're targeting with this is like database and data processing systems engineers, like folks who want to integrate Velox into their systems, be it Flink or Hudi or something internal, and you want to play around with or explore Velox or try things out before you use it in some large-scale production system. Pedro talked about this in the morning, and Konstantinos also talked about we are actually using PyVelox in Meta, in prod, in some capacity. So it's not like this is just for play. And you can install PyVelox just like any other package. And the great thing about this is it's available right now. You can just do pip install PyVelox, and you will get a pre-built PyVelox package. Out of the box, you get array integration, you get the full power of Velox, and a bunch of other nice things. And just to showcase that to you, we'll be creating a simple plan right now, and we'll be running it. Okay, so let's take a very simple and practical use case. This is TPCH query 1, right? I've taken the simplest possible case. And we'll write a simplified plan for query 1. And like I said, simplified. It's single-threaded. It's one file, and doesn't do any partial aggregation or remote exchange, everything. This is just a simple plan, the kind you read in a tutorial or on a lightning talk, and the hard stuff is left to the reader as an exercise. Right, so here you have a simple query that just reads from one table, does some aggregations on it, some projections, some aggregations on it, a filter, and it does a group by and order by. All right, so like I said, we will have a very simple plan. It's single-threaded. We're going to do a table scan on it, project and filter. So in this case, I just kept it even more simple and done a project, and then we'll do an aggregation, and then we will write out the result to a table, or in this case, I'll just print it out so you can, view it. So let's look at the query first. So to start off with, what are the columns that we need to read from the table? So we identify the columns that we're interested in: return flag, line status, quantity, some of these other columns, right? And we get the types that are associated with them. And then we just create this row type. Now, row is the containing data structure type that contains the mapping between the name and the type associated. And you can see we use like varchar, double states, etc. The next thing is what's the file we are going to use. So in this case, split. I pre-generated this TPCH scale 1 line item table and wrote it out as Parquet. It's pretty straightforward. PyVelox also contains the TPCH connector generator, so you can use that to generate any scale factor, the files you want interested, so you can play around with that too. At some point, maybe later, I'll put a full tutorial or something on this, so you can like write the data out and play, create plans. So in this case, I have a pre-generated Parquet data, scale factor 1. The supported file formats, as I talked about, Dwarf, Parquet, Nimble, all of these are supported. So now let's try and build a plan. So we import from plan builder, the plan builder type, and then we create this plan builder. It's used to create the actual DAG of plans that you need to run. In this case, let's just start off with table scan, and we tell, we pass the schema that we want, and we pass it the file that we want to read. So we generate the splits on that. And then we just ask for the plan node, and we get the plan node back. The plan node itself is just a plan. It doesn't run anything, right? So the next thing we do is, to run the generated plan, we need something called a local runner, which takes the plan, and then we execute it using the execute command. And you can see like a picture up above of me running this in local Jupyter notebook. So it runs, executes it, you can see the output. And at the end, you can also print stats related to the plan, how it performed and stuff like that. So really simple, basic stuff, but good enough for you to play with, to start off with. And next thing we have is, so that's the really basic stuff. And now we need to do the projection. So to get that working, it's as simple as, again, we create the plan, we do the table scan. But this time, as you can see highlighted in the green, we call project, and we pass in the expressions that we're interested in computing. So it will compute these expressions, and we'll need to do this before aggregation. And yeah, ideally, if you have any, if you have real plan, you will do partial aggregation along with the table scan. But like I said, this is like a very simple plan, and it's a lightning talk, and I don't have that much time. All right, so the next thing we do is aggregation and group by. So after you have done the projection, on the results of that, you can call aggregate. You pass the grouping keys and also the aggregations on them. So in this case, the sums and the averages and the counts, right? So it's pretty straightforward here. Okay, and the final plan is if you squint carefully enough, you can look at the final plan. So you just create the plan, you call table scan, you do a project, and then you do aggregate on it, you call order by, you have the local runner run it, and you can actually see it output all the results and work out. So this is a really nice tool for you to like play around with, create plans, explore and experiment with what works, and without having to go deep into the weeds of writing C++ code and like figuring things out. Then big thanks for all of this to Pedro, who added like most of the plan builder Python bindings, and Jacob for publishing all this to PyPy, and Sri and the folks at Vote on Data for all the coordination and help we got here. And so it's pretty straightforward. You can just go and pip install PyVelox, and we also have the documentation published on all the bindings and all the types and all of that, which is available on the Velox documentation website. And any questions?
I know Velox isn't a SQL parser, but it'd be sure nice to be able to put SQL in PyVelox. Is there any hope for that?
So we use DuckDB SQL parser internally in Plan Builder. Ideally, we don't want to use it, but for now, we are using that. So it is somewhat Presto compatible, not fully Presto compatible. But at the moment, we have some plans, but I'm not sure how fully materialized they are. So I'll leave that the actual answer to Pedro, and when we will get to doing something like that.
No, just saying that I think the idea is that you want to define things on a physical level. So it's mostly used for debugging when like people developing new engines. So it's not meant to be as simple to use as other data tools. I think usually the problem is if you define things using SQL, then you might lose something on this translation process, right? So I think we want that thing to be as specific as you can. So I think that's why you can define the exact types, the exact splits and everything. So I think the idea is having something that you have full control because you might need when you're debugging things, and not something that is as convenient to users. I think to your point, those are things that we can build on top of that, but I think that's not the purpose of PyVelox. It could be something built on top of PyVelox.
Also, I want to point out this is not like a data frame library. Like that's not our intention. There are many data frame libraries. In fact, we support conversion from Arrow to Velox and vice versa. So yeah.
Okay.
Ooh. All right.
Thank you.
Thank you.
All right, we're actually on time, which is very impressive. We have a short break now, so feel free to hang out, and then we'll be back here at 3:30.
Huh? Oh, you have to say something. What did you do?
Wait, what's that? What did you All right. We'll give it one more minute. If somebody can tell everybody out there to come in, that would be awesome. Come in.
The what? The key? There's the one that works, right? Huh?
All right, we're going to get started as people filter in. All right, we're in the home stretch, my friends. I'm really excited to introduce Remus Lazar as our next speaker. He is our VP at IBM of Software Development, and he's going to be talking today about the work we're doing on all of these open data engines at IBM. Take it away.
All right. It's great to see everybody. It's my second time speaking at VeloxCon. So last year we discussed about the importance of SQL. I'm going to reiterate the same phrase. I'm going to keep saying it. SQL is king. I don't know if it's my age or what's going on, but it takes me 2 hours. I have to wake up 2 hours earlier to use pandas versus SQL. It's maybe just me, but the importance of that language and our ability to execute it against our corpus of data remains crucial. And I have to say I'm very excited about where we are as an industry in terms of data and data processing. And it's for the first time when I see things coming together in a completely different shape than we used to do it in the past, right? We used to have these proprietary formats. We used to have a lot of things in created and closed ecosystem. But why do people store data? Why do you store data? You store data for downstream processing, analysis, and things around that nature. Keep building closed ecosystems. Keep building enclosed data formats. Ain't going to help anybody. We are at the time when we have the capacity and the power to consume it at large scales. Take a look at generative AI, take a look at other stuff, right? So based on that, about 3 years ago, when we started to build our data model factory, we called it data model factory. We based it on Presto and Iceberg. Those were the two things that we built internally in order to train models at large scale inside IBM. And eventually, after some evolutions and conversations, we ended up building an offering. And this offering is based on multi-engines and open source formats. We use Presto for interactive workloads, and we use Spark for batch, ETL, ELT. Why is that? We believe that engines themselves have, architectural designs and approaches to problems that we need to exploit. And yes, it introduces operational complexity. Having multi-engines is complicated. But fronting that and making sure you drive on top of open formats, unified layers of governance and metadata, as well as workload managers, right off the bat will get you where you want. And moreover, we are investing heavily in additional elements around Presto and Spark, which includes Velox, which includes Gluten, which includes all other engines that we need to bring in from the price performance perspective. But these architectures, what you guys see today, is what will define the way the lakehouses of the future will look like. What does it mean per se, if you look at it in a very simplistic way? And we had this conversation many, many times. Your typical processing in any enterprise right now implies transformations and replications and moving data from point A to point B and keep going, right? What happens right now, and you'll see much more often from now on, is the fact that relying on open formats, using the appropriate engine on top of it, without moving data, without having to recreate your ELT and ETL pipelines, will become the standard. How do we get there is not going to be an easy way, right? But we are at the beginning of that journey. I see a lot of good practices. Meta is doing a lot of good work in that domain. They are actually using a very similar architecture internally. They have a multi-engine for everything they use. And we start to see that more and more on any enterprise. They like that choice of changing engines to reduce their cost or actually increase their operational efficiency. We also have characteristics around multi-cloud deployments. What does that mean? A lot of our customers, and I have a vested interest to make money, so definitely I will accommodate them. They do prefer certain things to run equally on-prem, on cloud, this cloud, the other cloud. So I'm not going to be very prescriptive around my deployment tab. So it's one of our characteristics, and I think we are the only vendor that currently brings a multi-cloud approach with on-prem distributions for Presto, Velox, and Spark together. On top of it, we need to focus on, as I said, security right off the bat, and your ability to control your workloads. It's a complex environment. It's a little bit more complex than single engines, like Spark only, like Snowflake only. It's a little bit more complex, but it has immense benefits when it comes down to execution. And obviously, we focus on AI ready. I didn't just put that there. Typically, I do, but in this particular case, I strongly believe that making data ready for AI, and I'm not talking about only structured data, I'm talking about unstructured and unstructured processing, it will be the next frontier of the workloads that we need to win. There is no in between. We can't avoid that conversation. It happens today. It happens in vectors only. I don't think vectors are sufficient. I think it's a combination of things that will eventually make AI successful with data. Will it change? Oh, it keeps highlighting the multi-engine strategy. So at the core of everything we do is Velox. Why Velox? Well, it gives us the ability to go back to a C-level execution. It gives us price performance. And I'm going to talk a little bit about the vested interest of me making money versus the vested interest of me building technology. There are two separate trajectories, and I'm going to try to express one versus the other. Standing in front of your customers, and I think it's an important characteristic, even if you don't think it in those terms, and I'm not going to hijack the open source aspect of it, but sitting in front of your customer, no matter who your customer is, could be your boss or could be somebody in line of business that is consuming your products, their ability to execute reliably and with reduced cost, it's of utmost importance today. The sizes of data will continue to increase, and there is nothing you can do about that. That's an equation you cannot change. But what you can do is actually drive the right execution towards that data sets. And for us, we strongly believe when we have proof internally on TPCDS at 100 terabytes, that it's actually the best execution engine right now on the market, period. And it's only at the beginning. In addition to it, obviously, Gluten plays an important role for ecosystem, primarily from the Spark perspective. The same performance that we can bring in Presto through Velox, we can gain inside Spark through Gluten. And this is not a joke. We have, and Binwei earlier showed slides on the performance analysis. And it's our best chance as an industry to go against Databricks Photon. Apologies for any Databricks employees, but that's a reality. We need to go on open source. We have to. We have to contribute and we have to work together. That's not how we make money. Having a proprietary engine trying to squeeze the last ounce of performance there, it makes sense for a while, but we need to actually work together. I don't think it's a one company job to be able to do that. And what are we focusing on, right? Presto C++. We focus on these three elements. Presto C++ is Presto with Velox. Definitely number two is one of the crucial aspects on where we need to go. And I'm saying this will be upon us, whether you work for your CDO and your customer internal, whether you are selling to your customers, whether you are doing things in general, execution at speed, given the amount of data we will start generating and we will start seeing, remains crucial. Deeper format support, absolutely, it's imperative in order to retain the ability to not move data. Again, that's a no-no right now in the industry, or at least not yet, but it will be there. And tighter architecture is making sure that it works as it should be and as designed together with surrounding things around it. Iceberg integration. Why Iceberg? I'm not going to take a stab again against Databricks, but I will. Delta Lake is not really open. That's it. It's as simple as that. I don't have any other comments. It's a beautiful format. We love it. We support it. We all have to. It's not really open source. I don't know how else to say it. And therefore, Iceberg. We are heavy behind it, and we need to bring it in. We need to bring it in Presto. We need to make sure that it works, so we all have a chance. Not some of us have a chance. We need to focus on coordinator performance. We need to focus on optimizations and query optimizations. As I said, SQL is king. I strongly believe that remains one of the most used, and it will remain one of the most used interactive ways to deal with your data. And I know pandas are good, and I'm not going to say anything blasphemous here, but in general, 90% of the usage will continue to be SQL. And another important thing, there were some sins of the past with forks and other stuff that I don't want to bring up again. I just did, but just saying. We need to bring federation inside Presto to the point of where it becomes the only engine when it comes down to interactive execution and federation. And we are doing heavily into that domain. What do we do in Apache Gluten? This is C acceleration for Spark. And that's it. I don't have to say anything else. Like, we need to use Velox to accelerate Spark similarly with how we do Presto. And all of you are welcome to contribute and actually start to learn and understand, but we are doing it. We are doing it in open source. Gluten is an Apache project. And we are accelerating Spark. Lots of work to do. Of course, we need to support Delta Lake formats. But not only that, Iceberg and Hudi and other are very important characteristics on how are we going to make this useful. And the rest are clear, like PySpark implementation, ingest optimizations, acceleration, and GPUs. And that is another characteristic. We will end up, when everything, all this boring stuff about formats and stuff around that nature goes away, we will end up into another era of acceleration. And Velox Wave gives us a nice, good way. NVIDIA is playing a significant role between Meta, IBM, and NVIDIA, building GPU acceleration for Velox, which will benefit both Presto and Spark. There are others that will join, AMD, NeuralBlade. Kudos to all of you by joining this. It's important. I think the benefits that we are bringing into AI can equally apply to data. We have memory bandwidth problem, we have that type of problems, but we are working through it. And I think it's one of the next frontiers that we will tackle as long as we will continue to retain a way of executing with the community around Velox, Velox Wave, formats, and open source without thinking about all the financial benefits that we'll eventually get. And probably you look at me as being one of the most likely offenders in the room. I will tell you that I have zero interest in just making money. I have a vested interest for the industry to move forward. And I think it's important that we come together. By the way, congratulations for the VeloxCon. It's probably twice the size of what was last year, and I hope next year will be 4 times the size of what is this year. So I think it's amazing. I'm not going to brag about these numbers from Binway. He already did. And I'm going to end up with what are we focusing on Velox? It's our shared engines for everything we do. End of conversation. It's our future as a company internally, as well as this is where we will drive the industry for everything that remains out of IBM Might. We will push in that direction. And these are the main things that we are focusing on. Formats and file system support, SQL and function coverage, performance, and we are doing significant amount of work in research to gain optimizations and exchange optimization and GPU accelerations and things around that nature. I'm going to end up with this. We are all in. We as IBM, we are all in open source. We believe in it. We work with it. We are not only leeching out of it, we are also contributing back. And I think it's good to see us coming together, defining the future of lakehouses, defining the future of technology, and I really hope that Databricks will join much closer with Iceberg rather than Delta Lake. I'm really waiting for that. They are one of the strongest forces in the industry today, and we need them close. So is Snowflake, which they bet in those formats. And I think a lot more people can contribute to Velox. It's one of the coolest engines that we had in recent history. So enjoy the conference, and thank you for listening.
Thank you. Sergey, I think you're up next. I am happy to introduce Sergey from Uber, who's going to be talking about what is going on with Velox at Uber. Thank you. And as a reminder, while you're setting up, we're doing our reception, happy hour, whatever you want to call it, after the talks today. So please, I encourage you to stay. It's going to be really fun hanging out with each other and having fun and celebrating. So please stick around after the talks are done today. Just go click back. Quit. You're going to do that.
Cool. Perfect. Thank you so much.
Thank you.
Hello, everyone. My name is Sergey. I'm software engineer at Uber Presto team. And today, I'm going to talk about the journey that we started at Uber for Velox and usage of Prestissimo. First, let me share the scale of Presto at Uber. So right now we have around 7,000 weekly active users. We do run 650,000 queries per day, read over 50 petabytes of data. We are spanned across 4 data centers, 2 on-premises and 2 on cloud. And we are actively migrating to cloud. 16,000 hosts and over 50 different sized clusters. There are some express clusters, there are some batch clusters, interactive clusters. In terms of workload, only 15% of our queries are actually accounting for interactive. So it's like ad hoc queries. Around 85% of all the queries are coming from batch scheduled queries. Why do we want to consider Velox? So Velox, or how usually people, sometimes people say Velox or Velox, I'm not sure. it has proven itself from Meta and like other companies. And what we do see, like this is the chart like which shows like the breakdown on the different operators in Presto. We see that 90% plus of CPU cycles that we spend is actually spent on the scan filter and projection. And obviously, Velox with its SIMD optimizations and like filtering capabilities should be helping us a lot, right? And we did some POC benchmarkings early last year. So, and we did confirm that the workload, which is very scan heavy, could lead up to 7x improvements in terms of CPU time. And so, yeah, we decided to start the journey and start migrating and like building tools around development and start migrating to Prestissimo. Of course, we faced the early challenges. Some of them were like just basic stuff, like lack of tools for C++. So Uber is actually not like a C++ shop at all. And nothing in the code base is in C++, so mostly everything is in Go and Python and Java. Even such basic stuff as like, I don't know, maintaining like a Debian version, so we run vanilla Debian instead of like Ubuntu or maybe CentOS, dependency management and everything, remote developer environment setup, like DevBots. It was all kind of challenging at the beginning, so lack of observability and other tools, like for instance, worker metrics were not actually there, and it's something very important we need to keep track of. Of course, in the early stages, we saw tons of worker crashes and OOMs. Some of the crashes were actually caused by dependency management, like one of the cases in open source, and thanks to a HANA team from IBM for helping us to pinpoint lib and bind issues. One of the first things we actually invested in was metrics integration using Apache Prometheus. So within Uber, we use M3. It's an open source metric system for Prometheus. And it was a collaborative effort with HANA from IBM. Detailed implementation proposal is present in the linked RFC. And as per proposed architecture, there is a subprocess within the Prestissimo process. It buffers Prestissimo process metrics and also serves as a streamlined HTTP server. And the mentioned subprocess above is implemented using the Prometheus CPP library to buffer metrics and make them available as an HTTP endpoint for the M3 stats collector to scrape them. So this is like a rough architecture of the metrics integration, which was open sourced and collaborated together with the HANA. Next challenge is we understand that Presto on Velox, Prestissimo has been widely used and adopted by Meta, but there are still some differences, right? Like some of the examples is actually Parquet. We use a totally different data format compared to Meta. Meta using Dwarf. And we couldn't start migrating without actually proper verification. So Presto Verifier was actually proven to be very helpful for us, especially in the early stages, to build the confidence around the support of the Presto on Velox. We integrated into Uber's infrastructure. We use it very extensively to onboard the first 5% of our traffic. 5% of like global traffic. And we found it not quite scalable to run verifier for every single onboarded query shape. And going forward, we're actually migrating more like on the shadow testing base. So basically, if queries can actually succeed, we do like mark them as eligible for Velox, but we do still run continuous verification on the queries selectively. And honestly speaking, we didn't face too many issues with the verification. I think Amit was sharing some of the SQL with like different like regex expressions and some complex regex. So probably maybe our customers don't actually write such complex regex, but definitely like Johnny versus Ritu and other things like Jackson and SIMD-JSON bring some differences, but we didn't face anything, and our first 5% of the traffic was quite randomized. One of the major things was, of course, memory tuning. So we did end up adopting memory arbitrator. I'm just like putting some configs over here, which we use for the total of about 250 gigabytes of RAM. We do see that since we are using Parquet and like memory management in Velox, yeah, it's doing a great job, right? Like on the overall. But many of the things, like such as third-party libraries, are still actually using direct memory allocation, and it's actually possible that the processes are actually going to be killed by the underlying system, which is running our clusters. So in the recent development, for example, we faced an issue with Parquet footer metadata loading, right? Like, we've seen some examples of, like, we have some tables which are like 5,000 columns wide, right? And many of those columns are actually structures, right? I think it's something similar that Masha was sharing about, not at that scale, but in earlier presentation, where there was like 13,000 column-sized row. And yeah, so some of our footers are actually more than 100 megabytes, so which is quite like huge, right? So compared to the industry standard, where the sweet spot is like less than 1 megabyte. But yeah, this is our state, and yes, we have to do something about it. Memory cache proved to be helpful, and early actually I think memory cache was causing some issues when it was misconfigured, but like eventually we could actually enable the memory pushback, and like our workers are more or less stable this time. Now the biggest, the biggest part is about how do we actually migrate the queries, so query routing infrastructure. So luckily, while working on Presto and infrastructure and ecosystem for quite a few years at Uber, we built some systems which we just could basically successfully reuse. So queries are routed to Presto and Velox queries, Presto and Velox to Prestissimo based on query fingerprint eligibility. What is a query fingerprint? We parse the query, strip off some of the like literals, like string literals, and we obtain the hash of a query. So there is exact and there is abstract fingerprint. If date string just changed or something like that, or maybe like some dates are changed, it's not really matter. That doesn't really matter much. It means that the query still remains the same, but underlying data is kind of similar shape, so the tables are still the same. So portion of the queries are still running through the Presto verifier, and in other cases, we at least ensure that the query can run in Velox through the continuous shadow testing. So essentially, we have a continuous shadow testing, which is adding to the pool of supported query fingerprints. And queries that are failed during shadow testing are analyzed and prioritized accordingly to further improve query coverage, and that's how we actually compute the query coverage for us. So this is basically here we can see that whenever Presto actually completes, query completes, we have Presto event listener, which will log the completion event to the Kafka topic. And then based on that, we have a modulator service, which is our like shadow testing framework. It can shadow the queries which have not been shadowed yet to the Velox staging cluster. So we want to avoid running the same query multiple times for the sake of saving capacity. We do save the list of supported fingerprints in the storage, and then we have pre-on service. Name doesn't really matter too much, but it's our like distributed like service, like coordinator-only service, which can do like parsing of the query, and in live actually detect the query fingerprint. It will actually, check if this query fingerprint is actually eligible, and if it is, it will be submitted to Velox cluster. And for now, since we are around 20% in migration on the cloud, we are still actually falling back to the Java clusters in case of a query failure. But so far, this is looking good. Parquet reader stability fixes and gaps. So this was one of the major issues for us because nobody else is using Parquet. Well, I shouldn't have said that. So like we started collaborating with Pinterest right away, and like not so many other companies like who actually onboarded like last year used Parquet. But yes, there is Pinterest. So we worked together with Pinterest and with Ahana, with the help of Ahana. And we did fix some things like complex type handling. We resolved issues related to the parsing of null values in complex types. And they actually previously resulted in incorrect output. Also, Pinterest team shared some technique about how to use unit testing framework that leverages the existing unit tests from Presto's Java implementation. It basically generates Parquet files using Java unit testing framework, and we ensure that we can actually run and read them using using Presto and Velox. Backwards compatibility is a big issue as well. So we run Parquet version 1.10. Right now in open source, we already have 1.15. And we address multiple backwards compatibility problems, some schema evolution problems. And CLAC support, CLAC stands for column level access control, is the major contributor to support coverage for us. So it could actually unblock for us about 40% of the queries. And my colleague Yunfei will talk about this in more details in tomorrow's session. So this is the data for the first, actually, 5% of the traffic. So we just did some benchmarking, detailed benchmarking of comparing the same setup of Velox on Prestissimo with 100 nodes versus Java with 100 nodes, and also Prestissimo with 70 nodes and versus Java with 100 nodes. We can see that under the same circumstances, same capacity, CPU time has been reduced 3.7x, elapsed time reduced 2.5x, and total number of queries which we processed was like 40K, and unique query shapes was 1,000. Even if we actually cut capacity by 30%, so we still see huge improvements in CPU time, 3.5x improvement in CPU, and 1.5x improvements in elapsed time. And here we can see that Java could be, we could actually push Java quite heavy on the CPU utilization. So in many cases, we actually could achieve like close to 95% utilization on the CPU. With Velox, we couldn't actually push it closer to maybe like 60% of the average utilization. So current migration status is we support over 10,000 different query shapes. We run 3 Prestissimo clusters with 30% capacity savings and migrated 20% of Presto Cloud. We're also moving from JSON to gRPC format in GCS connector. It's also showing us great results in like latencies for scanning. Parquet write evaluation, so we just evaluated this. We don't have much of the write workload. Most of our workload is select-only queries. But we did identify some issues we are planning to prioritize, and some of them were actually filed to open source. So the current implementation does not support end-to-end schema updates. Most of the common data types actually working fine, but there are some issues with time and timestamp. Compression ratio, we saw that Java Presto is producing the Parquet files much smaller size. And we filed some PRs to make a few of the coding policies configurable. And there were some minor Spark SQL compatibility issues. But yeah, they will be looked into. And also wanted to add a slide about the CLP connector. It's something we added in a collaboration with like CLP developers. Basically, it's a storage engine specifically designed for schemaless and semi-structured logs. It produces high compression ratio on log data and efficient queries, and it exposes a table-like interface for searching logs data, and so it allows us to search logs with 2x higher compression and 3x faster query compared to Parquet. This CLP connector RFC is linked over here, and we are adding it to open source as well. Geospatial support is a big topic for us. Obviously, we are Uber. We do things like polygons and stuff, and SD contains. They account for about 15% of Presto CPU time at Uber. There is an ongoing discussion, which we also collaborate with, and we are trying to contribute the pull request to the open source about supporting those like geometry functions and spatial joins. As for now, we're just trying to make it work, because spatial join is not actually supported natively, but for now we are using inner loop join, but basically first trying to make it work and then make it fast. And last but not least, wanted to share some thoughts about Uber's open source strategy for Prestissimo and Velox. So we have actually a separate fork for Prestissimo, and it's a separate fork compared to Presto Java. Currently, Prestissimo is running with 291 release, and Presto Java runs on 287. Prestissimo is like more lightweight version because it has like C++ part. And the Java part has minimal changes for Uber to make it work with Uber infrastructure. But we stripped away a lot of stuff which we added historically. Because we don't need them, because we don't run Java workers. And our end goal is to pull the changes from open source on a weekly or maybe like closer basis. It doesn't mean we want to run this directly in production. But the reasons we want to do that is debugging time is never actually wasted. So we've seen some issues when like we pull the latest like open source release or something like that. And in 2 of the 3 latest upgrades, we faced issues in Parquet. And obviously the Presto release is not probably tested sufficiently enough for us because it runs on the TPCDS, which doesn't really cover like many of the use cases like complex data types for Parquet and other things. And we face some issues when we're debugging something like for a quite extensive amount of time, and then we find that it actually already been fixed in 3 or 4 weeks down the road. So we want to make sure that this debugging is never wasted. It's actually easier because we want, like latest upgrade, for example, is going to be like 300 Presto commits and 400 Velox commits. We don't want to be alone. We want our OSS community to be our team, and issues we find and fix are community issues as well. We also want to know what we pull, because like oftentimes upgrades are basically, hey, we upgraded it and we are happy because everything is building and passing tests. But we oftentimes don't know what features we actually have pulled. And by taking a closer look, we will try to contribute by pull requests, by comments on the pull request, and tracking more frequently what's actually changing. Avoiding dual work, like for instance, the work which we do for the CLAC, column level access control, it actually has some conflicts in the master, so we basically have to maintain like 2 versions of the same code. So we want to avoid that. And we want to step out of isolation and engage actively with open source community. Learn from community best practices, coding standards, and debugging tricks and other things. Future work. Exploring mixed worker setup to run queries with unsupported catalogs. And geometry functions is a big thing for us. Continue work on query coverage percentage support. Continue migration of batch workload. Eventually, we want to move away from the fingerprint-based onboarding, because we want just to do this live to detect if the query is supported by Velox or not. And of course, like from there, we can move to supporting interactive traffic. Thank you.
Any questions? Okay. Thanks, Sergey. Next, I am pleased to introduce Ying Su from IBM, who's going to be talking about all of the work going on with Presto C++ and Iceberg. So do allow, and then quit. Then you can use this to move the slides. Oh, this to move? Yeah. Okay. Yeah. Thank you.
Hi, everyone. This is Ying from IBM. So today I'm going to talk about the Presto C++ Iceberg support. So the content. So I'll first introduce what Iceberg is, but I think most of you have already known this popular table format, and then we'll talk about our status in supporting this table format in IBM. We'll briefly introduce the design and the implementation, and we'll also present the performance improvements we did on Presto C++ read. And also, we'll talk about the Iceberg insert implementation and future work. All right. So I think most of you have known this Iceberg table format, right? So basically, it is a table format for us to manage all the data over time. Like we can do insertions, deletions, and with full ACID compliance. It also supports schema evolution and time travel, so we can go back to a certain timestamp back in the past. And it also has the query performance in mind when the creators was originally designing this table format. For example, it avoided the expensive directory listing. And also, it has its own ways to keep the column statistics to eliminate files more efficiently. So currently the Iceberg community is trying to go native. So they're trying to develop Iceberg C++. And here on our side, we're trying to support this in Presto C++ in native to support this table format in full. So I think there is a pretty good opportunity for both communities to work together. Yeah. So currently, in our IBM Lakehouse, we have supported the read of both V1 and V2 tables. This includes the tables with positional delete files and equality delete files. And our team has done pretty good, awesome work to improve the scan performance from last year. And we also supported the insert into this year. So it supports both partition and non-partition tables, and some basic partition transforms like year, month, and day. So we have updated the Presto documentation in the Iceberg connector section. So you guys are welcome to check out the latest support status, like what table properties are supported, what session properties are supported, and what metadata columns you can query for Presto Java and Presto C++, respectively. Okay, so let's first quickly recap the design and implementation of the Iceberg read. So for Presto, the architecture is like there is one or several coordinators and a bunch of workers. So when the query comes in, the parsing, planning, scheduling are done in the coordinators. So this includes several steps. So in the planning phase, we will send the request to the Iceberg catalogs to get the table metadata. And then during planning, we added a special rule that pushed down the filter to Iceberg tables. And then with all this information, we send this scan task to Iceberg library, where it will return the scheduler, the split manager that what splits that we should read and send to the workers. So here is where the partition and file pruning is happening. So it's done by the Iceberg library. And this part is actually all in Java, so I think, sorry. And then once the splits were generated, the scheduler would distribute them to the workers, where the worker is backed by Velox, where local planning and execution happens. All right. So a quick recap of how the positional deletes are implemented. So it's so on Velox side, the read is done by Hive connector. So it's a Hive data source. And the Iceberg specific operations were done in Iceberg split reader and precision delete file reader. So this happens when you're adding a split to the Iceberg split reader. It would create the row reader for the base file and also create the precision delete file readers if there are any precision delete files. And then during the real read, which is implementing in the next function, it would ask the precision delete file reader to read the deletion positions, and the result will be sent back to the base file reader as a mutation object. And it's actually a delete bitmap. And this bitmap will be pushed down to the reader as an initial row set. So they will be excluded from the very beginning, meaning that we don't have to decode these values and put them into Velox vectors. Yeah. And last year, we supported the reading equality delete file as well. So, so Iceberg supports these two different delete modes. So precision deletes, where you have the positions of each rows being deleted. And the equality delete file actually holds the value. And so it could be a single column or multiple columns. These were Iceberg identifiers. So in implementing this, we will translate them into domain filters and filter functions. So if it's a single column, so we'll transfer them into a not-in filter with a special handling of nulls. And this can be pushed into the reader. Yeah, and multiple column delete files, or there are, so multiple columns will be created as a filter function as a remaining filter that the reader evaluates after the read is done. So you can see in this chart, we have a new equality delete file reader, which does the read and the interpretation of these values. And so with these basic implementations, we did some performance testing last year, but to our surprise, the Iceberg connector, Iceberg in Presto C++ is like 45% slower than the Hive connector in Presto C++. So our team worked really hard, and we have fixed this regression. So when looking at this regression, we firstly noticed a very long Presto query planning time, like in seconds or even in minutes. And also we noticed the plan difference between Iceberg and Hive. Okay, so then our brilliant optimizer team, mostly Zach and Ritika. So they made a bunch of fixes. Oh, I forgot to mention that the first thing we noticed was that the scan planning time was really long because the Iceberg library keeps reading small files in many times. So for a single query, it might be reading a small file for dozens of times. And this is very slow. So to fix this problem, so we introduced manifest file caching in Presto repo. And also, we also added the statistic file caching. And then the optimizer team come with several statistics and the cardinality estimation fix. So at the end of last year, so we were able to see the plans were exactly the same between these two operators. And then we start noting that there are some execution time regressions. So Zach first noticed that the split size is much smaller in Hive operator than Hive. So he introduced session property Iceberg target split size bytes, and also we support the table property read split target size that you can specify the split size, and this helps the problem a little bit, but not all. And then we noticed there are the skew problem was pretty bad in Iceberg connector. And so this was because the difference between Hive and Iceberg. So I think Andre made some fix in the Hive connector. So we ported that over. So then the skill was much better. So for now, we can see these two connectors were almost the same. So the run-to-run variation is within a few percent. Yeah. All right. So next, I'm going to talk about the insertion implementation. So with insertion, so everything else is very similar to Presto Java, except that the writer part is done, in the worker in Velox. And in our task, because we use Parquet, so this would default to the Parquet writer, which was originally copied from Arrow. So this is like the whole process is like. So similar as read, the split will be scheduled to the worker, and worker would do local planning and create the pipelines drivers, which contains the table writer operator as a data sink. So in the add input call, the Hive data sink would call append data, which would calculate the partitions, bar key IDs, and so on. And then it would, so we introduced the Hive Iceberg data sink, which subclassed Hive data sink. And with this custom implementation of split input rows and ensure writers, which is, we do Iceberg-specific operations, like we get the writer parameters from the Iceberg insert table handle, like the write directory, file format, table name, and so on. And then the ensure writer would create the writer, the actual writer, during which partition data will be calculated. So because Hive and Iceberg handles the partitions quite differently. So for Iceberg, it writes every data column. Every column, no matter is partitioned or not partitioned in the data file. So we have to remember what the partition values are. So we collect them during this moment. And then the table writers, the actual data writers like Parquet writers, Dwarf writers will actually do the write work. And at the close time, the commit data will be created. This includes the data path and the size and the statistics and so on. And this commit data will be sent back to the coordinator, which we handle it to the Iceberg library to do the final commit. Okay, and here is some performance numbers of the insertion. So we use the TPCH 1 terabyte data load from the TPCH connector. So we run this in Presto Java and Presto C++. In both Hive and Iceberg connectors. So we see that the C++ implementation is about 10% faster than the Java. And this is actually coming from the TPCH connector. So as you can see in the right chart, it comes from the scan, filter, and project operator, which is incurred in the TPCH generation. So the native TPCH connector is about 2 times faster than the Java one. But the right part is not particularly faster, which indicates future improvements, opportunities. Yeah. All right. So we're doing some testing work currently. So this includes like adding more end-to-end tests in Presto. And we're also building the pipelines for these 2 major benchmarks, which includes the data loading phase and data maintenance phase. Both includes the inserts. So we have built this into the pbench tool, which is also public, available to the public. And also in the next, we're going to port over the Iceberg Presto tests into our Presto repo. And at the same time, we're working on the unfinished partition transform. And sorting is also something we are working on. And in the future, we want to support more metadata tables and columns. So far we support 2 metadata columns in reading, which is path and I forgot the other one, but so these 2 are constant columns. So if you want to read a row number, for example, or which row is deleted, then that needs additional work in Velox part. And also, we want to make sure this equality delete file reader works for Gluten as well, because we use the logical expression evaluations, and some of these logical operators are different between these 2 engines. So we'll need to generalize these. Yeah. And also, there are some data types not supported yet. That we need to build the filter, the expressions for these data types. Yeah, and next we're going to work on delete. So we're going to support both writing precision delete and equality delete. And more performance optimizations in the Parquet reader and expression evaluation and Parquet writer. Yeah. And I'd like to thank our team in IBM. So they come from different teams in like execution and optimizer team. Yeah, so together we made this work. So special thanks to them. And also special thanks to Meta folks who help us reviewing the code. Yeah, so that is the end of my presentation. So any questions?
Staying up here, right? All right, thank you, Ying. Ying's going to stay up here because she's part of the next session, right? Okay. We're doing a feature deep dive. So Ying, Aditi, and Sumya, all from IBM, are going to come up and share a little bit more about some of the work going on in C++. Do you have a laptop? Who's starting?
Hello. So hi everyone. Hi everyone. This is Soumya. I'm Aditi and Ying, and we are going to talk about all the Presto native features that we have built at IBM over the last 6 months. So Soumya is going to talk about custom functions, custom user functions, and dynamic loading for Presto C++. I'm going to talk about some new cross-optimizer and runtime optimizations for streaming top-end and CTE, and Ying is going to talk about shuffle improvements all across the board. So we'll just do our presentations one after another and leave time for questions at the end. So Soumya will go first. Yeah.
All right, thank you. Thank you for the introduction. All right. Okay. Try the other clicker. Oh, yep, got it. All right. Okay, so hi everyone. I'll be talking today about the work that's going on in Velox right now regarding dynamic loading. And I will keep this short because I don't want to keep anyone from figuring out what Ying and Aditi are up to, so I don't want to be that person. But let's paint the picture. So what is going on right now? So in Velox, the only way to add any like custom functions, types, connectors right now would be to do it built in. And for anyone who's worked in the Velox code base, you might be familiar with what that effort looks like, but let me give you a quick overview. That can be cumbersome in that it requires a lot of understanding of the code base to begin with, to know where to put the code, where to write the code, what to do with the code, and all of that, right? At the same time, it can also be time consuming from a compilation standpoint because compiling and recompiling can take longer time and make your executable larger as all of your functions, connectors, types, and everything are sitting in the code base, right? So the solution is we have now added the ability for users to dynamically load any functions, custom functions that they would like. In the future, we also want to extend that to types and connectors that is currently in the work. So what does that look like? How would that look like? Let's explore this use case. So let's see how Presto C++ is going to load dynamically loaded user-defined functions, UDFs, and use this config-driven wrapper into like using the Velox's dynamic library. Okay, so I know this looks like a lot of code, but let me walk us all through this. So I labeled everything 1, 2, 3. So the big one is the CPP file, the C++ file. Next to it, we see the CMake list, and underneath, there's a JSON file. So these 3 elements are going to be needed for you to get started with these UDFs. For the CPP file, there we go. So much better. Most of this code that you're going to be looking at is boilerplate. What I want us all to take notice at is, you know that line that says result equals 1, 2, 3? That's where you were implementation for whatever you want to do with your user-defined function will go. Similarly, I see inputs and outputs, which you can write according to whatever types you want, whatever you would like that to look like. At the very bottom, the bottom arrow over there, there's a register Presto function. In there, you can find the name of the function. So the important thing to note here is that everything else is boilerplate code, and we want your implementation to be the only thing that you're worrying about right now. So how do I take the C++ file and turn it into the shared library that I promised you all you can load dynamically into your Presto workers and coordinators? So on the right side, there's a cmakelist.txt. Now, this is one of the ways that you can get started and get up and running. But this is, again, essentially some copy-paste boilerplate that the only thing that you will be that we would request you to change, and of course you have free will, but is going to be the name of that library so that you can find it afterwards. Lastly, that JSON file in the bottom is going to be the config-driven wrapper layer. Now, what does that mean is we want to have some sort of validations for whatever function that you're going to be loading. So I'm going to show you from these arrows what we are looking to validate. One, the file name over here is going to have to match up to what we just defined in the CMake list, or the name of the shared library. And then there is a few other things. For instance, the name of the function, dynamic VeloxCon, how convenient, and our parameters, return types, and whatever else that you would like to be able to check, you can take a look here. And I know this looks like a lot, so there is extensive documentations and examples that we've left for you to explore this on your own time, and I've linked the documentations to these slides as well. So once you've set this up, how do I get up and running? All right, so for that, we would ask everyone to take their workers and check their config.properties file. In that config file, you would add your plugin.dir property, your plugin.config property to the paths of these files that we just created, the shared library and the config JSON file. In addition to that, when you start your coordinator and your worker, the Presto server is going to do all the validation and load these user-defined functions dynamically. All right, so that's all for me.
So our next set of features are around performance. And we sort of came up with these features examining our TP-CDS query workloads, but these are really broadly applicable features and are useful across the board. So the first feature is something we're calling streaming top N. And if you see like the TP-CDS profile here, right, there's one query that stands out, and that's Q67. And if you see the runtime, I mean, with release 288, which is some time back, the native engine had a runtime of 31 minutes for 100 queries, and 9 minutes out of those 30 minutes were in Q67. So it's a pretty bad query. So we kind of wanted to, we spent some time trying to understand Q67 and what we could do there. And so on the left-hand side, I've projected like Q67. And if you see what that does, is that there is an inner like subquery that does like this massive join, and it has a group by rollup to compute like aggregates for different sets of columns. But what happens at the outer layer is that we do this rank function. So, and that rank function basically kind of separates the rows, it partitions by category, orders by the sales that it has computed as an aggregate, and is only looking for actually the top 100 ranked rows in every partition. So like your inner massive join has like 386 million rows, but the result is only like 1,100, well, 1,000, around 1,000 rows. the rank computation today is done with this window function, window operator. And the window operator today, what it does is it gets all the input, stores it in an internal row container, then it does a big sort at the end of seeing all the input, where it uses the partition by and the order by to sort the data, and uses that to demarcate the partitions. And after you identify all the partitions, it computes the rank across for all the rows, and then post this window operator, we do a filter to just take the top 100 ranks. Now this is very inefficient, and we can do much better. So at the very least, we want to push the filter into the rank so that the window operator doesn't really generate that many rows, but we can do better than that. And so rank can be computed in a streaming fashion. And so you don't really need to see all the data and then do this massive sort. Rank can be computed on the go. And the partition can only retain the 100 rows per partition, and so you won't have this massive memory sink and intermediate data that you need to keep for this query. And so with these two optimizations, we saw that the latency for Q67 fell from around 400 seconds to 146 seconds. So how we did this is that we wrote this new top-end row number, top-end rank operator. And what this does is it does a streaming top-end rank computation. So basically, it uses a hash table to identify the partitions using the partition key. And then for each partition group, we maintain an accumulator with a priority queue for just the top 100 ranked rows. And as every row comes in, we decide whether it should remain in the queue or leave the queue, depending on its order by key and its rank in the partition. And we've implemented this logic for rank and dense rank functions. And since this is a new operator, it needs planner changes. And so we added a planner rule to identify the query pattern where you have a rank filter. And we will now use this new operator instead of the window. The second optimizations are for CTE with clause. So SQL users use with clause to identify common tables that are used multiple times in a query. SQL semantics dictate that with clauses should be computed once across the scope of the query and reused each time the with clause is used in the outer query. But this is not what happens in Presto today. Presto expands the with clause just like a view, and it is recomputed each time. Now, this can get ugly, and because CTEs can use other CTEs, and so what that means is that you're kind of multiplying the number of times you might expand the innermost query. So this is example Q64, where there is CSUI, which is the innermost layer of the with clause that is used in the next layer of the with clause, which is computing cross sales. And then cross sales is used in the outer query, which is actually doing a join, self-join of cross sales. And so the innermost query is going to be repeated multiple times. So this is very prohibitive. And we wanted to make with computation closer to the standard by actually doing common table materialization. And so again, this has a whole lot of optimizer work because figuring out which common tables you actually want to materialize and reusing them in the query, it's a complicated problem. And there are many rules, you want to ensure that your with query is used more than once. If there are common filters, you want to push them down in the with clause so that it's more efficient. But so I've linked this article that Jay from Uber wrote about the planner work that's needed for executing CTEs. But in just a quick summary, right, what we do for CTEs is that we look at the CTE references, and they're actually, instead of expanding them, they're separated into a producer and consumer part. And so the producer is like a writer. You do the inner subquery, write it to a table. That table is only for the lifetime of the query. And then the written table is reused in all the references in the rest of the query. And in order to ensure that we have the right sequencing, that the write pipeline completes before the read pipeline, there is a sequence operator that the scheduler works with. So we made all the runtime changes to support these new CTE reader writer configurations, and saw a lot of improvement using CTE in the native engine. And we are doing a lot more experiments because right now we're using just the regular like ORC and Parquet reader, but we want to use more efficient like serialization, deserialization formats. And if possible, we want to do like a proper streaming CTE so that we don't have like writers and readers. So that's that. So I'm going to hand it over to Ying.
That's quick. So the next, I'm going to briefly talk about Presto C++ shuffle performance. This is an ongoing work. It's far from finished, but yeah, it's quite interesting. So I will first talk about so what consists of the shuffle cost and what we have done so far, and we'll briefly go through the design, implementation, and so on. But these are in a very preliminary stage, so just some data points and discussions. All right, so why do we look at shuffle? So this is because when we are running these benchmarks like TPCH and DS, we saw that the shuffle cost is quite high. So for example, in TPCH, partition output and exchange and local exchange, they comprised of over 40% of the total CPU, and this is very high. So in this benchmark, you're supposed to see some big aggregations, but this shuffle thing is too high. And also TPCDS shows some similar numbers. So let's zoom into one particular query, TPCH query 9. So this query has the highest shuffle cost in TPCH, the 22 queries. So as you can see, this partition output itself takes 30% of the total CPU, and the next one, exchange, takes 29, and then the next one, table scan, 20. So yeah. So then we ran some CPU profiles. We saw that a very high percentage spent in Exchange I/O and HTTP I/O. So these network threads are taking a lot of CPUs. So this is what our research team is working on a binary exchange protocol, which tremendously improved these two parts. And also, I did some tests just last week. So because this query shuffles a lot of data, so we thought maybe compression would help. So to run this, we have to introduce a new session parameter, exchange compression codec. So this is new, so you guys are welcome to try. So currently it supports every compression codecs, LZ4, gzip, DSTD, and so on. So with LZ4, unfortunately this doesn't help, and it's even slower, 2x slower. So we'll have to do something else. So my talk is mostly, in the driver part, especially in partition output and the exchange protocol and exchange operator and so on. So if we zoom into the driver part, the partition output is taking 42% of total CPU. And then the next one is exchange, 17%, and then hash join also 17%. So within this partition output operator itself, so which is a small pie chart to the left, so you can see most of these were spent in serializer, like serializer appending, and also estimate serialize the row size also is the green part. It's like nearly 10%. And the CRC flush takes 31%, which mostly it's in CRC 32. All right. So we did some internal experiments by introducing a new optimized partition output operator and a new partitioning iterative partitioning serializer. So I have implemented for flat vectors and array vectors and dictionary vectors, and I'm still working on those, but got some pretty good numbers so far. So for flat vectors, we can see there are over 15 times to over 20 times improvement. So this is done using exchange benchmark. All right, and big array. So I did some simple tests as well. Shows about 4 to 5, 6 times of improvements, and dictionaries shows improvements as well, like at least dozens times. But unfortunately, I lost the data yesterday. But it shows that it works. But other exciting ideas is that this partitioned vectors, okay, in place partitioning. So it doesn't only work for partition output, but we can also use it for streaming aggregate or sorting. So I believe this will help streaming aggregate at least. So yeah, but this is something I'll do next. So other improvements including like improved CRC 32 computation, which is not included in my numbers, in my tests, but thanks to Bingwei, so we are able to see that we can do 4 times faster than the current Folly CRC 32 hardware function implementation. And hash partition function improvements. So we have 4 times improvements with streamlined loop and AVX2. And also range reduction improvement. Yeah, it's improved at least over 1 magnitude times. All right. So that's the efforts to reduce the CPU times. And we also see some pretty big contentions in output buffer implementation and the exchange queue. So for output buffer, so the basic operations like acknowledge, enqueue, get data, delete results. So they currently all require a global inclusive lock. So with a new prototype, so we can move all these to their single destination buffers instead of the whole output buffer. So meaning that when you're inserting into one destination, you don't have to lock the whole output buffer for all destinations. Yeah, and also, I also noticed that the exchange queue contention was pretty big. So inside of the exchange client request function, so substantial CPU it's used in the mutex acquire and so lock and unlock. So the idea is that we want to replace this queue to a lock-free queue, so we can potentially use follies, so it has several implementations there. Yeah. So the next steps includes like covering all data types, all types of vectors. Like so we currently have so we don't have map yet, and also that delta, or I forgot the name. So constant and also nulls. I'm also working on this, the exchange side, the receiving side. So when I was looking at the profiles, I actually found a large portion of the CPU was spent in the memory deallocation of the serialized pages in the receiving side. So thinking maybe we can reuse this part of, so especially for local exchange, that we can reuse these memories. Yeah, and also, like I said, this output buffer and exchange queue contention. I'm still working on it. So, yeah, I still have some bugs to fix. Okay. Yeah, so that's the end of my presentation. Thank you.
Also, quick shout out to PrestoCon days happening soon. And any questions from anyone?
So in the production, when we put the UDFs and you put a library in there, at some point we have to upgrade the library. So how can I do it in a live system?
So I'm so sorry, could you repeat the question
Okay,
really quick?
so you registered library, okay, it is running. At some point I want to upgrade that library to go to the next level. I'm not changing the name of function or anything. How can I do that while the system is running? I have existing queries that they're running, that they're using the current version, and then new ones hopefully will use the new one. Can you handle two libraries at the same time? And understanding while not affecting the existing queries running.
Oh, no, we don't do that.
We
don't do that.
Yeah, I know. So that's a problem, right?
Yeah.
Because then you have to shut down, you have to quiesce the system. That's not an option.
Yeah, it's going to be multiple steps to make that happen. Yeah.
Yeah. So you have to have versioning over there.
Yeah, we have to.
And the runtime.
Yeah.
Lock the version for the existing query, and then new queries take a new version. So you have the token over there to handle this. Otherwise, it's a big problem.
All right. Thank you. Oh. Sorry. Yeah. You just talk loud.
Thank you. Yeah. Just a question about the CT bit. For the inlining, does that only occur when like the CT is being used once, or does it occur if the CT is being used multiple times? Like in Postgres, there's like a not materialized keyword that can control whether you can push down the filter even if the CT is only being used the one time.
I believe we have a configuration to say like what is the threshold. So you can say that only like use CTE, with the materialization when there's more than so many occurrences in the query. So we have a config for it, yeah.
Thank you.
All right, thank you. Okay, we're going to round out our day with our last session, End Strong. We're going to dive into some operational efficiency work that's been going on with Presto C++. So I'm going to welcome Christian, Deepak, and Minhan up to stage, all from IBM, to share more. And just a reminder, as they're getting set up, if you are leaving any point, like later tonight or now, just make sure if you're not a Meta employee, that a Meta employee does escort you out. It's a rule here. I was told to remind folks. All right. Here you go. Allow. Start mirroring.
Entire screen?
Yep.
Extended display. Start mirroring.
And then quit. Yeah. And you just want to go to slideshow. Yeah. Yep. I don't know which clicker it is. You have to try both.
All right, hi. My name is Christian. I work for IBM. And today I want to talk about the Linux memory checker. And we've seen already, and first of all, I want to say thank you for all sticking around. It's kind of like a long day for every one of us, I think. Later on will be the reception, so I hope we have also more fun then. But I promise it's going to be the last group of presentations today, so we're almost done. Anyhow, so the Linux memory checker. Now, Sergey already, I don't know where Sergey is, but he talked about, he had a slide there and he was talking about memory, out of memory conditions and certain configurations that would have to be done in order to kind of prevent this kind of situation. And he was kind of already hinting at there's something there that enables the memory pushback. And what that is that Linux memory checker, I believe, that he's using. And so I want to go and explain a little bit more as to the motivation why we have it, and how it actually works a little bit, and some of the configurations. So Velox itself has already a very sophisticated memory management. So when you configure it in Presto C++, you tell it, oh, as a memory manager, you have a certain amount of capacity that you can use, and it is used for the query memory pool, for the async data cache, right? And when you think about deploying Presto C++ in a cluster in an environment where you want to make use of all the caching, the async data cache is really useful because it caches data that you have read from your external storage. And if you reuse it a lot, you gain a lot of performance by not going back to your original data source. The problem with that is that your memory manager and the usage of the memory will run out of capacity really quickly, because we found when we did run the TPCDS benchmarks that most of the memory is actually taken up by the async data cache. In itself, it has out-of-memory handling, so you're running up against the capacity, and what it will do is it can push back that usage of the file cache, the async data cache, and free up some more memory that it can then use for query processing, for example. Right? So it's a very good workable memory management, but it runs up against a little bit against what the reality is when we are looking at the Presto C++ deployments. The one configuration where you define the capacity for the memory manager is the system memory GB. And I don't know if you remember this from Sergey's slide, he had it set to 180 GB, I believe. So because not all of the memory will be controlled by the memory manager, we have to think about, okay, how do we address the problem when we run up against this capacity? Presto C++, it does have its own HTTP component for the exchanges with the other workers, for example, memory that's not accounted for within the Velox context. Then when Velox reads Parquet data, there is a file metadata that's also not under control of the memory manager, because it's not part of the query memory pool itself. It's not accounted for. And then at the time that we investigated this a little bit further, we also found that in the hash probe operator, there were a couple of vectors there, the raw vectors that also used unaccounted memory. But that by now has been fixed. So now it's using the memory pool for any of these raw vector allocations. But at the time when we implemented this and researched this, we didn't have that. And so what happened was when we were looking at the TPCDS benchmark, we get all the nice slides that we saw earlier on how helpful Velox is, we ran out of memory. And I think we heard from Sergey that they had similar problems as well, and I believe other people had it as well. So what to do about this? So if you think about it again, if you look at the total system memory you have available, so when you deploy it in the context of a container or on a host. If you deploy it on a host, you run the Presto server process with all the configuration, but of course you're not going to allocate the entire memory that your system has to the system memory GB, right? Because you do have operating system processes that are running. that that you have to take into account. And so therefore, you wouldn't want to allocate all this memory. And the same when you have in your container context, so you can have one or multiple containers running on the host operating system. And then the way that your container configuration is, you have the container runtime, and you say, oh, this container uses X amount of memory. And again, you probably don't want to set all the memory that's available in that container configuration to be used by Presto C++. And so what we end up having is that we're configuring the memory for Velox to be a subset or slightly smaller than what you have available in total on your system within the container or on the host. And so what you then end up with in a situation is once Presto server is running, you run some queries, right? It loads up async data cache. We're assuming that async data cache is enabled here. Then it slowly starts filling up using all of the memory. And meanwhile, on the other side, you have other operating system processes or other things that you run. For example, one thing that could be running is the proxy, the Prometheus. You have some local process that scrapes the Prometheus metrics, for example, and sends them on some else or whatever. So you have memory usage outside. And now you're running, you come from the top and the bottom, for example, left and right, and they eventually will collide. And so you have the total unaccounted memory that Velox does not know about. And then on the other hand, you reach into that available memory that's being used up by the memory manager. And this is highlighted here, where some of the memory that you have reserved for use by Presto server is actually being used eventually, perhaps, from outside of Presto server itself, right? And once you run out of all your memory, what happens is the container runtime will just snap your container. And the host, well, if you're running on the host, then your kernel will give you a sick kill, signal 9. And so this is highlighted here in this situation where you have an overlap of that memory. You just run into a situation where you completely run out of the memory itself. An operating system will not give you anything more for your process, and it kills it off. And that means your query cannot finish processing. Like it's a non-recoverable situation at that point. So what to do? We've heard that there is a pushback mechanism that is implemented. And one thing that was contributed by Meta is that periodic memory checker that implements that pushback mechanism. And it's a generic implementation that we then built on top with that Linux memory checker. So the Linux memory checker decides when to call the pushback and how to determine that. The shrink mechanism itself is on the file cache. So because we know most of that memory is going to be used by the async data cache anyway. So what happens in the pushback case is you tell it, I want to free up an emergency free of memory to continue processing. I want to free up that memory now. And I don't care what you free, because normally there's a least recent used algorithm that displaces pages. Just free anything, right? So there is some performance impact in doing this, but at least your query, your worker won't die from it. So the Linux memory checker extends the periodic memory checker. And what it does is we are setting a particular limit, and we'll see later in a slide what it looks like, a specific limit of up to which the process server can use memory. So a very particular value, and that value is going to be lower than what your host has available. Sergey mentioned the Prometheus metrics, and similar to that, you have to enable a build flag to get the Linux memory checker built. So Prometheus has the same thing. So it's not coming by default. You have to sort of do a little bit of build time changes, and then you have it available in your executable. So what happens is, same situation as before. Now you're setting a memory limit, right? The memory limit, the way that you choose it is kind of like try, right, to see what is the best outcome, because you want to allocate the memory, or you want to allocate as much memory as possible to the Presto server. So your memory should be close to what the host is, but be careful because you have allocations, and if the distance between the memory limit and the host memory is a little bit too small, then again, you could run into the out-of-memory situation, because we'll see in a second that the periodic memory checker, it will check every second for this condition. So if you have more allocations possible within a second between the memory limit and the host total available memory, then you might still run into problems. So you have to be a little bit careful. And so what happens is, okay, you have more allocations. They just cross the memory limit. Periodic memory checker kicks in. And the Linux memory checker implementation of that says, oh, you're exceeding your memory limit now. Then it will call the pushback, and so that later on, less memory is being utilized. And that memory comes out of the async data cache, as I mentioned earlier. And now we're back to a reasonable amount of memory, no problem to the query continuous processing. So how do we know how much memory is being used by the process in the first place, right? For that, we're using a Linux feature, or a feature of the Linux kernel, the Linux control groups, C groups, and they is like file-based, and it exposes information about the process. And specifically, there's all kinds of metrics that are in there, and one of them is about the memory usage. There are two different types of the C group, V1 and V2, change the file layout a little bit and where it's located. Okay, that's fine. So we support both of them. And then if we cannot find the C group information at all, then we fall back to the proc mem info of a Linux kernel. And I mentioned before, that check against information that is contained within the C group is checked every second. At the bottom, you can see a little bit of an output that you have when you start a Presto server. So it will tell you what your configuration is and how much memory it detects that you have available. So besides just knowing how much memory the process itself is using at every interval, it also can detect what is your current or total system memory that's available as well. So it uses also information from proc mem info and the C groups for that as well. So we know what is the total system memory, regardless of what you configured, and how much memory are you currently using at the time of the check. So there are these three configuration variables. We saw them in Sergey's talk. And there is a condition upon them where your system memory GB is less or equals than system limit GB and is less than the total system memory that you have available in your host or in your container configuration, right? The system mem limit GB, you want it to be larger than system memory GB, because otherwise you run up against the limit and you're not making full use of the total available memory that you want the Presto server to use, right? So that's why it has to be larger than that. At the same time, system mem limit GB, it cannot be larger than total system memory, because then the pushback would never kick in, right? The condition to trigger the pushback would just never happen. And so we added like a check for that as well to make sure that these conditions are all true at the time of Presto server startup. Yeah, that would be the talk. And I hope my next colleague, or maybe one quick thing, some links about the C groups. You can read about it, how they're implemented, and the documentation for them. And then the configuration you can find also on the Velox documentation as well. All right. And I'm handing over to my colleague Minhan, who's talking about the SSD cache.
All right. Thank you, Christian. So hello, everyone. My name is Menon. I'm also a software engineer at IBM. I'll be presenting about how to utilize the SSD cache. This also will relate somewhat to the async data cache as well. So a little bit of an overview for this SSD cache. It is supposed to serve as an extension to the async data cache, otherwise known as the in-memory file cache. One reason to use SSD cache is to help mitigate the number of reads from slower storage. So let's say you have a storage in like the cloud S3. Instead of reading from there and making a request, which is slower, you could read it from the SSD instead, which would be a faster read. And yeah, the SSD cache and also the async data cache is in the Velox code base. And the way it's set up is the SSD should be on the worker machine for the Prestissimo workers. Yeah, so why use the SSD cache? So it will help with performance due to reads from a local disk instead of reading from a cloud online storage like S3. You save costs as well, because with every request, there will be a little bit of a cost to it when you do a GET request to the S3. Then ensure your SD is large enough for your workload or work set to fully utilize the SSD itself. So the setup and configuration for the SSD. So one thing is the local file system needs to support underlying or direct reads and writes. For example, at IBM and our clusters, we use the ButterFS file system on a CentOS Stream 9 host machine. So to turn on the SSD cache and use it in your configs.properties, you want to set these two configurations here. The first one is the async cache SSD GB. By default, it's 0, which means it's off. So you would ideally set it to the size, max out your SSD, or whatever size, how much you want to use of the SSD. And then the next configuration is the async cache SSD path. You would set that to the path where your the ButterFS file system is mounted on in your SSD. The default is this path right here. And then this will be a link to other configs that would be you could use for the cache. And here is an example log when you start up the Presto server process for the Prestissimo worker. So if you start it up correctly, you should see some details here about your SSD cache, the number of shards, and also it should say async data cache with SSD has been set up, which means it was successful. And then these are some important configs that has to do with the SSD writes. So the first config is the async cache max SSD write ratio. What this config controls is it's basically the maximum threshold of how much data you want to write over to the SSD. So some of these data, they have to be marked as SSD savable in order for them to move to SSD from the async data cache. So out of those, so the default here being 0.7, it only move up to a maximum of 70% of the data in the async data cache. And then the next config, which is async cache SSD savable ratio, you think this as like the minimum part of the ratio, where this is when you would start writing to the SSD. So for example, once it reaches 12.5% of SSD savable data, then it will start writing from the async data cache to the SSD. And the last config is async cache min SSD savable bytes. So by default, this is 60 megabytes. This is basically just how big by minimum do you want these data to be written over. And then here's a diagram of a before. So the orange here is to show that this is the data is to be saved or copied over to the SSD. And then in the next slide, what happens is it will be saved over to the SSD, as you can see here. And then the reason that we want to save it over is one example is, so let's say you as Christian was talking about earlier about the Linux memory checker. Let's say you do run into like hitting the memory limit, and that causes a shrink in your async data cache. So the pink on the left, that is the data that is to be evicted, which is being shrunk from the async data cache. So that will be gone when it's evicted. But then, since you already copied it over to the SSD, if any queries in the future when you run it on your cluster, it will look at the SSD and it'll see that it's there, so it won't have to get it from like your cloud storage or S3. So that's one of the benefits of using SSD. And then some endpoints here you can call. The first one is to clear up the async data cache entirely, if you choose so. The second one is to clear the SSD cache entirely. And then the last one is to trigger the write to SSD. And then here are some tables with some data points on the runs what we tried with and without SSD cache. So the first table is without SSD cache. As you can see, it ran in 4.76 hours, whereas the second table with the SSD cache, it ran in 3.73 hours. So that was a pretty big improvement of 1 hour difference. And then also, if you focus on the total S3 number of storage reads, 5 million against 2 million, so there's 3 million difference here. So yeah, better performance in time and also less S3 reads, which is help you basically offset the cost of storage for SSD by reducing cost of reading from cloud storage like S3. Then here's another some data points by running the TPCH SF1K. Yeah, so same thing. We saw improvement in runtime of about 30 minutes. Also, 2.72 times less S3 reads as well. So yeah, that would be the end of my presentation. And now I'll be passing on to my colleague Deepak.
Thanks, Minhan. Is your laptop, Minhan? Take yours. All right, the last talk of the day. So I'm going to talk about another key feature of Velox and Prestismo, which are stats and metrics. And to keep things interesting, I'm going to do a live demo towards the end of my talk. So stay tuned to see if the live demo is going to work or not. I'm that brave speaker today. All right, so throughout the day, we saw a lot of production applications of Velox at various companies. And a key for all of them to run effectively are the stats and metrics that Velox and Prestismo provide. So I'm just going to give you a rough background on what these stats and metrics contain. So if you use Presto, you have this UI when you run a query, and you see a bunch of numbers like CPU time, schedule time, parallelism. And all these are very important to understand how your query ran, how your workload ran. And all these are, this UI is actually supported by the stats and metrics that Velox and Prestismo provide. In fact, for Prestismo, some of these stats are critical because it impacts the scheduling. If you report the memory or CPU or splits incorrectly, then you might see a scheduling problem, and your workload might actually perform poorly. So it's very critical that the stats are reported accurately, the memory consumption is reported accurately. Otherwise, you might overschedule or underschedule, and you might see a performance problem. And similarly, Ying showed this dashboard earlier. In IBM, we continuously monitor the releases of Presto versions using something called pbench, where we run some TPCH and TPCS benchmarks. And we use this dashboard to see how the queries are running, either regression or not. And also, so in this dashboard is powered by the metrics and stats. All right, so the two things, stats and metrics, the names don't really capture what they are. But in a sense, stats are actually those which are always captured. If you're a profiling expert, you would have seen two kinds of techniques. One is instrumentation, and one is sampling. So stats are the instrumentation kind of counters, where you always capture those metrics or I'm again confusing, but you always capture those counters or those fields. And you have stats in Velox at every level. You have per query, per task, per driver, per pipeline, per operator, the memory level, spill stats, and whatnot. So all core components of Velox have stats that you can analyze and see how they are, how your workload is behaving. And for historical reasons, there are two types. One are typed counters, where you have like an integer timestamp, and those usually these metrics are common across different tasks or operators. For instance, if you have like a number of rows, it's a common counter across all operators. And you also have these untyped custom runtime stats, which are more free form, and they can be used to sort of specify operator-specific counters. For example, if you have a table scan, you might want to report splits or some I/O counters, and you can use the runtime stats to represent those kind of specialized counters. So some example stats that Velox has is like at the task level, you have like the start time, end time, number of drivers, number of drivers that are queued. So this will tell you that they're blocked for some reason, and you can probably investigate why they're blocked. And then there are pipeline stats. Within the pipeline stats, there are driver stats and operator stats. And also like with the splits, you can see how many splits are scheduled and how many are running and whatnot. And at the operator level, similarly, you can check out what is the time for getting the rows in, what is the time it takes to getting the rows out, if there is any spilling going on, and so how much memory the operator is consuming, and all the resources that go into that operator. You can pretty much profile. All right, so those are stats. Now, what are metrics? Metrics are sort of the optional events that you can capture at the sort of the global level. So this is similar to sampling, where you don't actually capture every event. You sort of do. It's up to the implementation to capture at what frequency these counters happen. These are optional. So if you only enable them if you want to sort of debug further, or if you want to have some sort of alert that you want to generate if says memory is hit, if it's going, the whole node memory is reaching the limit of the machine, then you sort of want to have a limit, then you can enable these to look out for abnormalities. I think Uber mentioned the one implementation of these metrics based on Prometheus, which is in Pestismo. So you can we can enable these metrics and optionally track node level counters. And if you want to implement your own, you just have to derive this base stats reporter. That's a Velox base class, and you can implement your own sort of metrics reporter based on your in-house implementation. And there are 5 types that are supported: count, sum, average, rate, and histogram. All right, and some example metrics are, again, like I said, they're mostly at the global level or the node level or worker level. So you have cache string count, which is not per query, but it's sort of at the whole node level, and total task splits across all the tasks. The SSD cache that Minhan just talked about, and the exchange data bytes, and again, all those, pretty much you have counters at every resource and every operator. All right, so if you want to define a new metric, it's pretty easy. IBM's developer, Shin Matthew, recently added counters for S3 file system. So we wanted to track how many gets and how many puts are happening at the S3 level. And you just have to define three steps. So one, you define a counter name, and then you define the metric type, which if it is a count or the 5 types we saw earlier. And then you sort of record that metric at the call site. So whenever there's a get in the S3 file system implementation, you just record that metric there. All right. I think Krishna earlier also said, talked about the sprint plan with stats. I don't think he showed the output. So yeah, here the view is sort of overflowing. Sorry for that. But you can also actually tie in the stats with your plan node and get an idea about how each plan is actually performing. So for instance, a table scan, you can see how many are local reads, which is the SSD read, how many are actually prefetched, how many are being prefetched, how many RAM reads, which is async data cache reads, and how many are the storage reads, which is the S3 or the remote storage read. So you can sort of quantify all the performance metrics using these stats and metrics. All right. So for demo purposes, Prestismo exposes these APIs where you can use to query the stats and metrics. So at the task level, you can specify a task ID and get to know the status. You can also list all the tasks. If you want to get details of a specific task, you can use the get detail with the task ID. And to capture the metrics, there's another endpoint, which is info metrics, that you can use to get the Prometheus-style metrics. So let's see a quick demo and see what do we get from the execution. So I'm going to start again, for demo purposes, it's easier to just launch a Prestismo worker. So I'm going to enabling log level 1 just to see some log output. So you can see that the server is running at port 777 on my local machine at this IP. So I'm sort of hijacking the Presto protocol because I can control the task ID. So I'm actually going to start a task on this worker. So I have this Presto task JSON representation that I'm sending it to the worker. So I did that, and you can see here that the tasks with this ID started with 2 max drivers. And then I'm going to send some splits to this worker. Again, this is again a Presto JSON where I specify the splits. So here I'm going to, so you can see that it added 2 splits. I added 2 splits because there are 2 drivers, and it sort of finished the splits in 21 seconds. And so you can now, before the task gets clean, let's see the info metrics. So you can sort of get all the optional metrics, and then you can also get the details of the task here. So you can see all the metrics I mentioned at the driver level, at the task info, and the pipelines. You can see how many drivers are blocked. Yeah, a lot of details that you can deep dive and look at where your performances can be improved or what's happening. Cool, so the demo worked. Any questions? For Christian, me, or Minhan?
Great. I am not one to stand in the way of this group and happy hour, so find these guys at the happy hour if you have questions. Thank you so much. Day 1's done. I mean, I thought this was an awesome day. Really good stuff. Hopefully you'll be back for day 2. If you are coming back, which I hope you are, please don't forget your badges tomorrow. You need these tomorrow as well. And if you are leaving, make sure that you are with a Meta employee, if you're not a Meta employee, to leave the office. All right, happy hour is going to be outside, I think. It's a great day, so hope to see you there.